Usually when you look at how the world works, there's this comforting predictability to it. Like
Mhm.
you drop a glass on a hard floor, it shatters, you throw a ball, it arcs through the air and, lands exactly where gravity and momentum dictate.
Right. The math just works.
Exactly. The universe feels solid, it feels reliable. But today, we're going to invite you to step completely outside of that comfort zone.
Way outside.
Welcome to a new deep dive. Our mission today is to explore a phenomenon that is, frankly, absolutely impossible to explain in any traditional, everyday way.
Yeah, it really defies all logic.
It does, yet it contains the entire heart and the single defining mystery of quantum mechanics.
It is the ultimate mystery. And
Mm.
I want to give you a fair warning before we really dive in here.
Oh, please do.
Human intuition is a wonderful survival tool, but it's built entirely for large, everyday objects. Your brain is wired to understand, apples falling from trees or predators moving through the brush.
Stuff we can see and touch.
Exactly. To truly grasp the deep dive we're taking today, you are going to have to actively abandon your everyday common sense.
You live it at the door.
Right. Because the universe at its absolute smallest scale simply does not care about what makes sense to us.
I love that. And we are pulling all of this mind-bending material from one incredibly famous source, Chapter 1 of the legendary Feynman Lectures on Physics, Volume 3.
Oh, yeah. Richard Feynman was a master at breaking down the seemingly impossible.
He really was. Okay, let's unpack this. Our goal today isn't to get bogged down in heavy math or abstract jargon. You won't hear a single complicated equation.
Thankfully.
Right. Instead, we're going to walk a logical tightrope right alongside you to understand how matter actually behaves when we zoom all the way in.
And to do that effectively, we have to start by establishing a very firm baseline.
Okay.
If we're going to understand the bizarre behavior of atoms, we first need to agree on how normal things behave. Our source material sets this up beautifully with two classic analogies.
So we need to look at how particles act and then how waves act.
Precisely. Let's start with particles.
Okay, so if matter acts like rigid lumps, how does that look? Feynman gives us this great mental image of a bullet experiment.
Right, the machine gun.
Yeah, imagine a machine gun, and it's kind of a messy, erratic machine gun, right? And it's firing indestructible bullets. We're aiming this gun at an armor plate wall that has two vertical slits or holes cut into it.
Just big enough to let a bullet pass through.
Exactly. And behind that wall, there's a sandbox acting as a detector. We can move that sandbox back and forth to measure the probability of a bullet arriving at any given spot.
It's a brilliantly simple setup,
Mm.
and it establishes a crucial rule for how macroscopic objects function.
Right. If I try to picture this for you, it's like standing in your backyard throwing heavy baseballs at a hidden fence that has a couple of missing planks.
That's a great way to visualize it.
You just chuck the baseballs randomly. Most of them hit the solid and bounce off. But every now and then, one sails cleanly through a gap and hits the side of your house.
And the key detail here is that the baseballs, or the bullets in the machine gun experiment, always arrive in whole, discrete lumps.
Right. You never walk up to the house and find half a baseball or
Yeah.
a quarter of a bullet embedded in the sand.
No. It is one intact object arriving at one specific place. That is the defining feature of a particle.
It's a lump.
It's a lump. And because they're indestructible lumps, their behavior follows a highly logical rule. The probabilities simply add up.
Okay, what do you mean by that?
Well, think about it. If you break out one hole in the wall, you get a certain spread of bullets hitting the sand behind the open hole. Let's call that probability 1.
Right.
If you close that first hole and open the second, you get another spread of bullets behind that one. Probability 2.
Makes perfect sense.
Now, if you open both holes at the same time, the total chance of a bullet hitting any particular spot in the sand is just the sum of those two individual setups.
So P12 equals P1 plus P2.
Exactly. The bullets going through hole 1 don't care about the bullets going through hole 2. They don't interact. There's a complete lack of interference. The odds just stack up naturally.
Okay, so that is our particle baseline, lumps that just add up. But what's the alternative? Like, what happens if we use something fluid instead of solid lumps?
That brings us to our second baseline, waves.
Waves! Okay.
For this, we swap out the machine gun for a shallow trough of water.
Okay, let me visualize this. We put a little motor in the water, jiggling up and down to create continuous circular ripples.
Right.
And we keep the same wall with the two holes in the middle of the trough, but instead of a sandbox on the other side, we have a little sand beach that absorbs the waves.
Yep. And we also have a detector that measures the intensity of the water's motion as it hits that beach.
And immediately, The rules we just established change completely, don't they?
Entirely. Waves do not arrive in discrete, indestructible lumps. The intensity of a wave hitting the beach can be any size at all.
Because it just depends on how hard that motor is jiggling the water.
Exactly. The most important distinction, the thing that separates waves from bullets, is that waves interfere with each other.
Oh, I see. Because when that main water wave hits the wall with the two holes, is it like each hole becomes its own little pebble dropping into the pond?
That's exactly it.
Like two brand new sources of ripples spreading out on the other side.
You've hit on the exact mechanism. As those two new sets of ripples spread out from the two holes, they overlap. And this is where things get really interesting.
Okay.
If the peak of a wave from the first hole meets the peak of a wave from the second hole, they push the water up even higher.
Oh, they combine.
Right, they combine to construct a much larger wave. That's called constructive interference.
Right, they're working together.
But if the peak of one wave meets the lowest point, the trough of another wave, they're completely out of sync, basically out of phase by a difference of pi.
So the first wave is trying to pull the water up, while the second is pushing it down at the exact same moment.
Exactly. They cancel each other out entirely, and the water stays perfectly flat. That is destructive interference. You get zero intensity.
Wow.
So you can't just add the intensities together like you do with independent bullets. The math requires a whole complex interference term to account for that overlapping canceling behavior.
So just to summarize our everyday world, bullets are independent lumps that just add up. Water waves are continuous fluid energy that creates these beautiful overlapping patterns of peaks and flat spots.
That is our intuitive macroscopic world.
We get it. It makes sense. But now we take our entire experiment and we shrink it all the way down to the atomic level. We're going to find out which set of rules electrons follow.
And this is where that everyday common sense we talked about starts to completely fracture.
So we set up a thought experiment scaled for atomic particles. Instead of a machine gun or a water motor, we have an electron gun.
Basically a heated tungsten wire spitting out electrons.
Right. We have our microscopic wall with two tiny holes, and behind it, a movable Geiger counter to detect the electrons as they arrive. We turn on the gun and listen to the detector. We hear sharp, erratic clicks. Click, 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 click. And every single click is exactly the same volume.
That's a crucial detail.
Yeah, because if you lower the temperature of the wire to slow down the read of electrons, you just get longer pauses between the clicks. The loudness of the click never changes.
Which leads any logical observer to a very classical conclusion. The electrons are arriving as complete, intact entities.
Like lumps.
Just like the indestructible bullets, yes.
Okay.
Electrons always arrive in lumps. There are no half clicks. There are no partial electrons hitting the wall.
Okay, hang on. I have to admit some confusion here.
Sure.
If they're arriving in whole, indestructible lumps, exactly like bullets, then what's the big mystery? Shouldn't their probabilities just add up like bullets?
You would think so.
Couldn't they just be, I don't know, bouncing off the edges of the tiny holes or ricocheting wildly and taking incredibly complicated looping paths before they hit the detector?
It is a completely natural urge to try and force the electrons into a classical framework, like ricocheting bullets. But the data from the experiment shuts down that bouncing theory entirely.
Really? How?
When researchers measured the arrival rates of the electrons, they found something astonishing. There are certain dead spots on the backstop where, if both holes are open, almost no electrons ever arrive.
Sure.
But if you block off one of the holes, the number of electrons arriving at that exact dead spot actually increases.
Oh, wait. That makes no sense. Closing a path shouldn't increase the traffic reaching the destination. Not unless the open paths were somehow actively blocking each other.
Exactly. Take that logic a step further.
Yeah.
If they were just taking complicated ricocheting paths like little baseballs, closing a hole wouldn't cause a massive surge in arrivals at a dead zone.
Right.
It proves they aren't taking classical paths. And this reveals the mind-bending truth of the double-slit experiment. Even though electrons definitively arrive in discrete whole lumps exactly like bullets, their overall probability distribution creates an interference pattern exactly like water waves.
Wait, so P12 does not equal P1 plus P2?
Not at all.
Okay, let me try to visualize this absurdity. They hit the detector one by one, like solid little baseballs. Click, click, click.
Right.
But if you step back and let enough of those baseballs hit, the pattern they paint on the back wall isn't two clumps. The pattern looks exactly like the interfering ripples of a water wave.
Yep.
With peaks of high impacts and completely flat dead zones where nothing hits. So they act like solid particles when they arrive, but they act like a wave while they're traveling.
Yes. They are somehow interfering with themselves in transit.
That's insane, because human intuition demands an explanation for how a single, solid lump can interfere with itself like a scattered wave.
We want to see it happen.
Right. Our natural instinct is to say, let's just look at them. Let's peek behind the curtain and watch the electrons while they travel.
So we design a new experiment.
Exactly. We put a really strong light source directly behind the wall, right between the two holes. Electrons scatter light.
They do.
So the idea is, right before we hear the Geiger counter click, we should see a tiny flash of light at hole 1 or a flash of light at hole 2. That'll tell us exactly which path the lump took.
And when we run this experiment, we find that our basic assumption, what Feynman calls proposition A, actually holds up perfectly.
Oh, it does.
It does. For every single click of the detector, we see a flash at hole 1 or we see a flash at hole 2. We never see a flash at both holes simultaneously.
Right.
The electron definitely, demonstrably chooses a single hole.
Okay, so mystery solved, right? They're
Sure.
just lumps taking one path.
Not quite.
Oh, no.
What's fascinating here is what happens at the detector. The moment we turn on the light and start keeping track of the flashes, we look at our final distribution pattern on the backstop.
Yeah.
And that beautiful wave-like interference pattern has completely vanished
Whoa. Wait, just from turning on a light?
just from turning on the light. The distribution reverts to acting exactly like the machine gun bullet.
Kidding.
I'm not. The probability with both holes open becomes exactly equal to the sum of the probabilities of each hole alone.
Right.
So P12 prime equals P1 prime plus P2 prime.
That's wild.
The very act of looking at the electrons, of measuring their path, fundamentally changed their motion.
Okay, let's unpack this, because my brain is instantly trying to find a loophole here.
Most brains do.
Okay, the light source. We put a bright light behind the wall to see the electrons. But light isn't just invisible magic, right? It has energy, it exerts force.
It definitely does.
So this feels like, okay, I feel like we're trying to find a ping pong ball in a pitch black room by throwing bowling balls at it.
Ah, I like that.
Right. Every time a bowling ball, which is what hits the ping pong ball, the electron, we hear a massive crash and say, aha, there it is.
Right.
But obviously the impact just knocked the ping pong ball wildly off its original course. The bright light is giving the electrons a physical jolt, and that jolt is what ruins the delicate wave pattern.
That is a brilliant way to picture it. The light is absolutely jolting the electron. So you might naturally think to try and fix it by throwing something lighter.
Yeah.
If a bowling ball is too heavy, maybe we use handfuls of sand. In our experiment, that would mean using a gentler light.
Right. We just turned down the dimmer switch. Less intensity, fewer bowling balls.
But here we run into another strange quantum reality. Light is also lumpy.
Wait, what?
Yeah, light travels in discrete little packets called photons. Turning down the brightness on a dimmer switch doesn't make the individual photon smaller or softer.
It doesn't.
No, it just means the light source is spitting out fewer of them.
Oh. So we just have fewer bowling balls flying around the dark room, but the ones that do hit are still just as heavy.
Precisely. And the experiment reflects that perfectly. With a dim light, some electrons actually manage to sneak through the holes without hitting a photon at all.
Sneaky electron.
Very sneaky. We hear a click on the detector, but we see no flash. And here's the real kicker. If we look at the data just for those unseen electrons, their impacts build up to form the wavy interference pattern again.
Wow.
But the electrons that do happen to scatter a photon, the ones we actually see with a flash, they get jolted and their impacts build up like the boring bullet pattern.
Okay, so dimming the light doesn't work because the individual projectiles are still too heavy. We need physically smaller projectiles. What if we change the color of the light?
Okay, where are you going with this?
Like if we use redder light or infrared or even radar, we're using longer and longer wavelengths.
That is exactly the right track to take. In physics, momentum equals Planck's constant divided by wavelength. So longer wavelengths inherently carry less momentum.
A gentler jolt.
A gentler jolt.
So we just keep dialing up the wavelength, making the light softer and softer until the jolt is so weak that it doesn't disturb the electron's path, but we can still see the flash. We beat the system, we can see the path and keep the wave pattern.
But here we walk right into nature's ultimate trap.
Oh no, what is it?
As the jolt gets gentler, you're right, the interference pattern slowly starts to return on the back wall. But there's a terrible, unavoidable catch. Because light operates as a wave, There's a fundamental limit to how sharply it can resolve an image, and that limit is tied directly to its wavelength.
Okay, what does that mean in practice?
Think of it like trying to paint a highly detailed portrait. A short wavelength is like a fine-tipped pen. A long wavelength is like a thick roller brush. As we make the wavelength longer to soften the jolt, the flashes of light we see become fuzzier and wider.
Oh no, you've got to be kidding.
I'm not. The exact moment the wavelength is long enough and the jolt is gentle enough to allow the interference pattern to fully return is the precise moment that the flash becomes too big and fuzzy to tell whether it originated from hole 1 or hole 2.
That is so frustrating.
Nature perfectly balances the scales against us.
It really feels like the universe is actively censoring the information. Like, it simply refuses to let you know two things at once.
It really does. And it's not just a technological limitation of our equipment. It is a fundamental law of reality. This brings us to Heisenberg's uncertainty principle.
Right, I've heard of that.
Nature fundamentally forbids us from designing any apparatus that can tell us which hole the electron passes through without simultaneously destroying the interference pattern.
Yeah.
And this is governed by a precise, fixed constant of nature.
Oh, the h-bar constant.
Exactly. Planck's constant divided by 2 pi, it's about 1.05 times 10 to the negative 34th joule seconds.
Which is incredibly tiny.
Unimaginably tiny. But you can think of it as essentially the universe's ultimate pixel size, a hard mathematical floor on how closely we can zoom in before reality just blurs out.
But scientists are incredibly stubborn. Surely someone tried to find a workaround.
Oh, of course.
What if we don't look at the electron at all? What if we look at the wall? Feynman proposed a brilliant workaround for this in the source material, right?
Figure 1/6, yes.
Yeah, what if we mount the wall with the two holes on a set of microscopic rollers? We don't shine any light, no bowling balls. We just let the electron hit the wall and go through a hole.
Okay, I'll follow.
Since the electron changes direction when it goes through, it must push back on the wall, right? Like a tiny kickback.
Newton's third law, yep.
So if it goes through the top hole, the wall recoils down a tiny bit. If it goes through the bottom hole, the wall recoils up. We just measure the momentum of the wall's recoil to see which hole the electron used. No photons, no jolts to the electron.
It is an incredibly clever thought experiment, honestly. But the uncertainty principle is ironclad.
Really? Even then?
Even then, to measure the recoil of the wall and deduce which hole the electron went through, we have to measure the wall's momentum with extreme precision before and after the electron passes.
Okay.
But according to Heisenberg, the more precisely you know an object's momentum, the less precisely you can know its position.
Ah, it's that seesaw again.
Yes. If we know the wall's momentum accurately enough to determine the electron's path, our knowledge of the wall's exact vertical position becomes completely uncertain.
And if we don't know exactly where the wall is,
Then we don't know exactly where the holes are. And if the holes are effectively shifting up and down unpredictably, the resulting wave wiggles on the backstop get completely smeared out anyway.
wow.
The interference pattern is destroyed once again. You cannot cheat the math.
So what does this all mean? If we can never know the path without destroying the result, what does this mean for the future of science? I mean, the whole point of classical physics is predictability.
Exactly.
We calculate the trajectory of the cannonball so we know exactly where it will land.
It means we had to accept a massive philosophical retrenchment. If we connect this to the bigger picture, physics has officially given up on predicting exactly what will happen in a definite circumstance.
Given up.
Given up. We can no longer tell you where a single electron will go. We can only predict the odds. We can only compute the probability of different events occurring.
But surely that's just because our microscopes aren't good enough yet. What if the electron has some kind of internal machinery? Hidden variables.
Like what?
Like a tiny internal clock or a microscopic compass that decides its path before it even leaves the gun. We just can't zoom in close enough to see the tiny gears turning.
It's a comforting thought. But Feynman addresses that exact hope and dismantles it using pure logic.
How so?
If the electron had internal machinery that predetermined its path and its destination before it even reached the wall, then it would be acting entirely independently of the second hole. It has already made up its mind.
Okay.
If that were true, the probability of electrons arriving at the detector would simply add up, just like the macroscopic machine gun bullets we talked about at the beginning.
But they don't add up.
They don't. The interference pattern proves they don't. Therefore, there can be no predetermined hidden variables deciding the path. The mystery is absolute. Nature at its core is not predictable. It is fundamentally probabilistic.
Wow. Let me try to wrap my head around this entire journey we just took.
It's a lot.
It really is. In our everyday macroscopic world, things like bullets act like solid, independent lumps. Things like water act like continuous interfering waves.
Right.
But when we zoom down to the foundation of reality, to the quantum level, everything is both and neither. The universe operates on this razor-thin logical tightrope where unobserved possibilities literally interfere with one another.
Beautifully said.
And the absolute second we demand a definitive answer, the second we try to force reality to pick a path by observing it, the magic vanishes and it behaves like a normal bullet.
It is a profound shift in how we understand existence. And if you're willing to follow that logic to its absolute conclusion, our source material offers one final, deeply unsettling thought.
Oh boy. Unsettling how?
The text notes something fascinating in Figure 1.5 about those macroscopic machine gun bullets we discussed at the very beginning.
The solid lumps.
Right. According to quantum mechanics, those massive, heavy bullets actually do have a quantum wave nature. They actually do have interference wiggles.
Wait, seriously, a flying piece of lead has a wave pattern.
It does. But because a bullet has so much mass, its wavelength is incredibly, infinitesimally tiny. The wave wiggles are packed so tightly together that any macroscopic detector we could ever build, even the sand in the box, is entirely too crude to measure them.
You just can't see them.
Exactly. The detector straddles millions of wiggles at once, blurring them together. It averages them out into what looks to us like a perfectly smooth, classical probability curve.
So it's just smudged into a straight line because our tools are too big.
Yes. Now, I want you to turn that realization back on yourself. You are a macroscopic object.
What? I try to be.
You were constructed entirely out of these strange quantum particles. Every atom in your body, every neuron firing in your brain, every single photon hitting your eye right now is governed by strange probabilities and unseen interference. This raises an important question. If the very foundation of your body and your world is built on this mysterious shifting quantum reality, is the solid, predictable, bullet-like world you experience every day just an illusion?
That is, wow.
Is your entire reality just a trick of your giant, clumsy macroscopic senses, averaging out the quantum wiggles of the universe into a comforting blur?
That is a genuinely heavy thing to realize. The idea that everything we touch, everything we feel, and everything we see is just a blurred out average of a fundamentally mysterious universe.
It changes how you look at everything.
It really does. I want to invite you, our listener, to really chew on that thought. Let it rattle around in your mind the next time you drop a glass or throw a ball until we see you again for our next deep dive.
Right now, you are sitting somewhere, probably assuming the chair or whatever surface is beneath you is completely solid.
Which is a pretty fair assumption to make, right?
Yeah, exactly. It feels completely solid. But according to the rules of classical physics, you should actually be falling right through it.
Right.
I mean, the atoms in your body and the atoms in that chair are mostly empty space. And the charges inside them should, theoretically, just collapse into each other.
They absolutely should. Opposites attract.
So to understand why you aren't plummeting toward the center of the Earth right now, we basically have to completely rewire how we think about reality.
It really is a total rewiring.
And welcome to our deep dive. We are looking at a masterclass in this exact rewiring today. It's Richard Feynman's Lectures on Physics, Volume 3, Chapter 2.
A classic.
It really is. And our mission in this deep dive is to explore the incredibly messy, completely mind-bending relationship between waves and particles.
Yeah, because it requires a profound shift in perspective. If you think about your everyday life, things are usually categorized pretty neatly. Like a wave is just a wave.
Exactly. Like the ripples spreading out on the surface of a pond. You know, you can't hold a ripple.
Right.
And a particle is a particle, like a baseball. You can hold it, you can throw it, you can track its exact path.
But, as this source material so brilliantly demonstrates, when we zoom down to the microscopic level, well, those comfortable everyday experiences completely fail us.
They fall apart entirely.
Yeah.
To get in the right headspace for this, imagine a backdrop of massive chalkboards just completely covered in complex wave equations.
Sitting right next to vast, sprawling star charts or something.
Yeah. Because what we're exploring today is what Feynman treats as a sort of half-intuitive bridge.
Okay.
It's a way to get a qualitative gut feeling for quantum mechanics using familiar ideas before anyone has to dive headfirst into the pure abstract math.
Okay, let's unpack this. Because if a microscopic particle isn't really a particle in the way we think of a baseball,
Right.
and a wave isn't really a wave in the way we think of an ocean ripple, then what exactly is the universe made of? Like, what is the actual stuff? So The framework we're looking at answers that by introducing the concept of probability wave amplitude.
Probability wave amplitude.
Yeah. In this quantum reality, the universe simply doesn't deal in absolute certainties about where a tiny particle is or what it's doing.
Right, it's all about chances.
Exactly. We can only talk about the likelihood of an event occurring. Think of the amplitude just as the height or the intensity of a wave.
Okay.
The higher that amplitude is in a specific spot, the higher the probability that you will actually find the particle there if you go looking for it.
Which is such a wild concept to wrap your head around, mostly because the math creates this incredibly frustrating paradox.
Oh, it really does.
Let's say you have a wave whose height is constant everywhere.
Yeah.
Just this continuous, perfectly regular oscillation spanning out infinitely across space.
Like a perfect sine wave.
Right. The math tells us that the particle associated with that uniform wave has a perfectly definite speed and energy.
Yeah.
We know exactly how fast it's going.
We have that locked down.
But because the wave's height is the same everywhere, the probability of finding the particle is the same everywhere. We have absolutely no idea where the particle actually is.
The uncertainty in its location becomes practically infinite.
It's like trying to pinpoint the exact location of a single specific drop of water by looking at a massive uniform ocean swell.
I love that analogy.
If the wave is everywhere, the drop could be anywhere. You know the energy of the swell, you know the speed of the swell, but where is that one drop? It's impossible to say.
Exactly.
But wait, why can't we just build a better microscope?
Yeah.
Or, a better tool to just look at it and find out where it is?
Because nature demands a trade-off. What's fascinating here is that to actually know a particle's location, to confine its probability to a specific searchable region, you have to change the wave.
Okay, how?
You need what the material calls a shortwave train. If you look at figure 2.1 in the text, you basically have to pinch the wave so it only exists in a small localized area.
So you're chopping it up.
Basically, yeah. But a short, chopped-up wave doesn't have a unique, definite distance between its peaks. Because you cut it short, the wavelength gets blurry.
Oh, I see.
And since momentum, which is the particle's speed and direction, is directly tied to that wavelength, your knowledge of the particle's momentum suddenly becomes blurry too.
And the really crucial point here for everyone listening is that this isn't just some spooky quantum weirdness.
Not at all.
This indefiniteness is a basic property of all waves, even everyday sound waves.
Yes, exactly. If you hear a super short microscopic blip of a sound, it's virtually impossible to tell exactly what pitch it is.
You need a sustained note, a longer wave, to actually identify the frequency.
It's the exact same math.
So how does this wave math translate to physical experiments we can actually build and see?
Well, physicists use a classic setup for this. The deep dive goes into figure 2.2, where particles pass through a single slit.
Okay, set the scene for us.
Imagine a beam of particles, let's say electrons. They are coming from very far away and flying toward a wall. And in that wall is a single, narrow, horizontal slit.
Got it.
Because these electrons came from far away on a totally flat horizontal trajectory, we know their vertical momentum is exactly zero.
Right, they are moving up and they are moving down, just flying perfectly straight and level toward the wall.
Exactly. And let's say that horizontal slit has a specific tiny width, which they call width B.
Okay.
Once an electron passes through that slit, we suddenly know its vertical position with considerable accuracy. It has to be somewhere within that tiny gap plus or minus B.
Because it just went through it.
Right. By forcing it through the wall, we've gained its position.
But because of the wave nature of matter, waves diffract. They spread out.
They always do.
Anyone who has ever watched ocean waves squeeze through a narrow gap in a breakwater has seen this. The waves fan out in a semicircle on the other side.
And that fanning out is the crucial mechanism here. Because the electron's probability wave diffracts and fans out after squeezing through the slit, there is now a chance that the electron will end up moving up or down.
So it's not flying straight anymore.
Right. It will hit a detector on the far side at various vertical points. By forcing the particle to reveal its vertical position, we caused its wave to spread.
And we completely lost our certainty about its vertical momentum.
Exactly. We gained position, but we destroyed our knowledge of its momentum.
Now, I have to push back here, because folks using plain common sense, and the text mentions this too, love you, to point out a supposed flaw in this logic.
Oh, the historical argument.
Yeah, they say, wait a minute. I knew the vertical momentum was zero before it went into the slit, and now it has hit the detector, so I know its final position. I know both. The uncertainty principle is wrong.
The framework addresses this exact objection quite firmly because it highlights a fundamental misunderstanding of what physics is actually trying to do.
Which is,
Quantum mechanics is a predictive theory. It is not a historical one. Knowing what a particle did in the past is entirely useless.
useless for making predictions, you mean?
Exactly. The uncertainty relation refers to the predictability of what the particle will do next.
It's like knowing a lottery ticket had the winning numbers yesterday. I mean, that information is completely spent. It doesn't help you predict the numbers for tomorrow.
That captures the logic perfectly. You knew the electron's momentum before the slit, but the very act of forcing it through the slit destroyed that momentum for the future.
You cannot use your historical knowledge to predict its future trajectory.
No, you can't. And if we look at the opposite scenario in Figure 2.3, using a diffraction grating, the strictness of this rule becomes even more apparent.
And a grating being a surface with thousands of tiny, closely spaced parallel slits, rather than just one single slit.
Yes, if you want to measure a particle's momentum incredibly precisely, you measure its wavelength by seeing how it scatters off this massive grating of thousands of slits. But to get a sharp, precise measurement, you need a very long wave train hitting the entire grating simultaneously. All the grooves need to be engaged by the wave at once.
What if a scientist tries to cheat the system, though? What if they say, well, I want to know its exact position too, so I'm going to send in a really short wave train, just hitting a tiny piece of the grating?
The physical reality prevents that from working. If you shorten the wave train to find the position, the wave only hits a tiny fraction of the grating.
So what happens?
The interference pattern gets muddy, the angular spread gets huge, and the grating simply stops working properly. The moment you narrow down the position, the tool you were using to measure momentum just breaks down.
Which gives us our first massive takeaway for you listening right now. This isn't about clumsy tools or human error or, bad microscopes.
No, it's baked into the universe.
Exactly. There is a fundamental mathematical limit built into the very fabric of the universe regarding what you or anyone or even a supercomputer can know at any given time. The universe strictly enforces this trade-off.
It's a hard boundary on knowledge itself. And once you accept that boundary, you can start explaining things that classical physics utterly failed to explain.
Right. Which brings us to sifting neutrons and the weirdness of solid matter. Because if these probability waves spread out and diffract when they hit a single slit or a flat grating, what happens when they hit a three-dimensional block of solid matter?
That's where things get really interesting.
Because if you think about it, a solid crystal is basically just millions of microscopic slits layered on top of each other in 3D.
Yes, a crystal is a highly structured array. The text, specifically in Figure 2 to 4, talks about unit cells.
Which are what, exactly?
They are basically a repeating 3D wallpaper pattern of atoms. When a wave, say a beam of particles, enters this crystal, it scatters off these endless planes of atoms.
Okay.
But it doesn't scatter in all directions equally. It only reflects strongly in specific directions where the scattered waves from all the different planes happen to be in phase, meaning their peaks line up.
And if the peaks don't line up,
Then they cancel each other out entirely.
this leads to one of the most mind-bending practical applications in the material. It's around figures 2.7 and 2.8. They talk about taking neutrons, which are definitively particles with mass, found inside atomic nuclei, and firing them into a long, thick block of solid graphite crystal.
Right. And the planes of atoms inside the graphite basically act like a dense maze. They bounce the neutrons around, diffusing them through the solid block.
But the wave nature of those neutrons dictates exactly how they bounce.
Exactly. The mathematical condition for them to reflect off the crystal planes depends entirely on their wavelength compared to the physical distance between the atomic planes.
And the math shows something incredible here.
It does. If a neutron's wavelength happens to be larger than twice the distance between the crystal planes, the equation for reflection literally has no solution.
Meaning, it physically can't bounce.
It cannot bounce. It simply passes straight through the crystal planes without scattering at all, as if the solid graphite were as transparent as clear glass.
Here's where that sieve analogy is incredibly helpful. Usually, a physical sieve or a colander in your kitchen catches the big stuff like pasta or boulders and lets the tiny grains of sand fall through the holes.
Right. That's how a normal sieve works.
But this solid graphite block does the exact opposite. Because momentum is inversely proportional to wavelength, the fast, high-momentum neutrons have very short, tightly packed wavelengths.
They act like the sand.
Yes, They act like the sand. They bounce around, get scattered out the sides, and get completely lost in the graphite.
Well, the slow neutrons do the opposite.
Right. The very slow, low-momentum neutrons have these long, stretched-out wavelengths. They are the boulders, and they just glide right through the microscopic caps.
Totally counterintuitive.
So out the far end of this solid block of graphite, you get a perfectly pure beam of incredibly slow, long wavelength neutrons, sifting solid particles through a solid block based entirely on their wave properties.
And if we transition that logic, right, if we follow that logic down from a massive block of graphite to the individual atoms themselves, we finally solve the mystery of why atoms act as physical obstacles in the first place.
Which answers a question that tormented classical physicists.
Yeah.
Why doesn't the atom collapse?
Exactly. You have a negatively charged electron orbiting a positively charged nucleus. Classically, the electron should just radiate all its energy, spiral inward, and crash into the nucleus.
Because the most stable arrangement in classical physics for a positive and negative charge is sitting right on top of each other.
Yes.
Wait, so if the positive nucleus is pulling the negative electron in, why doesn't matter just implode? What stops the crash?
The uncertainty principle saves us.
Really? How?
Remember the trade-off we discussed with the slits? If the electron gets pulled too close to the nucleus, its position is suddenly being confined to a very tiny area. We are severely shrinking its position uncertainty.
Oh, and nature strictly forbids knowing both.
Mm-hmm.
So if the space shrinks, the momentum has to go crazy.
Exactly. The electron's momentum must increase dramatically. And a higher momentum means a much higher kinetic energy. The harder the nucleus pulls the electron in, forcing it into a smaller space, the more violently the electron jiggles and resists being confined.
So it reaches a kind of stalemate, a minimum energy state where the inward pull of the electrical charge perfectly balances the violent outward push of the quantum kinetic energy.
We call that compromise, the Bohr radius.
Oh, wait, so is that why? I'm not falling through this chair right now.
That is the exact reason you don't fall through the floor right now.
Oh, wow.
When you sit down or stand up, the atoms in your body press against the atoms in the chair or the floor. Classical physics says all those orbiting electrons should just squish together into a tiny, dense point under your weight.
But they don't.
But they don't, because the electrons in the chair resist being squeezed. Confining their space forces their kinetic energy to wildly spike, which creates an immense outward pressure.
So the solidness of the world you touch, the reason a chair holds you up, is purely a quantum mechanical effect.
It is entirely quantum.
The strength of matter isn't mechanical, it's probabilistic, it's just electrons refusing to be pinned down.
That's a great way to put it. Now, if atoms are locked in this ground state compromise, it raises the next logical question. How do they interact with the rest of the universe? Can they absorb or release energy?
Like, how does a neon sign actually glow?
The material tackles this by looking at Figure 2-9, the energy diagram of an atom. A free particle flying through the vacuum of space can have any random amount of energy it wants. It can travel at any speed.
Okay.
But a bound electron, trapped in that quantum tug-of-war we just talked about, doesn't have that luxury. It can only exist in specific, strictly permitted energy levels.
Like standing on a staircase.
Yeah.
You can be on the first step or the second step, but you physically cannot hover in the empty air between the steps.
Right. We call these excited states energy level 1, level 2, level 3. But an electron doesn't like being in an excited state forever.
It wants to go back down.
Eventually, it drops back down to a lower state. And when it drops, say from step 3 down to step 1, it has to get rid of that extra energy. It does this by emitting a photon of light.
But if the atom drops from level 3 down to level 0, the ground state, is it completely random what color or frequency of light it shoots out?
Not at all. If we connect this to the bigger picture, the frequency of the emitted light is perfectly mathematically precise.
Okay.
The energy of the light is exactly equal to the difference in energy between the two levels. This leads to something called the Ritz combination principle.
The Ritz combination principle.
Yeah, it's essentially the arithmetic of light. The frequency of the light emitted when an electron drops all the way from level 3 to level 0 is exactly equal to the sum of the frequencies if it had taken 2 smaller steps.
So dropping from level 3 to level 1 and then from level 1 down to level 0.
Exactly. The sums match perfectly.
It's like if you jump from the third floor to the ground, the energy of your impact is exactly the same as if you jump to the first floor, paused, and then jumped the rest of the way.
That's a very visceral way to think about it.
But why are these levels so strictly locked in? Why steps and not a ramp?
The most elegant way to picture this is to think of the electron not as a tiny ball, but as confined waves in an organ pipe.
Oh, I love this analogy, because if you blow air into a physical organ pipe, you don't just get a chaotic blast of white noise.
Right, you get a specific note.
The physical dimensions of the pipe only allow certain resonant sound frequencies to vibrate within it. The sound wave has to fit perfectly inside the physical space, with the nodes of the wave hitting the edges of the pipe.
Exactly. If the wave doesn't fit perfectly, it reflects back on itself out of phase and destroys itself. It cancels itself out.
So it's the exact same logic for the atom.
It is. The confined probability waves of the electron can only exist if they perfectly fit the space around the nucleus. Only certain exact wave patterns, and therefore only certain exact energy states, are allowed to exist without canceling themselves out entirely.
Which beautifully explains why different elements emit specific signature colors of light.
Yes, it all comes back to the waves.
But connecting all these concepts brings us to a massive philosophical cliff edge.
Oh, definitely. The philosophical fallout here is huge.
Because if, at the fundamental level, particles are just these hazy probability waves that jump between allowed states unpredictably, does this mean the universe is entirely random?
Right. What happens to determinism? The idea that cause always leads to a predictable effect.
Exactly. The deep dive tackles this philosophical fallout head-on. It starts with that old riddle. If a tree falls in a forest and no one is there to hear it, does it make a sound?
And from a physics perspective, the text argues the answer is an absolute yes.
Even without a conscious observer to hear it, physical traces remain. The sound waves shake the leaves. A falling branch might rub against another and leave a microscopic scratch. The event happened, objectively, regardless of human consciousness.
And there's also a strong defense of classical physicists here, which I think is important.
Because a lot of people today look back and say, wow, those classical guys were so stupid for assuming an electron had an exact position like a baseball.
Yeah, but the text aggressively defends them. Science absolutely must make constructs. You have to extend the concepts you know into unknown regions in order to make predictions.
You have to stick your neck out.
You do. If you don't assume something is there independent of your experiment, you can't predict anything. Assuming an electron had a definite position was completely sensible at the time.
Pushing that classical theory until it finally broke was the only way to discover quantum mechanics in the first place.
Exactly.
So what does this all mean for us? People love to use quantum indeterminacy. The idea that you can't exactly predict when an atom will emit a photon to explain the human mind.
Right, free will.
Yeah, they say, aha, physics isn't perfectly predictable, therefore that's where human free will lives. That's why the universe isn't just a cold, mechanical, ticking clock. Is that a fair leap to make?
Well, this raises an important question. And the material delivers a massive, almost shocking counterpoint to that idea. You actually don't need quantum mechanics to escape a mechanistic, perfectly predictable universe.
Wait, really?
Because classical physics is practically indeterminate, too.
But classical physics is usually described like a giant cosmic pool table. If you hit the billiard balls exactly right and you know the math, you can predict where they will bounce forever.
In pure abstract theory, sure. If you knew the exact position and velocity of every particle in a box of gas, classical laws say you could predict its future exactly. But think about the reality of finite accuracy.
Okay, meaning we can't measure perfectly.
Right. Let's say you measure the position of one billiard ball or one atom, but you have a microscopic error in your measurement. Let's say your measurement is off by just 1 part in a billion.
Which is an incredibly tiny error.
Oh,
For
man.
all intents and purposes, you have it exactly right.
But then that atom hits another atom. Because of that 1 in a billion error, you miscalculate the angle of the bounce slightly, so your error for the next collision is a bit larger.
Oh, I see where this is going.
This error magnifies logarithmically with every single collision. Because atoms are colliding millions of times a second within a fraction of a second, that microscopic error has compounded so massively that all your predictive power is completely gone.
Think about water falling over a massive dam. If you stand near the bottom of a dam, every now and then a drop of water splashes out and lands right on your nose. It feels completely, utterly random.
But according to strict classical physics, that drop landing on your nose was determined by the precise wigglings of the water molecules way up at the top before they even went over the edge.
But because the tiniest microscopic irregularities at the top are magnified exponentially as the water falls and crashes against itself, the final result, the drop hitting your nose, becomes completely random for all practical purposes.
Yes, you would need absolutely infinite precision to predict it, and infinite precision is physically impossible.
So practical unpredictability is built right into classical physics.
It is. You can find a time limit, usually a fraction of a second, after which you cannot predict what will happen next, no matter how good your starting data was.
So it is completely unfair to say we needed quantum mechanics to release us from a perfectly predictable universe.
Classical physics was already delightfully chaotic. You don't need quantum mechanics to escape a mechanistic universe. Uncertainty is everywhere.
This has been such a phenomenal journey. Thank you so much for walking us through this.
Oh, it was a pleasure. It truly forces you to rewire your understanding of the physical world from the ground up.
It really does. We started with the bizarre, hazy probability waves of quantum mechanics, where knowing a particle's speed means losing its location. We saw how squeezing those waves creates a violent pushback, which is the very mechanism that keeps electrons from crashing into the nucleus, giving the chair you're sitting on its physical strength.
A literal lifesaver.
Truly. And finally, we arrived at the splashing water of classical physics, realizing that uncertainty isn't just a failure of our tools. It is a fundamental, inescapable feature of nature at every single scale.
Beautifully said.
And I want to leave you, listening to this, with a final thought to mull over as you go about your day. If a fully predictable classical universe loses all its predictability in a fraction of a second due to a microscopic rounding error, does the true fundamental nature of reality even matter to our daily lives? Whether it's quantum probability waves collapsing or just the infinitely chaotic wiggling of splashing water magnifying as it falls. Maybe the universe is simply built to surprise you, regardless of the math happening beneath your feet. You know, if I throw a baseball at a wall with two open windows, I know exactly what's going to happen. It goes through window A or it goes through window B. It's just a clean physical trajectory.
Right, it's a binary reality. I mean, we can trace its path perfectly from your hand right to the wall, and that classical mechanics framework is, comforting because it aligns perfectly with our macroscopic logic.
Yeah, it makes sense to our brains. But shrink that baseball down to the size of an electron, and reality just it breaks. It doesn't just pick a window. It seems to go through both. It interferes with itself, and it hits the wall behind them in this pattern that's completely impossible for a solid object. So, welcome to your custom deep dive.
Glad to be here.
Today, for you listening, we are bypassing the really dense differential equations of quantum physics to look at why the universe actually behaves this way. And we're drawing straight from Chapter 3 of the legendary Feynman Lectures on Physics, Volume 3.
Yeah, and Feynman took a very specific approach in this volume. It was really a pedagogical experiment.
Yeah.
He abandoned the traditional curriculum entirely. Usually that forces students to spend years solving Schrödinger's wave equations for basic states before they even touch the advanced quantum mechanics.
Which sounds exhausting, honestly.
No, it is. So he decided to teach the advanced concepts like particle spin and indistinguishability first.
Because mathematically, those advanced concepts are actually simpler. You don't need a background in complex calculus to understand this chapter. The math relies on basic algebra. But before we get into the equations, Feynman issues this really stark warning.
Right, the big caveat.
Yeah, he says we have to completely discard our intuitive reliance on physical, three-dimensional space when we picture these systems.
Exactly. Because when physicists say an electron behaves like a wave, the immediate temptation is to visualize, ripples on a pond.
Right, like water.
Yeah, but if you have a system with two particles, their probability wave doesn't actually exist in 3D space. It exists in a six-dimensional mathematical space.
No. 6 dimensions.
I know, it's wild. The mathematical abstraction is the reality. You really have to let the rules of the algebra guide you rather than trying to map the behavior back to everyday physical objects.
Okay, let's unpack this and get straight into that algebra. To understand the strangeness of quantum mechanics, we have to look at how it calculates the likelihood of an event occurring. Let's take a simple scenario. Say an electron moving from a source, which we'll call S, to a detector, which we'll call X.
Right. So in classical probability, if an object has two possible paths to a destination, you just determine the percentage chance of path A, the percentage chance of path B, and you add them together.
50% plus 50%.
Exactly. But quantum mechanics discards that approach entirely. You do not add probabilities, you add probability amplitudes.
And Feynman introduces Paul Dirac's bracket notation here to represent this, right?
He does, yeah. Instead of writing out a massive equation, Dirac shorthand just uses brackets. You put the start state on the right, the end state on the left, separated by a vertical line.
So reading right to left, a bracket containing X and S simply represents the amplitude for a particle to travel from S to X.
You got it. And that bracket represents a complex number. It has both a magnitude and a direction, or a phase. The entire architecture of the universe is built on the rules for combining these complex numbers.
Wait, so if a particle has two possible, indistinguishable routes to reach a detector?
Then you add the amplitude of the first route to the amplitude of the second route. Only after you have that combined amplitude do you calculate the actual real-world probability.
Okay, and you do that by squaring the absolute value of the total sum, right?
Exactly.
And what if the movement happens in stages? Like, say the electron goes from the source S to a specific slit, and then from that slit over to the detector X.
Well, for sequential events, you multiply. You take the amplitude of the first leg of the journey and multiply it by the amplitude of the second leg.
So mechanically, that is very similar to calculating the odds of a multi-leg flight making it on time. You factor the odds of the first flight arriving and multiply it by the odds of the connecting flight.
Yeah, that's a really good analogy.
But I want to push back on the core framework here. Why introduce probability amplitudes at all?
What do you mean?
Well, if there is a 50% chance of path A and a 50% chance of path B, why deal with complex numbers and phases? Why add these invisible vectors first, only to square them into physical probabilities later? What is the mechanical necessity of doing that extra step?
What's fascinating here is that this extra step is the only mathematical mechanism that allows for interference.
Okay.
Because these amplitudes are complex numbers, they possess a phase angle. They act like rotating vectors. When you add the amplitude of path A to the amplitude of path B before squaring them, those vectors interact.
Ah, I see.
Right? So if they point in the same direction, they compound, creating constructive interference.
Yeah.
But if they point in opposite directions, they completely cancel each other out.
They annihilate the probability entirely.
Exactly. And that is exactly the behavior that classical probability misses. I mean, if you just added the final probabilities 50% plus 50%, you would only ever get a larger number.
Right, it would just keep going up.
Yeah, and you could never explain the dark bands on the detector wall where absolutely zero electrons land. So the equation from the text P equals the absolute value of phi1 plus phi2 squared is really the engine of quantum mechanics. That little plus sign inside the absolute value brackets, combining the complex numbers before the square is taken, allows the mathematical paths to interfere.
Okay, so if the mathematical paths interfere when they are open, what happens when we intervene to isolate one of them? Feynman introduces a modified double-slit experiment to test this.
Right, the sneaky light source.
Yeah. We take our standard setup, a source, a wall with two slits, and a detector screen, but we place a light source behind the wall, right between the two slits. We also position two photon detectors, D1 and D2, near each slit.
Because we are attempting to catch the electron in the act. When an electron passes through slit 1, it will scatter a photon from our light source into detector D1. And if it passes through slit 2, we get a scatter into D2.
And the text reveals this startling result. The moment we run this experiment using a short wavelength light, a light sharp enough to give us high-resolution data on exactly which slit the electron passed through the interference pattern on the back wall, completely vanishes.
It just disappears.
Right. The complex bands of probabilities collapse into a standard classical distribution. By simply determining the path, the interference is destroyed. But Feynman details a really specific nuance here regarding adjusting the wavelength of the light source.
Yeah, this is crucial. A short wavelength light provides precise spatial resolution, but it carries higher momentum. If we switch to a long wavelength light, we lower the momentum disturbance, but we also sacrifice resolution. The light basically becomes fuzzy.
So the scattering still occurs. A photon hits our detectors. But because the wavelength is so long, the flash is too broad to pinpoint whether it originated near slit 1 or slit 2.
Exactly. The detector triggers, but the specific path remains a mystery.
And the moment the detector becomes too fuzzy to differentiate the paths, the interference pattern on the back wall magically returns.
Because this isolates the defining principle of the text. Some call it the golden rule of quantum mechanics. You must never add amplitudes for different and distinct final states.
Okay, walk us through how that rule applies mechanically to the two different light sources.
Sure. So when you use the sharp short wavelength light, the universe reaches one of two entirely distinct final states. State 1 is an electron hits the wall at position X, and a photon is registered at detector D1.
Okay.
State 2 is an electron hits the wall at position X, and a photon is registered at D2. Because those two final macroscopic states are distinguishable from one another, they are orthogonal. The math forbids us from adding their amplitudes together.
So we square the amplitude for state 1 to get its probability, square the amplitude for state 2 to get its probability, and then we just add the resulting probabilities.
Right. And because they were squared separately, the cross terms, the mathematical components that cause the vectors to cancel each other out never actually materialize.
But with the long wavelength light.
With the long wavelength light, the final state of the universe is singular. An electron hit the wall at position X, and a blurry photon scatter was detected somewhere. You cannot distinguish the paths based on that final state.
So the paths remain indistinguishable.
Yes, so you add their amplitudes inside the absolute value brackets. The cross terms survive, the vectors interact, and boom, the interference pattern emerges.
So what does this all mean? Feynman points out a really brilliant kind of chilling quote from the text to highlight the spooky nature of this. He writes, "Nature does not know what you are looking at, and she behaves the way she is going to behave whether you bother to take down the data or not."
It's a great quote. And it removes human consciousness from the equation entirely, which is a really common misconception in pop science.
Oh, totally.
People think the observer effect means a human has to literally look at it, but the collapse of the interference pattern has nothing to do with a human observer looking at a screen.
Right. You could automate the photon detectors, record the exact path data onto a hard drive, and literally incinerate the hard drive before a single human eye ever processes the information. The interference pattern on the wall is still destroyed.
Exactly. The mere fact that the final state of the universe contained the distinguishing information is enough to trigger the orthogonal math.
Wow. So if objective distinguishability is the sole arbiter of whether reality operates via interfering amplitudes or classical probabilities, we need to test how subtle that distinguishability can be.
Right, let's push it further.
What if a particle leaves a microscopic physical record of its path without any external detectors or light sources involved at all, like entirely on its own?
Well, Feynman sets up an experiment for exactly that, firing a beam of low-energy neutrons at a crystal lattice. And a crystal is just a highly ordered, repeating grid of atoms. We are measuring the probability of a neutron scattering off this crystal and hitting a specific counter.
So detail this for us.
Both the incoming neutrons and the atomic nuclei within the crystal possess quantum spin. Let's assume we polarize our neutron beam so every incoming neutron has an upspin. And we prepare our crystal so every atomic nucleus has a downspin.
Okay, so a neutron enters the lattice and scatters off an atom. Because it's a low-energy collision, it doesn't possess the kinetic energy to knock the atom out of its place in the grid. If the neutron scatters, and both the neutron and the nucleus retain their original spin states, the lattice remains completely unchanged.
Right. The neutron deflected, but you cannot examine the crystal afterward and determine which specific atom caused the deflection.
Because it looks exactly the same.
Exactly. The atom that was struck looks identical to the billions of other atoms in the lattice. The paths are indistinguishable. So you must add the amplitudes for the neutron striking atom 1, atom 2, all the way to atom 1 billion. The superposition of all those amplitudes creates massive, sharp interference peaks at the detector.
But, and here's the twist, quantum mechanics allows for a different interaction during that collision. There is a probability that the neutron and the specific nucleus it strikes will exchange spins. The neutron leaves the collision with a downspin, and the atomic nucleus flips to an upspin.
And if we connect this to the bigger picture, think of that flip spin as a tripwire.
A tripwire.
Yeah. Out of billions of atoms in the crystal lattice with a downspin, there's now exactly one atom with an upspin. The environment has been permanently physically altered by the passage of the neutron.
It's a localized record. The universe kept a secret receipt of the exact scattering location.
Exactly. The final state of the universe is fundamentally changed. You have a neutron at the detector and a crystal with, say, atom number 4 million flipped. That is a distinct mathematically orthogonal state from a neutron at the detector and atom number 5 flipped.
Wow.
Because the state is distinguishable in principle, we revert to the rules for distinguishable events.
We add the probabilities, not the amplitudes. And the result, those sharp, beautiful interference peaks on our detector vanish. They are completely replaced by a smooth, smeared-out distribution curve, typical of classical background scatters.
It just washes out.
But let me play the role of the skeptical physicist in the lab here, directly referencing an argument from the text. But wait, I don't care which atom in the crystal has its spin flipped. I'm just looking at the neutrons hitting my detector. I am actively choosing to ignore the spin states of the lattice atoms.
And Feynman's rebuttal is uncompromising on this. Nature knows. It is totally irrelevant whether the experimenter measures the lattice or ignores it.
The universe still kept the receipt.
Right. The mathematical reality is that the final state of the entire system, neutron plus lattice, is distinguishable. The cross terms in the probability expansion vanish regardless of human intent. The architecture of probability depends entirely on the objective distinguishability of the physical states.
Man, that is wild. So if leaving a tiny trace, like a flipped spin, is enough to destroy interference because we can tell the paths apart, what happens when two interacting particles are so fundamentally identical that the universe itself cannot distinguish between them? Like, distinguishing them is physically impossible.
This is where we test the absolute limits of identity. We move to scattering atomic nuclei against other nuclei.
Feynman starts with a baseline here. We fire an alpha particle, a helium nucleus, at an oxygen nucleus. We measure the probability of either particle deflecting at a 90-degree angle into our detector. Because an alpha particle and an oxygen nucleus possess entirely different mass and charge, they are perfectly distinguishable.
Right, there's no confusion there.
You measure the alpha particle deflecting left. You measure the oxygen recoiling right. The measurements perfectly match the classical calculations.
The mathematics function normally because there is no ambiguity about which particle triggered the detector. But if we replace the oxygen target with another alpha particle, we create a collision between two identical bosons.
And here's where it gets really interesting. We fire an alpha particle at an alpha particle. They collide. Our detector, sitting at a 90-degree angle, registers a hit. But which particle just entered the detector? Was it the incoming bullet particle that deflected 90 degrees to the left? Or was it the stationary target particle that was knocked 90 degrees forward and to the left?
It is physically and mathematically impossible to tell. I mean, they share the exact same mass, charge, and quantum numbers.
You literally can't put a tag on them.
No, you can't. The two alternative paths, bullet deflecting or target recoiling, result in the exact same final state. Therefore, according to the rule we've established, you must add the amplitudes of those two paths together before squaring.
Okay, so when we calculate the interference, exactly 90 degrees in the center of mass frame, the amplitude for the bullet to scatter to 90 degrees is identical to the amplitude for the target to recoil to 90 degrees. Let's call that amplitude F. So we add F plus F, giving us 2F.
Right.
And then when we square that to find the actual probability, we get 4 squared.
Which is exactly twice the classical prediction. Classical physics assumes you just add the probabilities F squared plus F squared, resulting in 2F squared. But because they are indistinguishable bosons, their amplitudes compound constructively. The interference literally doubles the odds of finding an alpha particle at that 90-degree angle.
Double the odds. That's incredible. Now for the grand finale, we take this exact same indistinguishable collision framework and we apply it to electrons. We fire an electron at an identical electron and measure the 90-degree scatter. Because they're identical, we expect their amplitudes to interfere and double the probability, just like the alpha particles.
Well, they do interfere, but the mathematical outcome is completely inverted. The amplitude for identical electrons interferes with a minus sign.
A minus sign. Wait, really? Instead of adding the amplitude of path A to path B, you subtract path B from path A.
Exactly. This is the defining characteristic of fermions, which is the class of particles that includes electrons. When the mathematical equations swap the identities of two identical fermions, the entire wave function is multiplied by -1.
Wow.
It introduces an automatic mandatory phase shift of 180 degrees.
So let's trace how that phase shift impacts the physical measurement. If we are looking at that same 90-degree angle, the amplitude for the bullet electron to deflect is F, and the amplitude for the target electron to recoil is F. But because of the minus sign, we have F minus F.
Which equals 0.
The probability drops to absolute 0. It is physically impossible for two identical electrons with the same spin to scatter at a 90-degree angle. The destructive interference is absolute.
But we do have to factor in the specific quantum states of the electrons to understand the full picture, referencing back to that crystal lattice experiment. Electrons possess quantum spin.
Right, so this raises an important question. If we polarize the beams, so the bullet electron has an up spin and the target electron has a down spin, we have reintroduced distinguishability.
Precisely. Because you could theoretically check the detector. If an upspin electron arrives, you know it was the bullet. If a downspin arrives, you know it was the target. They are distinguishable states, so the amplitudes do not interfere. You simply add their separate probabilities and you get the standard classical distribution.
And Feynman maps this out brilliantly in the final data tables of the chapter. If you use completely random, unpolarized beams of electrons where the spins are a chaotic, 50-50 mixture of up and down the mathematics undergo a fascinating averaging effect.
Yeah, half the time the colliding electrons will have opposing spins. They are distinguishable and they scatter following classical probability calculations.
Okay.
But the other half of the time, the electrons will happen to share the same spin. They become perfectly indistinguishable. That minus sign dictates their interaction, and their amplitudes destructively interfere to zero.
So when you average those events together, the total observed probability of finding unpolarized electrons scattered at 90 degrees is exactly half of the classical prediction. The intrinsic identity of the particle and that underlying minus sign in the algebra totally rewrites the math of reality we measure in the lab.
It really demonstrates that quantum mechanics isn't just a slight modification of classical physics at smaller scales. It is an entirely different operational framework where indistinguishability dictates reality.
It's mind-bending. So just to recap for you listening, we have traced this from the simplest mathematical rule of combining complex amplitudes all the way to the deepest architecture of matter. We saw how adding complex amplitudes instead of probabilities allows paths to interfere. We saw how extracting distinguishability from a system, whether through a light flashing behind a slit or a single flip spin inside a crystal, forces reality to abandon that interference.
Nature knows if a path can be traced.
Exactly.
Yeah.
And finally, we saw how the sheer impossibility of telling identical particles apart forces them to interfere, governed by whether they are bosons compounding constructively or fermions destructing with a minus sign.
You know, the mechanics of that minus sign warrant a final, deeper consideration for you to mull over.
Oh, absolutely.
We established from the text that identical electrons, fermions, with the exact same quantum state, including spin, mathematically subtract each other's probability amplitudes. That results in a probability of 0 when forced into the same indistinguishable state.
Right, F minus F is 0.
Exactly. Now, this isn't just a quirk of a scattering experiment. This absolute mathematically mandated negative interference is the Pauli exclusion principle. It is a mathematical refusal of identical fermions to occupy the exact same indistinguishable state.
Which has huge implications.
Massive. Consider the implications of that subtraction. Could this bizarre negative interference, the simple minus sign in the foundational algebra, be the structural mechanism that prevents all the electrons in an atom from just collapsing into the lowest energy level? Could this simple minus sign be the fundamental reason why matter actually takes up physical space? The literal reason why you, the listener, and the chair you're sitting in don't just instantly collapse into a single, infinitely dense microscopic point.
From basic algebraic brackets to the literal reason solid objects exist. It is a striking reminder that the strangest, most complex parts of the universe often require the simplest, most rigid math. Thank you for joining us on this custom deep dive. We'll see you next time. And remember, whether you're throwing a baseball or tracking an electron, the universe is always keeping the receipt. Look at your hand, like really look at it. Now look at the device you're listening to right now, and then just glance up at the light in the room.
Yeah, you take all that for granted, right?
Exactly. But what if I told you that the fundamental difference between, the solid matter you can touch, like your hand, and the light you're seeing comes down to a microscopic math glitch?
I mean, calling it a glitch is almost understating it. It's the core rule of everything.
Right. So we've been doing a deep dive into Chapter 4 of the legendary Feynman Lectures on Physics. This is the chapter on identical particles. And Richard Feynman points out something just wild.
He really does.
He shows how the universe's simple inability to tell two identical particles apart is basically the secret code that creates the entire physical world. Like everything from the chemistry of your body to frictionless liquids to the light from the sun. It all hinges on this single rule about whether particles are hardwired to be extreme clumpers or extreme loners.
It completely upends how you view reality, honestly. We spend our entire lives interacting with the macroscopic results of this rule, usually completely unaware of the microscopic toggle switch that makes it all possible.
Yeah, toggle switch we can't even see.
Right. But to really grasp how bizarre this is, we kind of have to set a baseline of how things work in the normal, everyday world.
Okay, lay it on me.
Think about two cars crashing at an intersection and bouncing off each other. In the macro world, we can always track them. We know which car is the red sedan and which is the blue truck.
Sure, I mean, because they look different. But, okay, even if there were two... absolutely identical red sedans fresh off the factory line, we could theoretically, I don't know, paint a little X on the bumper of one of them. Right. Or just keep a camera fixed on it. It's just a matter of observation.
Precisely. In the macro world, you can always track the history of an object. But in quantum mechanics, that tracking system breaks down on a fundamental level.
How so?
Well, if you have two perfectly identical electrons and they scatter off each other into two different detectors, say one on the left and one on the right, it is physically impossible, even in principle, to know which electron went to which detector.
Because they're truly identical. Like, not just they look similar,
Right.
but they are fundamentally the exact same thing. You can't paint a tiny X on an electron.
You can't. You really can't. And this is where the physics gets incredibly strange, because we cannot tell which electron went where, the two possible realities. So electron A going left or electron B going left, they physically overlap.
Oh, wow.
Yeah, quantum mechanics says we have to calculate the total probability of the event by combining the probabilities or the amplitudes of both those possibilities.
Okay, so it's like two separate timelines of reality bleeding into one another, and we have to factor both of them in.
That is a really great way to visualize it. But here is the crossroads. When you take the mathematical equation for the first scenario and you swap the particles to get the second scenario, the math dictates you have to multiply by a certain mystery number, a phase factor.
Mystery number, okay.
Right. Now, just think about the pure logic here. If you swap the particles once, you multiply by this factor. But if you swap them a second time, putting them right back where they started, you have to multiply by that factor again.
Well, a double swap changes nothing. I mean, you're just back to your original starting point.
Exactly. So that means whatever this mystery factor is, if you multiply it by itself, like if you square it, it must equal exactly 1, so nothing changes.
Right.
So algebraically, what number squared equal 1?
Oh, only two numbers do that, +1 and -1.
Yes. The math only allows for those two possibilities. When you swap identical particles, either the overlapping reality contributes with the exact same sign, so a +1, or it contributes with the opposite sign, a -1.
So instead of like a random coin toss, it's more like a permanent toggle switch hardwired into the universe's code for every single particle.
Exactly.
Some are hardwired to add, and some are hardwired to subtract.
And that toggle switch divides the entire universe into two distinct tribes. The +1 particles, where their overlapping realities add together, are called Bose particles, or bosons.
Okay, bosons.
Yeah, these are things like photons, so particles of light, as well as mesons and gravitons.
And the -1 particles, where the realities subtract, those are called Fermi particles, or fermions.
All right, you got it.
And this tribe includes electrons, muons, neutrinos, protons, and neutrons.
That's the dividing line. But things get a little complicated when these fundamental particles start building larger objects.
Wait, hold on. Let me test that. Because protons and neutrons are fermions, right? The -1 particles.
Yes, they are.
But they clump together to form the nucleus of an atom. So does the nucleus itself act like a fermion, or do composite particles follow some different set of rules?
Well, tightly bound composite objects actually act as a single particle. And they follow a really elegant, odd, or even rule.
Oh, I like rules. How does it work?
If the composite object contains an odd number of Fermi particles, it acts like a fermion. But if it has an even number, the whole thing acts like a boson.
Wait, let me see if I can walk through the math on that. Take an alpha particle, which is just a helium-4 nucleus. It has 2 protons and 2 neutrons, so that's 4 fermions.
Right, 4 is even.
Okay, so if I swap 2 alpha particles, am I swapping 4 pairs of fermions all at once? Does that mean I multiply 4 minus signs together?
Follow the signs, yeah?
Let's see. Minus times minus is positive, times minus is negative, times minus is positive again, so a double negative makes a positive. The whole alpha particle, with its 4 fermions, acts like a +1 boson.
You've nailed it. Now contrast that with lithium-7. Its nucleus has 3 protons and 4 neutrons. That's a total of 7 Fermi particles.
And 7 is odd.
Right. 7 negative signs multiplied together leaves you with a negative sign. So lithium-7 acts as a fermion, and what dictates this odd or even nature is intimately tied to the particle's spin.
Spin?
Yeah, the physics rule of thumb is objects with half-integral spin, like 1/2 or 3/2, imitate fermions. Objects with integral spin, like 0 or 1, imitate bosons.
Wait, spin. Like the physical rotation of the particle, why would how fast a particle spins dictate whether it's a +1 adding particle or a -1 subtracting particle?
I mean, that is the million-dollar question. It's so profound that we are actually going to hold off on answering it until the end of our deep dive.
Oh, keeping me in suspense.
For now, just know that spin and this toggle switch are fundamentally locked together. Helium-4 has a spin of 0, so it's a boson. Lithium-7 has a spin of 3/2, so it's a fermion.
Okay, fine. I'll put a pin in the spin mystery.
Oh.
Let's look closer at the bosons then. The +1 integral spin particles. If their realities add together when you swap them, what does that actually mean for the real world when a bunch of them get together?
It means they are the ultimate followers. They absolutely love to be in exactly the same state.
Like a trend.
Basically, there is a bizarre mathematical reality for bosons. If you have a certain number of them, let's call the number n, already sitting in a specific quantum state, the probability of getting one more particle into that exact same state is mathematically enhanced by a factor of n+1.
I have to pause you there because that sounds completely crazy.
It does, yeah.
Like if I have a tiny box and there are already 100 photons in that box bouncing around in the exact same state,
Yeah.
you're saying it's easier for the 101st photon to enter. Does the photon exert a physical gravitational pull or like an electromagnetic tractor beam on the new photon?
No, and I'm really glad you asked that because that is a very common trap people fall into. There is absolutely no physical force pulling that new photon in.
None.
None. No gravity, no magnetism. It is a pure probability enhancement. The very structure of the quantum math means they just have a statistical tendency to crowd together.
That is so weird.
I know. The more bosons are at the party, the more likely another boson is to walk through the door.
So if an atom is getting ready to emit a photon of light, it's more likely to do so if there's already light around it.
Yes. Einstein actually figured out that the rate an atom emits light has two parts. First, there's spontaneous emission, which is just random. But second, there's induced emission.
Induced.
Yeah. Because photons are bosons, the existing light literally increases the probability that the atom will emit more light of the exact same kind.
Oh, wow. So one photon encourages the next, which encourages the next, until you have this massive synchronized beam of light.
Wait, is that the mechanism behind a laser?
That is the exact mechanism. Light amplification by stimulated emission of radiation. The boson clumping rule is the stimulated emission part.
That is amazing.
But Feynman points out an even bigger aha moment regarding this math. Back in the early days of physics before quantum mechanics, scientists treated the electromagnetic field light as a classical standing wave, kind of like a vibrating guitar string.
Right, the classic wave versus particle debate. Right. But when you actually calculate the math of these clumping boson particles bouncing around inside a box using this n+1 rule, you arrive at a specific formula. And it turns out that formula is identical to the one you get if you treat the system as a classical vibrating wave.
Wait, identical?
Completely. Whether you calculate the probability of boson particles clumping or the energy levels of a continuous wave, the math aligns perfectly. The result is Planck's famous black-body radiation law.
That is one of those deep structural miracles of the universe. The math for clumps of particles and the math for oscillating waves are basically two different languages describing the exact same truth.
Beautifully put.
Okay, but light is one thing. If light particles can pile up like that, what happens if you try this with actual matter, like a beaker full of those boson alpha particles we talked about?
Well, then you get the phenomenon of superfluids.
Superfluid.
Yeah. Normally, in a liquid like water or liquid helium, the atoms are bouncing all over the place because of heat. Thermal energy keeps them occupying all sorts of different energetic states.
Right. Heat makes things jiggle so they can't synchronize.
But if you take liquid helium-4, which is a boson, and you cool it down to nearly absolute zero, you remove that thermal agitation, suddenly that statistical n+1 clumping rule takes over completely.
Oh, I see where this is going.
There is a dramatic phase shift where almost all the helium atoms cooperatively drop into the exact same foundational quantum state.
They all crash the same VIP room.
Exactly. And because they are all in the exact same state, the liquid loses all internal friction. It becomes a superfluid.
No friction at all.
None. It
Yeah.
will literally creep up the sides of a glass beaker and empty itself out. It is the ideal dry water. You can't have turbulence where one part of the fluid drags against another because they are mathematically behaving as a single, perfectly rigid entity.
That honestly sounds like science fiction. How do we know it's not just some weird chemical quirk of helium as an element?
Because of helium-3. It's an isotope with 2 protons but only 1 neutron. So 3 fermions in total.
Which is an odd number, so helium-3 acts like a fermion.
Bingo. And when you cool helium-3 down to the exact same incredibly low temperatures, it does not become a superfluid. It remains a normal, viscous liquid.
Wow.
Yeah, the frictionless flow of helium-4 is purely a quantum mechanical effect of its particles being bosons.
Okay, so helium-4 acts like a frictionless liquid because its atoms are bosons and they all crash to the same state. But earlier you said the electrons in my body are fermions.
Yes, they are.
If they all crash the same state, wouldn't my body just collapse into a tiny puddle? How does their -1 toggle switch stop that from happening?
It stops it with absolute mathematical finality. Remember, for identical fermions, the overlapping realities subtract from each other. The amplitude is the first state minus the exchanged state.
Okay, so if two identical electrons try to occupy the exact same location with the exact same spin, the equation is the state minus the exact same state. Algebraically, x minus x.
And x minus x is 0.
The universe subtracts one possibility from the other. 1 minus 1 is 0. The probability literally becomes 0. The universe says, no, this state doesn't exist.
That is the Pauli exclusion principle. It is physically impossible for 2 fermions to occupy the exact same quantum state. If bosons are the ultimate partygoers, fermions are the ultimate introverts.
It's like that VIP room, but with extreme social distancing.
Yeah, exactly.
If electrons were bosons, they'd all pile onto the single best seat in the house, like the lowest energy spot right next to the atomic nucleus. But because they're fermions, the first electron takes the best seat. When the second electron shows up, if it has the same spin, the universe acts as the bouncer and literally says, seats taken. It's forced to sit further away.
And that bouncer shapes all of chemistry. Take lithium, for example. It has 3 electrons. The first 2 can actually sit close to the nucleus together, but only because their spins point in opposite directions, one up, one down.
Oh, so they aren't exactly the same.
Right. By having opposite spins, they are technically in different quantum states, so the bouncer lets them in.
But the inner shell only has room for those 2 states. So what happens to the third electron?
It is banished. It is forced into a state much further out from the nucleus. Because it's pushed so far away from the positive pull of the protons, it's barely holding on. Feynman notes it takes 25 electron volts of energy to rip an electron away from tightly bound helium. But it only takes 5 electron volts to rip that banished third electron away from lithium.
So it's incredibly reactive. It wants to give that electron away.
Exactly. This mathematical minus sign forces electrons to stack outward into larger and larger shells. That creates valence, which dictates how atoms share and trade electrons. It is the literal foundation of the periodic table.
I'm starting to see the scale of this, but I want to bring it back to the macro world for a second. You mentioned my body collapsing. How does this exclusion principle practically hold the world around me together?
It provides stability. Imagine squeezing 2 hydrogen atoms together. Why don't they just keep squeezing endlessly into one giant, dense smear of protons and electrons?
Good question.
Because as they get close, the electrons of one atom refuse to occupy the same spatial and spin states as the electrons of the other atom. Matter takes up physical space specifically because fermions refuse to share space.
But that's why I don't fall through my chair. The electrons in my pants are being repelled by the electrons in the wood because the seats are taken.
Yes, and it also explains how they stick together in the first place. A covalent chemical bond happens when 2 atoms share electrons in the space between them. But the exclusion principle dictates there can only be 2 electrons in that shared space, and only if they have opposite spins.
Okay, so it creates solids and it creates chemical bonds. But the source text goes into ferromagnetism too. How does this introvert rule create a magnet? Magnets are all about things lining up, right? That sounds like clumping.
It does sound like clumping, which makes it wonderfully counterintuitive. In a magnetic crystal, you have free electrons wandering around from atom to atom. The exclusion principle forces these wandering electrons to be anti-parallel, so opposite in spin to the inner electrons of the atoms they pass by.
Wait, slow down. How does a free-floating electron being opposite force 2 completely different atoms to line up with each other?
The free electron acts as a middleman. Let's say it passes atom A. The exclusion principle forces the free electron spin to point down because atom A's inner electrons are pointing up. Then, that same free electron wanders over to atom B.
So if the free electron is still pointing down.
Exactly. It forces atom B's inner electrons to point up. The only way the wandering electron can exist among all these atoms is if it forces atom A and atom B to have their inner electrons pointing in the exact same parallel direction. The exclusion principle indirectly forces all the atomic electrons to align, creating a macroscopic magnet.
So it's like a quantum gear system. The middle gear turns the outer gears in the same direction. A macroscopic force of nature, just a byproduct of electrons refusing to share a quantum state.
It really is. And this fierce independence doesn't just happen with electrons. It happens deep in the nucleus with protons and neutrons too. Consider a deuteron, the nucleus of heavy hydrogen. It's one proton and one neutron. They have parallel spins, bind tightly together, and are very stable.
Okay, but if a proton and a neutron can stick together, why couldn't two protons stick together? Like a helium-2 nucleus.
Because of the minus sign, the strong nuclear force that binds the nucleus together is highly sensitive to spin. It is vastly stronger when the spins of the particles are parallel. Now, a proton and a neutron are identical, so the exclusion principle doesn't apply. They can occupy the same space with parallel spins and bind tightly.
Ah, I see where this is going. But two protons are identical fermions.
Yes. If you try to stick two protons together, they absolutely cannot be in the same space with parallel spins. The universe subtracts the probability to 0. They are allowed to be in the same space if their spins are opposite, but remember, the nuclear force for opposite spins is incredibly weak. It's too weak to actually hold them against their own electrical repulsion, so they just fly apart. Helium-2 is physically impossible.
That is just wild. To summarize this whole journey we've been on through Feynman's text, it all starts with a simple toggle switch when indistinguishable particles overlap. If the universe flips a plus sign, you get bosons. They love to clump. That plus sign gives us light, lasers, and perfectly frictionless superfluids.
Right.
But if the universe flips a minus sign, you get fermions. They absolutely refuse to share. And that minus sign gives us the periodic table, solid matter, chemical bonds, and magnets.
It's an incredibly elegant system, but, we promised to pull the pin on that mystery from earlier.
Oh, right, the spin.
Yeah, we've established the rule. Half integer spin makes something a subtracting fermion, and integer spin makes it an adding boson. But why? Why are these mathematical phase rules so strictly linked to the mechanical rotation of the particle?
Right. We just accepted that they were locked together to make the math work.
Well, Feynman leaves us with a provocative thought here. He notes that the great physicist Wolfgang Pauli did mathematically prove that spin and statistics must be linked. But he had to do it using incredibly complex relativistic quantum field theory.
So really dense math.
Unbelievably dense. To this day, Feynman says, there is no simple, intuitive explanation for why they must go together. As he puts it, we are forced to just accept it as one of the mysterious, deep-down rules of the world. The universe knows exactly what it's doing, even if we don't fully have the simple words to explain why.
I love that. The universe has its underlying code, and we're just slowly translating it. So for you listening, the next time you look at the light in your room or you knock your hand on a solid piece of wood, I want you to ponder that mystery. You're not just touching a table or seeing a lamp. You're experiencing the macroscopic magic of clumpers and loners, born from a mathematical toggle switch at the very dawn of reality.
Imagine moving to a new country and realizing that absolutely none of the grammar rules you grew up with actually apply there.
Oh, that sounds like a nightmare.
Right. Like, verbs just don't function the same way at all. Nouns completely change meaning depending on who is looking at them. And, well, the basic syntax of how a sentence is built just sort of shatters in your hands.
Yeah, you'd basically have to abandon everything you thought you knew about communication just to, order a cup of coffee.
Exactly. And that sense of total, overwhelming disorientation is exactly what it feels like to step into the world of quantum mechanics.
It really is. You just have to leave your baggage at the door.
You do. You have to ditch classical physics entirely. No apologies, no trying to force old comfortable rules onto this very strange new reality. So today, our mission in this deep dive is to learn the true, unadulterated language of the quantum world.
And we are going to accomplish that by focusing intensely on one single, incredibly elegant prototype.
Yeah, the source material we're using today is amazing. It draws from the iconic Feynman lectures on physics. Specifically, we're looking at Volume 3, Chapter 5.
Right. We are digging into the notes, the context, and his brilliant thought experiments outlining the behavior of what physicists call a spin-1 particle.
Which I know sounds highly technical right off the bat.
It does, but it's actually the perfect gateway.
It really is. And I can promise you, the listener, by the end of this deep dive, you will understand the underlying machinery of the universe in a completely new way.
Without needing a PhD in math, which is the best part.
Exactly. We are going to look really closely at the physical actions like what actually happens to these tiny particles in real three-dimensional space, and we'll let those physical behaviors guide us directly into the logic of the universe.
It's the perfect starting point. Because, this specific example is mechanically pretty simple, but it contains literally all the conceptual weirdness of quantum mechanics.
It's like the ultimate prototype.
Yeah, it stands in for all quantum phenomena. The bizarre rules we uncover today by just watching this one atom, they will generalize to absolutely everything else in the quantum realm.
Okay, so let's set the stage with the physical setup. We're talking about the classic Stern-Gerlach experiment.
Right, from figure 5.1 in the text.
Yes. So picture a tiny oven. It's essentially a hot furnace, and it's shooting a single, perfectly straight beam of atoms out of this tiny little hole.
Just firing them out.
Firing them into a vacuum. They're flying horizontally, and we pass them through a specialized apparatus. Now, this apparatus has a magnet in it, but it's not, it's not a fridge magnet.
No, definitely not. It has a very specific geometry.
Right, maybe a sharp, pointed ridge on the top pole and a flat groove on the bottom pole. This creates what physicists call an inhomogeneous magnetic field.
And that specific shape is just absolutely critical to the mechanics of the whole experiment.
Yeah.
If you just used a standard uniform magnetic field.
Like two flat parallel magnets.
Yeah, exactly. If you use those, you wouldn't get a quantum sorting effect at all.
Yeah.
A uniform magnetic field just acts like the Earth's magnetic field acts on a compass needle.
Oh, so it just twists it.
Right. It grabs the atom and applies a torque until it aligns.
Yeah.
The compass needle points north, but it doesn't physically fly toward the North Pole, right?
Okay, let's unpack this. Because if I take a regular classical steel ball bearing, right, and I roll it past a really powerful magnet on a table, the ball physically translates through space. It gets pulled toward the magnet.
Yes, it deflects.
It deflects in a smooth curve based on, how fast it's rolling and how close it gets. So why do we need this weird, sharp-pointed magnet for the atoms?
Well, because atoms are just so impossibly small and moving so fast, we need a field that doesn't just twist them, but actually physically pulls them off their straight path.
Ah, I see.
So an inhomogeneous field, where the magnetic force is drastically stronger near that sharp pointed tip than it is near the flat groove. It pulls harder on one side of the atom's magnetic pole than the other.
So it's an uneven pull.
Exactly. That uneven pull creates a net force. It physically drags the atom up or pushes it down as it flies through the machine.
But wait, in classical physics, wouldn't you expect those atoms, which are just tumbling out of a hot furnace with completely random orientations, to just sort of smear out vertically?
That is exactly what classical mechanics predicts, yeah.
You'd expect a continuous blur of atoms just hitting the detector wall on the other side, like a giant messy smudge of gray.
Right, but the actual result is wild. The beam of atoms doesn't smear into a continuous blur at all. It splits cleanly into exactly 3 distinct, widely separated vertical beams.
3 distinct beams.
Just 3. We have a top beam, which we will call the pluses state, a perfectly straight middle beam, the zero state, and a bottom beam, which is the minuses state.
It is honestly like the apparatus is a physical filter or, I don't know, a magical quantum sorting hat.
A quantum sorting hat is a great way to put it.
It just forces every single atom to abandon its random tumbling and snap into one of 3 distinct categories.
And you are hitting the absolute essence of quantum quantization right there. The atoms we are observing have an inherent property that physicists call spin 1.
Okay.
You can think of them as tiny atomic magnets that possess internal angular momentum.
Like a spinning top?
Kind of, but unlike your classical steel ball bearing or a spinning top, their spin cannot just point in any random continuous direction when forced to interact with the world.
The universe just won't allow it.
Exactly. The universe dictates that when their spin is measured along a specific vertical axis by this gradient, it can only exist in very specific, discrete, whole number amounts.
Hence the quantization.
Right. For a spin 1 particle, it can only ever be measured as +1, 0, or -1. There is no plus 0.5.
No, -0.8.
No, nothing in between. The gradient magnetic field basically forces the tumbling atom to reveal its state, sorting it strictly into one of those 3 allowed paths.
So it physically separates them based on a property that fundamentally refuses to exist in fractions. It's amazing.
It is.
And the source text takes this a step further with a brilliant thought experiment. And because it's a thought experiment, we don't have to worry about the engineering budget, right?
Thank goodness. We can make it as complicated as we want.
Right. So we can complicate the equipment to get a totally pure result. We imagine a sequence of 3 high gradient magnets in a row.
Okay.
The first magnet splits the beam into those three diverging paths we just talked about. But then a second, longer magnet with the opposite polarity catches those diverging beams and reverses their bend, pushing them back inward.
Like bringing them back together.
Exactly. And finally, a third magnet catches them just as they meet and flattens their trajectories, bringing all three beams perfectly back together along the original central axis.
And Feynman's thought experiment even assumes we have a magical mechanism to start the atoms from rest and bring them perfectly back to rest at the very end of the machine.
Which is practically impossible, but we're in a thought experiment.
Good.
Why? Why go through all this elaborate theoretical engineering?
The whole reason is to mathematically isolate the spin from the messy physics of motion.
Oh, because they're usually moving so fast.
Right. When atoms are flying around, they have velocity, trajectory, momentum, all this extra baggage. By controlling the exact path so perfectly and bringing the atoms to a dead stop at the end, we strip away all the chaotic variables of their flight.
We don't have to worry about how fast they're going.
Exactly. We are left with a mathematically pure way to study just the quantum state itself, nothing else.
And because they are split so widely in the middle of this machine before coming back together, it gives us a physical place to intervene. Right?
Yes, a place to actually mess with them.
We can slide physical blocks, literally pieces of metal, into the middle of the apparatus to act as masks. So if we drop a block over the bottom two paths, the zero and the minus paths, they just absorb those atoms.
Right, they block them completely.
So only the atoms taking the top pluses path actually make it through to the end, meaning we have successfully manufactured a beam of absolute certainty. Every single atom surviving that machine is definitively, unequivocally, a pluses state atom.
Well, with respect to that specific upright orientation of the apparatus, yes.
Yeah.
We have created a pure polarized state.
Which naturally invites us to mess with it.
Of course it does.
Let's take this beam of perfect certainty and just throw a massive curveball at it. We take our pure pluses state emerging from our first apparatus, let's label that machine S.
Okay, machine S.
And we feed that pure beam directly into a second identical apparatus, which we'll call T. But here's the trick. We physically tilt apparatus T on its side at some random angle relative to S.
Okay, so it's skewed.
Yeah. Now, my classical everyday logic tells me that an atom's inherent properties are just that inherent. If a ball is painted red, it stays red no matter how I tilt my head.
Right, that's just common sense.
So if I have a perfectly pure plus atom, it should either confidently march through the pluses channel of the new tilted machine, or, I don't know, because the physical channels are now misaligned, maybe it just crashes into the metal wall of the new filter.
But what's fascinating here is that the quantum world completely defies that kind of objective, persistent reality. A pluses state with respect to the upright machine S is absolutely not a plus state with respect to the tilted machine T.
So it doesn't just stay a plus.
No. The atom doesn't crash into the wall, and it certainly doesn't just pass cleanly through the pluses channel. Instead, the moment it enters the tilted gradient, it is forced to completely reorient itself with respect to the new environment.
And it does this entirely by luck, which is crazy. If we send 1,000,000 of those pure pluses atoms into the tilted T machine one by one, they just scatter.
Completely scatter.
Some of them will randomly end up taking the plus path in T, some will randomly take the zero path, and some will take the minuses path. They are forced to pick one of the three new states defined by the tilted machine, and we cannot predict which one any individual atom will choose.
No, we can't.
Our perfect certainty is completely shattered just by tilting our perspective.
The only thing we can predict are the overall odds. The probability of which path the atom will choose is calculated using complex numbers, which in quantum mechanics we call amplitudes.
Amplitudes, okay.
Yeah. And the foundational rule here is that the absolute square of the amplitude for the atom to transition from its original state into the new state, that gives you the physical probability.
So it tells you the exact odds.
Exactly. And the universe is very strict about the accounting here. The sum of the probabilities for the three possible paths in the new machine is always exactly 100%.
So it has to go somewhere.
The atom must be found in one of those three states. It cannot refuse to play. It cannot get lost in the margin.
It has to pick a door 1, 2, or 3.
Always.
But, this brings up a massive conceptual hurdle. Let's trace an atom's journey here. I send an atom through the first machine, S, and I block the bottom two paths, so it survives as a pure plus S atom.
Okay, pure plus.
Then it flies into the tilted machine, T. This time I block the top and bottom paths, leaving only the middle open. By sheer probabilistic luck, our atom happens to take the middle path and survives.
Okay, so it emerges as a pure 0T atom.
Right. Now, I send it into a third machine, and this third machine is oriented perfectly upright again, exactly like the first machine. Let's call it S prime.
Back to the original orientation.
Exactly. Does the atom remember that it started its life as a plus S atom? Like, will it automatically gravitate back to the plus channel because of its history?
It absolutely will not. It has total irreversible quantum amnesia.
Wow. Quantum amnesia.
Yeah, once that atom has been cleanly filtered by the tilted T apparatus, its future behavior depends entirely and uniquely on its current status. The fact that it used to be a plus S atom, that has been completely erased from the universe.
See, that is such a huge departure from the macroscopic world. Like, if I take a steel ball bearing and scratch it, then roll it down a ramp, then bounce it off a wall, it still has the scratch.
Right, it carries the history of its interactions on its surface.
But filtering an atom into a pure state is it's like picking up a pair of dice that you previously rolled a 12 on, shaking them up and re-rolling them. The dice don't carry the memory of the 12 into the new roll.
That's a perfect analogy.
The past is entirely wiped clean.
And that wiping of the slate is what physicists call reducing the system to a base state.
A base state.
Yeah, any atomic system can be separated by a filtering process into a defined set of base states. And once it's locked into a single pure base state, its entire history is severed. It is a completely fresh system. The act of measuring the atom, of forcing it to declare itself through a filter, destroys all the information about how it got there.
But does it really? Because the source text sets up an experiment that completely broke my brain, and it hinges on exactly this idea of destroyed memory. Let's look at what happens if we don't block the paths.
Oh, the famous three-stage experiment.
Yes. Here's where it gets really interesting. Let me just logic this out for a second. We have our first apparatus, S, filtering for the pluses path. We get our pure beam of atoms.
Yep.
Then we put them through the tilted apparatus, T, but we put masks in to only let the zero channel through. As we established, they scatter, so only a fraction of our atoms actually make it through that middle channel.
Because in the probabilities.
Right. Then we put that surviving fraction through a final upright apparatus, S prime, also set to only let the pluses channel through. Again, they have amnesia, they scatter again, and only a tiny fraction of the remaining atoms survive. We start with a lot, and we get a very, very small depleted number at the very end.
We've forced them to gamble their existence at every single step, and most of them lost.
Right. But what happens if we run that exact same physical sequence, but we take all the blocking masks out of the middle apparatus, T?
So the T machine is completely wide open.
Totally wide open. It splits the beam into 3 wide paths, reverses them, and recombines them at the end. My logic says that if I take a pure plus beam, shoot it into a tilted machine, and let all the doors stay open, the atoms are going to disperse.
I should, yeah.
They are going to be forced to choose new tilted states, mixing up into plus 0 and minus T states. It should be a chaotic, scrambled mess when it hits the final upright filter.
Classical logic dictates it should definitely be a mess. But the quantum result is astonishing. If you leave that middle apparatus completely open, meaning you don't block any paths, and you don't interact with the atoms while they are inside, 100% of the atoms that enter the middle apparatus will successfully pass through the final plus S prime filter.
100%.
Every single one of them.
How is that physically possible? By opening more paths, by letting the atoms disperse into completely different tilted states, we actually get all of the atoms back exactly where they started.
It's incredible, isn't it?
If we block paths in T, we lose almost everything. If we leave all the paths open in T, they somehow perfectly remember that they started as plus S atoms, and every single one confidently glides through the final pluses filter.
I thought we'd just established they have quantum amnesia.
Well, if we connect this to the bigger picture, you are staring directly at the deepest, most beautiful mystery of quantum mechanics. Interfering amplitudes.
Interfering amplitudes.
Yes. The information about the past state wasn't lost simply because the beam was physically split by the tilted magnetic field inside the T apparatus. The information was lost in our previous experiment because we slid physical pieces of metal into the machine to block the paths.
Wait, so the act of blocking the path, the act of selectively filtering is what destroys the memory, not the physical splitting of the beam itself. Precisely. The text uses a wonderful metaphor here. Humpty Dumpty has been put back together again.
I love that.
It fits perfectly. When the T filter is wide open, the beam is split and recombined without any uneven disturbances. And the mathematics underlying this is where the real magic happens. We talked earlier about amplitudes, right? Those complex numbers that dictate probability.
Right.
Think of those complex numbers like ripples in a pond. When ripples meet, the peaks can line up to create a massive wave that's constructive interference.
Okay, so they build on each other.
Exactly. Or a peak can meet a trough, and they flatten the water entirely. That's destructive interference.
So the atoms are acting like waves of probability.
They are.
Right.
When no paths are blocked in the middle machine, the quantum amplitudes for the atom to take all three of those open paths and end up in the final pluses state literally sum up and constructively interfere to exactly 1.
Meaning 100% probability.
Yes. And the amplitudes to end up in any of the other final states destructively interfere, completely canceling each other out to exactly 0.
That is wild.
Because no paths were blocked and no path was unequally disturbed by a piece of metal, all those complex amplitudes perfectly reweave themselves together to perfectly recreate the original pluses state. It is as if the middle T apparatus wasn't even there.
That Humpty Dumpty interference is just stunning to visualize. But practically speaking, if I'm a working physicist in a lab, how do I actually keep track of all these crossing, splitting, canceling ripples of probability without losing my mind?
It sounds impossible to calculate by hand.
Right. If I'm putting atoms through 5 or 6 different tilted magnets, there has to be a robust system to track them out. I mean, nobody's drawing a million little overlapping waves on a chalkboard.
No. Thankfully, there is a very robust mathematical machinery beneath all of this. And it all boils down to matrices.
Matrices, like grids of numbers.
Exactly. Every single state of an atom, any state whatsoever, no matter how weirdly it's tumbling, can be completely and perfectly described by just 3 complex numbers.
Just 3.
Just 3. Those 3 numbers represent the amplitude for the atom to be found in each of our 3 chosen base states.
So 3 numbers completely define the atom's reality.
Yes. And every piece of apparatus, every complex magnetic filter you put the atom through can be completely described by a grid of 9 numbers.
A 3x3 matrix.
Exactly. These 9 numbers represent the transition amplitudes, basically the odds for an atom to transition from any of the 3 incoming base states to any of the 3 outgoing base states.
You know, I love this because it brings to mind a giant vintage telephone switchboard, or maybe like an audio mixing desk.
Oh, that's a good way to picture it.
Like if my atom is an audio signal coming in on 3 wires, the apparatus is a mixing board with 9 volume dials.
Right, 3 times 3.
Yeah. The pluses input wire splits and routes through 3 different dials. The 0 input routes through 3 dials, and the minuses input routes through 3 dials. Those 9 dials are the complex amplitudes. They mix, boost, and cancel the signals and output the result onto 3 new wires.
That is surprisingly accurate.
And so, if I want to know what happens when an atom goes through a chaotic sequence of 10 different tilted magnetic filters in a row, I don't have to break my brain visualizing invisible probability waves. I just take the 9 dials of the first mixing desk and physically wire them into the 9 dials of the second mixing desk.
In math terms, you just multiply the matrices together.
Multiply the matrices.
That is a perfect mechanical analogy. Matrix multiplication abstracts all that mind-bending Humpty Dumpty interference into straightforward arithmetic.
Which is a huge relief.
It is. But there is a crucial quirk to matrix algebra that flawlessly maps to our physical reality. When you multiply regular numbers, the order doesn't matter, right? 3 times 4 is 12, 4 times 3 is 12.
Right, simple math.
But with matrices, the order absolutely dictates the outcome. Matrix A times matrix B does not equal matrix B times matrix A.
Which perfectly maps to the physical universe.
Exactly.
If I send an atom through an upright filter and then a tilted filter, the resulting state is entirely different than if I send it through a tilted filter first and an upright filter second. The physical sequence changes the reality, and the mathematical sequence of the matrices changes the final numbers.
The math flawlessly reflects the physical truth. It's beautiful. And actually, this deep connection between geometry and probability is also why a spin-1 particle is referred to as a vector particle in physics.
A vector, like an arrow.
Exactly like an arrow. Think about drawing a 3D arrow floating in the space of your living room. You can describe exactly where that arrow is pointing by measuring its length along your room's x-axis, y-axis, and z-axis.
Right, 3 numbers.
3 numbers. Now, if you tilt your head, meaning you change your perspective and your coordinate system, the physical arrow floating in the room hasn't moved a millimeter. But the 3 numbers you use to describe it to a friend have to change to reflect your newly tilted perspective.
Because my personal axes have rotated.
Precisely. In quantum mechanics, the three complex amplitudes that describe the state of the atom transform mathematically, in the exact same way that the spatial coordinates of a 3D arrow transform when you tilt your head.
Oh, wow.
Yeah. When you physically tilt the Stern-Gerlach apparatus in the lab, you are applying the exact same mathematical transformation to the quantum probabilities. The correspondence between physical space and quantum probability is absolute.
That is just, wow. So what does this all mean for us? Let's take a step back and just look at the conceptual journey we've been on today.
It's been a ride.
It really has. We started by seeing how forcing an atom through an uneven magnetic filter doesn't just passively sort it into pre-existing buckets. It fundamentally forces the atom to abandon its continuous tumbling and snap into a completely new, discrete reality based purely on probability.
The sorting hat.
Right. But then we saw that if we leave those paths unblocked, if we refuse to peek or filter them further, the atom miraculously retains its history through the beautiful rippling interference of quantum amplitudes.
Humpty Dumpty put back together.
Yes. And finally, we learned that this entire spooky, magical-seeming process can be mapped, predicted, and mastered using a simple switchboard of just 3 numbers for a state and 9 numbers for a machine.
It's a complete paradigm shift in how we understand the fabric of reality at the fundamental level.
And I really want to remind you, the listener, of the profound implication hiding inside this physics lesson. When we talk about measuring or filtering a system in quantum mechanics, we are not just taking a passive photograph of a world that is already there.
No, not at all.
The act of gathering information, the physical act of sliding a metal mask into an apparatus to see which path an atom took it, destroys the interfering ripples. It fundamentally resets the system's future. The act of observing changes the reality of the thing being observed.
And, this raises an important question, which brings us to the final lingering concept from our source text, the unpolarized beam.
Ah, right.
We've spent this entire deep dive talking about perfectly pure, polarized, carefully filtered states.
The S&T machines.
Exactly. But when atoms come boiling straight out of that hot, chaotic furnace at the very beginning of the experiment, before they hit any magnets, we don't know their state at all.
Yeah.
Their orientations are a completely random, tumbling mess.
The text is very clear on this.
Yeah.
We can't assume any beautiful quantum interference is happening initially because the states are completely mixed up. We just have to fall back on blind statistics.
Right.
We assign a classical 1/3 probability to each of the 3 paths and just hope for the best.
We have to treat the universe as a probabilistic blur right up until the moment it interacts with a filter.
A blur of probability.
Which leaves us with a profound, almost unsettling thought to ponder. In the grand scheme of the universe, out there in the vast cosmos, are there any truly pure quantum states naturally occurring on their own?
Or is absolutely everything we experience, every atom burning in the stars, every molecule in the chair you're sitting on, and every cell in your own body just an unpolarized, chaotic blur of statistical probabilities, right up until an observer or an interaction or a filter like you forces the universe to finally make a choice?
Usually, when you want to figure out how a complex machine works, like an antique grandfather clock or something, you just crack it open.
Right, you look for the gears.
Yeah, the literal nuts and bolts.
It's the most intuitive way we humans solve problems. I mean, we want to see the physical parts interacting to understand the whole.
Exactly.
Yeah.
But what if you were handed a clock that was completely sealed? Like, totally indestructible. You can't look inside.
Oh, that would be incredibly frustrating.
Right. All you can do is turn it upside down, spin it around, and just watch how the hands move. For most people, you'd assume you could never truly understand how it works without seeing those gears.
You'd feel like you're missing the core mechanism.
But in the really strange landscape of quantum physics, it turns out that tearing the clock apart might actually be, well, the wrong approach entirely. Sometimes, just spinning it around in space tells you literally everything you need to know. And we are building this deep dive custom for you today, exploring an excerpt from the legendary Feynman lectures on physics, specifically Volume 3, Chapter 6, which covers spin 1/2.
And it is a profound departure from how we usually think about science. Richard Feynman actually calls this specific exploration a cultural excursion.
Some excursion, yeah.
We are actively setting aside the desire to build tiny mechanical models of fundamental particles. Because historically, whenever physicists try to imagine, say, an electron as a tiny spinning sphere of charge, the model just completely fails.
It breaks down.
Right. To generate its known magnetic field, a physical sphere that small would have to spin at the equator faster than the speed of light.
Which immediately breaks the laws of physics.
Precisely. The mechanical models fall apart. But abstract logic about the geometry of space, that always seems to agree with the experiments. So today, we are using pure reasoning to decode the universe.
I love that. So to do that, before we can talk about how particles behave when we, rotate space, we need a way to actually measure them in the first place.
We need our sealed clock.
Yes, exactly. And Feynman grounds this in something called the Stern-Gerlach apparatus. It's essentially this machine with magnetic poles. You shoot a beam of spin 1/2 particles, like electrons or silver atoms, right into it.
And the key here is that the magnetic field inside the apparatus is intentionally uneven or inhomogeneous.
Inhomogeneous, yeah.
If it were a uniform, perfectly flat magnetic field, the particle would just experience a twist, like a torque.
Okay.
But because the field is stronger at the top than at the bottom, it physically pulls on the magnetic moment of the particle. It splits that single beam into exactly 2 distinct paths.
2 paths.
Right. There is an upper path, which we call the plus state, and a lower path, which we call the minus state.
And crucially, for anyone trying to visualize this, there's no zero state. The beam doesn't just spread out into a blurry, continuous line on the back wall. It splits cleanly in 2.
It's totally binary.
Okay, let's unpack this. Think of this apparatus not like a gentle fork in the road, but like an incredibly strict, unyielding highway toll plaza.
Oh, that's a good way to picture it.
You have this chaotic flow of traffic coming in. But the plaza has exactly 2 exits, an upper bridge and a lower tunnel. Every single car, meaning every particle, is forced to make a binary choice.
There's no middle ground.
None. You cannot park in the middle. You cannot take a ramp that goes somewhat up and somewhat down. You're either definitively up or definitively down relative to that specific machine.
And that strict binary outcome is the foundation of everything that follows here. We aren't going to look at the internal mechanics of the particle that, make it choose the bridge or the tunnel.
Right, no gears.
Exactly. Instead, we are going to deduce the rules of how these particles behave, what physicists call transformation coefficients, purely by abstract reasoning. And to do that, we only need to accept one major philosophical premise.
Which is?
Space itself has no preferred direction.
Meaning the universe doesn't have an absolute up or down?
It's exactly.
So the physics should be exactly the same, whether my toll plaza is built in New York or, I don't know, floating entirely sideways out in deep space.
The rules depend solely on the relative angle between your measuring devices, not their absolute orientation in the void.
Okay, so we have our one sorting machine. But to really test this geometry, we need to chain them together.
Well, we have to add a second machine.
Right. Imagine we have 2 of these Stern-Gerlach machines, one right after the other. We'll call the first apparatus S and the second apparatus T.
Okay, S and T.
We set up machine S, and we completely block the lower tunnel. Like we put a physical wall there. So now the only particles making it out of S and heading toward machine T are from the pure up beam.
We have filtered the chaos. We now have a guaranteed pure plus state.
Exactly. But then we take machine T, the second one, and we tilt it. We cock it at some angle relative to S.
Okay.
The framework suggests that the chance for a particle to go up or down in that second tilted machine depends solely on the relative 3-dimensional rotation between the 2 machines.
Yes.
But wait, I have to stop you there. Because if the particle is already locked into the up state by machine S, how can it have any chance of being up in machine T if T is tilted?
Because the perspective changed.
But hasn't the particle already committed? It took the upper bridge.
This raises an important question, and it really highlights the exact moment classical intuition fails us.
Because it feels like it should be locked in.
Right. If you throw a baseball through a vertical window, it doesn't suddenly care if the next window is tilted. But in quantum mechanics, we deal with amplitudes.
Amplitudes.
An amplitude is not a certainty. It's a mathematical arrow that tells us the probability of finding a particle in a certain state. When you tilt machine T, you are asking the particle a completely different question.
Oh.
You are no longer asking, are you up relative to S? You are asking, are you up relative to T? Because T is tilted, the particle acts as a wave of probability filtering through a new orientation.
I think a better way to visualize this isn't cars at a toll plaza, but like light passing through polarized sunglasses.
Oh, definitely.
If you wear 2 pairs of polarized lenses and they are perfectly aligned, light passes through both.
Right.
But if you slowly rotate the second pair of glasses, the lenses block more and more light. The light that made it through the first lens isn't permanently safe. It has to run the gauntlet of the second lens's new angle.
That is a brilliant way to picture it. The rotation physically alters the probability filter. And to calculate those final probabilities, the actual amount of light hitting your eye or the number of particles hitting the wall, you take the mathematical amplitude and you find its absolute square.
But there is a quirky mathematical rule introduced here about phase factors. And this is vital for you to understand because it's the engine driving Feynman's whole proof.
It is. Think of an amplitude not just as a number, but as an arrow pointing on a two-dimensional grid. The length of that arrow gives you the actual physical probability, that absolute square we just mentioned.
Right, so a long arrow means high probability.
And a short arrow means low probability. But there is a second property, the direction the arrow is pointing.
And that direction is controlled by the phase factor, which is written mathematically as e to the I delta.
Right.
It acts like a hidden dial.
Precisely. If you multiply a set of amplitudes by the exact same phase factor, that dial simply spins all the mathematical arrows around their bases by the same angle.
It just turns them.
Yeah, it changes the direction they point in this abstract mathematical space, but it does not stretch or shrink the length of the arrows at all.
So if you measure the length, the absolute square, it is completely unchanged. The physical reality we observe remains identical, even though the underlying math has been rotated.
Physics allows for this hidden mathematical freedom. The underlying numbers can shift and rotate together, and as long as they all do it by the same common phase, the actual reality we measure in the lab doesn't change one bit.
That hidden freedom is the exact tool Feynman uses to unlock the wildest revelation in this entire journey.
It really is wild.
Because we know that rotating that second machine, T, changes the probability filters, we have to map out the mathematical rules of that rotation. And we start with the simplest possible movement, turning the machine around the z-axis.
Right. So to visualize the z-axis, imagine the straight line the beam of particles is traveling along.
Like the actual path of the beam.
Exactly. Rotating around the z-axis is like spinning a drill bit along the wood. You are twisting the machine along the beam path without tilting it up, down, left, or right.
Right. So S and T are perfectly aligned, but T is just twisted along the beam path. We want to find the mathematical rule for this twist. Now, naturally, you would think that if you rotated machine T a full 360 degrees, you'd bring it right back to where it started.
That's what you'd expect.
Mathematically, the phase multiplier, let's call it M, should just be 1. You turn it 360 degrees, the phase shifts by a full circle, and everything is identical.
That is what any classical geometry would demand. I mean, if you spin a coffee mug 360 degrees, it is exactly the same coffee mug in the exact same orientation.
But wait, you're jumping a step. Why does Feynman argue that M cannot be 1? Just because a full circle feels intuitive doesn't mean we can't, interrogate it.
Let's follow the logical trap Feynman sets up. If we assume our multiplier M is 1, then spinning the machine 360 degrees gives a mathematical phase shift of a full circle. It brings our mathematical arrow right back to where it started.
Which makes total sense.
But look what happens when you stop halfway, a 180-degree physical turn.
Okay.
If M is 1, a 180-degree physical turn generates a phase shift of exactly half a circle. Mathematically, that multiplies your amplitudes by -1.
And as we established with our hidden dial, multiplying everything by a common phase, like -1, doesn't change the absolute square. It doesn't stretch or shrink the arrow.
Which means if M equals 1, a 180-degree physical turn shouldn't change the physical probabilities of our machine at all.
But that is a massive physical contradiction.
Exactly.
If I have a machine measuring left versus right, and I physically spin it 180 degrees, the left side is now on the right side. A particle that was purely in the plus x state is now completely in the minus x state.
The physical reality absolutely changed.
So if we say M equals 1, the math tells us nothing happened, while the physical machine is literally sitting there backwards.
Therefore, our assumption that M equals 1 is fatally flawed. The math demands a different multiplier to avoid this paradox. It demands that M must be 1/2.
Because if M is 1/2, a 180-degree physical turn only creates a 90-degree mathematical phase shift.
Right.
And a 90-degree shift does change the underlying probabilities, matching the physical reality of the backwards machine.
But look at the staggering implication of M being 1/2. It means the mathematical phase shift is always only half of the angle you rotate the physical machine.
Here's where it gets really interesting. If the phase shift is only half the angle, what actually happens when you rotate the physical machine a full 360 degrees?
Your phase shift only travels 180 degrees.
Yeah.
Your mathematical arrows are multiplied by -1.
You rotated the physical heavy metal machine in a complete perfect circle, and the quantum state did not go back to normal.
Whoa.
You literally get negative amplitudes.
Okay.
To mathematically get the arrows back to exactly where they started, to make the phase shift travel a full 360 degrees, you have to rotate the physical machine 720 degrees, 2 full circles.
It completely shatters our standard perception of reality. But it doesn't break the rules of physics because, again, both the plus and the minus amplitudes become negative. It's that common phase change.
Oh, right.
Because they both change sign, the physical probabilities you measure in the lab remain identical. If you spun the machine 360 degrees, you wouldn't notice a difference in how many silver atoms hit the top wall versus the bottom wall.
But the math secretly keeps track of it. It's like the universe has this hidden counter, quietly logging that you only did half the necessary work to truly reset the structural foundation of the particle. You have to spin it twice.
The universe knows you spun it. The geometry retains the memory of the rotation.
It's mind-blowing. Okay, so spinning it like a drill gives us this 720-degree paradox. But space is three-dimensional. That math only works for one axis. How does the particle handle being flipped entirely upside down?
This brings us to rotations about the y-axis. Imagine taking machine T and flipping it end over end, a 180-degree somersault.
In this case, what was the upper bridge relative to machine S is now the lower tunnel relative to machine T because T is completely upside down. So a particle that was perfectly in the plus state for S is now perfectly in the minus state for T.
That's the straightforward boundary. But what happens in the middle? What if we only flip it 90 degrees? What if machine T is standing entirely on its side, measuring left to right instead of up and down?
Well, if you tilt that machine exactly 90 degrees, Feynman points out this beautiful symmetry. It creates a perfect 50-50 mix.
Exactly.
If you fire a pure up particle into a machine tilted 90 degrees, it has exactly a 50% chance of going left and a 50% chance of going right. It is completely up to chance.
And because we're calculating amplitudes, not just raw percentages, we have to work backward from that 50%.
Right.
If the final measured probability must be 1/2, we need the mathematical amplitude that, when multiplied by itself, the absolute square equals 1/2.
Which is 1 over the square root of 2.
It is essentially the Pythagorean theorem applied to the geometry of chance. If you have a right triangle where both legs are length 1, the hypotenuse is the square root of 2.
Right.
The math is just balancing the probabilities to ensure that when the particle is forced to make a choice, everything still sums up to exactly 100%.
Feynman actually has this wonderful quote about how hard this is for our brains to process. He says, perhaps if we were fish or birds, and had a real appreciation of what happens when we turn somersaults in space, we could more easily appreciate such things.
I love that quote.
Our grounded, human, flat Earth intuition constantly fights against these three-dimensional combinations.
It does. But the mathematics does not struggle. By understanding these two simple moves, the twisting drill rotation along the z-axis and the somersault flip along the a-axis, physicists can mathematically map out any rotation in three-dimensional space.
Wow.
To rotate something along the x-axis, you simply combine a y rotation and a z rotation.
Which brings us to the climax of this abstract reasoning. By combining rotations about the z, y, and x axes, we construct a universal master key for any rotation in the universe.
We enter the realm of Euler angles.
Euler angles.
The orientation of absolutely any coordinate frame, no matter how weirdly it is tilted, pitched, or spun, can be described completely by just 3 angles, alpha, beta, and gamma.
And using these 3 angles, Feynman derives a final, elegant set of equations, a transformation matrix. It's a grid of mathematical rules that can predict the particle's behavior from literally any perspective you could ever invent. He gives a perfect example to show how this matrix balances everything effortlessly. If a particle is in a pure verified up state along the z-axis, we already know it has a 50-50 chance of being measured as up or down if we check the x-axis.
Sorry, that was the 90-degree tilt we just mapped out.
But the matrix shows it also has a 50-50 chance of being measured as up or down along the y-axis. There is no prejudice in the void of space. X and Y are equally likely.
Exactly.
But the math reveals one tiny crucial difference. The amplitudes for the y-axis have a 90-degree phase difference compared to the x-axis. There's a little imaginary number, an I, baked right into the equation.
And that I is not just a mathematical parlor trick. What does an imaginary number actually do in a physical equation?
What does it do?
It represents a literal 90-degree rotation in phase space. It is an elegant bookkeeping tool. That I is the only thing distinguishing the x direction from the y direction in the underlying mathematics of the particle.
Because otherwise they'd be identical.
If that imaginary number wasn't there, space would be entirely symmetrical in those directions, and we wouldn't be able to tell them apart mathematically.
So what does this all mean? We started with a sealed clock and a strict toll plaza. We've navigated probability filters, the Pythagorean theorem of chance, and particles that require 2 full 360-degree spins just to reset their internal math. If you had to crystallize the ultimate takeaway for the listener, what is it?
If we connect this to the bigger picture, the sheer triumph here is the unreasonable effectiveness of abstract geometry. Think about what we purposely ignored today.
Skiers.
Exactly. We never once debated what a spin one-half particle is actually made of. We never discussed its internal structural integrity or whether it's a little spinning sphere of charge. Feynman specifically warns us that those mechanical models inevitably, predictably fail.
They just don't work.
Right. Instead, by simply accepting the basic, unbiased symmetry of 3D space and the raw experimental fact that our machine only gives us 2 binary answers, up or down, pure logic generated the exact, flawless mathematical matrix to predict the particle's behavior from any angle in the universe.
It's incredible. We went from a simple magnetic sorting machine to the realization that the universe requires 720 degrees to complete a full quantum spin. And none of it required us to crack open the clock.
Not once.
In an age of total information overload, where we are constantly told we need to dig into the microscopic granular details of every single system to understand it, there's something deeply profound about this methodology. Sometimes stepping back from the internal machinery and just looking at the abstract structural rules of a system yields the most powerful insights possible. You don't always need to see the gears to know how time moves.
That is exactly right. And it leaves us with one final lingering thought to really ponder.
I like where this is going.
Feynman admitted that any physical mechanical model of these particles fails, right? Yet, the pure geometry of space yields perfect predictions. So if the most accurate predictions in the universe come solely from abstract geometry, and any attempt to imagine a particle as a real physical object with internal parts fails, it begs the question.
What's the question?
Are these fundamental particles actually physical objects at all, or are they just pure mathematical manifestations of space itself?
Wow. That is wild. Are they even physical objects? That is definitely something for you to mull over as you go about your day. Thank you for joining us on this deep dive.
You know, usually when we think about a physical object at rest, there is this expectation of absolute stillness. Like, I don't know, a coffee cup sitting on a desk, you look at it and it's just sitting there. I mean, nothing is happening.
Right. It seems completely static. Classical mechanics basically tells us its velocity is 0, its kinetic energy is 0, and, well, that is the end of the story.
But then you step into the world of quantum mechanics and suddenly that boring stationary coffee cup isn't just sitting there. Like if you look at the fundamental particles making up that cup, they are vibrating with this invisible, furious internal machinery.
Yeah, it is the absolute definition of stillness as an illusion.
And that illusion is exactly what we are going to shatter today. So welcome to this deep dive. Today, our mission is to explore a truly dense, absolutely fascinating piece of physics history from the Feynman lectures. We're looking at Volume 3, specifically diving into how quantum probability amplitudes change over time.
And for you listening, our goal today isn't to just, throw equations at you or make you memorize formulas. We really want to conceptually understand how the universe ticks at the most fundamental level.
Exactly.
We are going to explore what change actually looks like in the quantum world.
It's going to be a wild ride. So we will start with a particle sitting completely still, then we'll push it into motion, force it to hit an unpassable nuclear wall, and finally we will watch a decaying subatomic particle, like actually dance in a magnetic field.
Yeah, and to understand how things change in quantum mechanics, we actually have to start by looking at what happens when a particle is seemingly doing nothing at all.
Okay, let's unpack this.
Yeah.
Because even when a particle, let's say an electron or an atom, is entirely at rest with absolutely zero kinetic energy, it isn't truly empty of energy. I mean, it has what physicists call rest energy.
Right, which goes back to Einstein's famous realization, right?
Yeah.
Mass itself is a form of energy. So the rest energy is simply the mass of the particle times the speed of light squared.
Yeah.
And in quantum mechanics, having a definite energy has a very specific, profound consequence.
Which is
It means the particle's probability amplitude varies in time like a ticking clock.
a ticking clock. I really love that visual. But I know the math uses something called an imaginary exponential to describe this. What does that actually mean for us physically?
Well, in the math, yeah, it's written as an exponential with an imaginary number.
Right.
But physically, you can just picture that as a mathematical engine that makes a wave spin in circles endlessly.
Okay.
Like without ever growing or shrinking, it just cycles. And the frequency of that cycle, basically how fast the clock ticks, is directly equivalent to the particle's energy divided by Planck's constant.
So a resting particle is just sitting there ticking. But there's a catch here with the uncertainty principle, right? Like, if a particle is completely at rest, it has a perfectly definite momentum, which is 0.
Yes. And the uncertainty principle dictates that if you know a particle's momentum perfectly, your uncertainty about its position must be infinite.
Which means there is an equal amplitude to find this resting particle anywhere in all of space. Like, it's essentially everywhere at once.
Exactly.
But, Feynman calls this a stationary state. If the phase of this amplitude is constantly spinning like a clock, ticking away at a furious rate, why call it stationary? I mean, it feels like calling a spinning top stationary.
Well, let's actually run with that spinning top analogy.
Okay.
Think of a top spinning perfectly upright in one exact spot on a table. Macroscopically, the object is in a single place.
Right.
The absolute square of its probability amplitude, which tells us the actual measurable chance of finding it somewhere, does not change over time.
Yeah.
That's the stationary part.
Ah, I see.
But internally, the top is a blur of constant motion. That internal spin is the phase variation.
So if the measurable probability doesn't change, nothing is actually happening. Like, to get probabilities that change in time, to see an event occur in the universe, you need more than one top. You need the interference of two different energy states.
Precisely. You need two different frequencies. When they overlap, they create a beat note, just like two slightly out-of-tune guitar strings played together.
Oh, yeah, you hear that wah-wah-wah sound.
Exactly. The sound gets louder and softer as the waves interfere. And in quantum mechanics, that interference is what creates a varying probability. That beat note is what change actually is.
That's incredible. And there's a fascinating aside in the text here about atoms in excited states that plays right into this. When an atom is excited, it has more energy, so its internal clock ticks faster.
Right.
But eventually, it radiates a photon and drops to a lower energy state. The question is, why? Why not just hold on to that energy forever?
Well, the answer actually comes down to entropy. It isn't that the atom, wants to lose energy. It's that there are simply more ways for that energy to exist, to wander around in the vast electromagnetic field than there are inside the tiny confined atom.
So the universe always moves toward the most probable situation, which usually means spreading energy out.
Exactly. Nature just loves options.
Yeah, it really does. Before we move on to actual motion, I want to clarify one thing about these energy clocks. The text points out that you can shift the baseline of the energy scale arbitrarily, like, say, subtracting the rest mass from your calculations, and it doesn't change the physics at all.
Right, because what's fascinating here is that quantum mechanics only cares about the difference in frequencies, not the absolute baseline.
Oh, okay.
Think of it like time zones. If you and I are trying to coordinate a meeting, it doesn't matter if we are both on Eastern time or both on Pacific time, as long as the difference between us is accounted for.
That makes a lot of sense.
So if you speed up every single quantum clock in the universe by the exact same amount, the beat notes, the interference patterns that dictate actual physical events, remain completely unchanged.
Wow. Okay. So we've established that a resting particle has this ticking internal clock. But what happens if we view that stationary ticking particle from a moving frame of reference? Like, say I pick up my coffee cup and walk across the room.
Well, this is where we have to bring in relativity.
Ah, of course.
If you apply a Lorentz transformation to our resting particle, which is just the math of how relativity works, things get strange. In relativity, if you move past a clock, space and time get mixed together.
Okay.
What was purely a time variation in the particle's rest frame suddenly bleeds over into a spatial variation in your moving frame.
Wait, so because I'm moving past the particle, the phase of the particle doesn't just change as time ticks forward, it also changes depending on where I look in space.
Yes. And the math of this relativistic shift naturally yields the famous de Broglie wavelength formula.
Oh, where wavelength equals Planck's constant divided by momentum.
Exactly. The spatial wave variations, the ripples in the amplitude, are directly tied to the particle's momentum. The faster you move relative to the particle, the tighter those ripples get.
But a single perfect wave just stretches on forever across all of space. To get a particle that actually looks like it's in a specific place and moving, you can't just have one wave, right?
No, you can't.
You have to add several amplitudes of slightly different frequencies and momenta together. They interfere with each other.
Right. They create what we call an interference lump or a wave packet. Inside the lump, the waves reinforce each other, so the probability of finding the particle there is high.
Got it.
Outside the lump, they cancel each other out.
Yeah.
And because the different waves making up the lump are traveling at slightly different speeds, the lump itself moves through space.
Wait. If we have this lump of waves moving, how fast is it actually going? Because it's made of all these underlying ripples.
Well, if you calculate its group velocity, which is basically the speed of the lump itself moving through space, the math simplifies down incredibly cleanly. It comes out to momentum divided by mass.
Hold on. Momentum divided by mass. That is just standard velocity. Like, that's how we calculate the speed of a baseball.
Yeah, it is exactly the classical velocity. What's fascinating here is that relativity combined with these quantum rest amplitudes perfectly recovers classical motion.
That is wild.
It acts as a seamless bridge between the bizarre, abstract quantum world of spinning phases and the concrete physics of a baseball you see every day. The macroscopic world of moving objects is literally built out of these microscopic beat notes moving through space.
That is seriously mind-blowing. Our everyday reality is just the group velocity of interfering quantum waves. Okay, so now we have our probability lump moving smoothly through empty space, but, the universe isn't an empty highway. What happens when that moving wave suddenly slams into an obstacle, like a force field or a change in potential energy?
Well, a constant potential everywhere just changes the 0 point of the energy scale, which, as we already established, doesn't change the physics.
Right.
But if a particle passes from one potential to a lower potential, its total energy stays the same, but its kinetic energy increases. It speeds up.
And because it speeds up, its momentum increases, which means its wavelength gets shorter. The ripples get tighter. That makes intuitive sense.
Yeah, but here's the real problem. What if the potential suddenly shoots up, creating a barrier with a higher energy than the particle actually possesses?
Okay, classically, this is simple. Imagine a ball rolling up a steep hill. If it doesn't have enough kinetic energy to reach the top, it stops, turns around, and rolls back down. It bounces off the barrier.
Exactly. But quantum mechanically, the wave equation does something incredibly strange.
Yeah, because total energy has to be conserved. If the potential energy of the wall is higher than the particle's total energy, the kinetic energy suddenly has to become a negative number.
Right.
And since kinetic energy is mathematically related to momentum squared, the momentum has to become an imaginary number.
Which I know sounds like a math trick.
Yeah, whoa, back up. Imaginary momentum. Does that mean the particle just, stops existing?
No, not quite.
Yeah.
I mean, it just means the wave stops acting like a typical wave. When you plug an imaginary number for momentum into the wave equation, the space dependence stops oscillating up and down. Instead, it turns into a real exponentially decaying amplitude.
Oh.
The probability wave crashes into the wall and quickly fades out, almost like a sound being muffled by a thick door.
So it doesn't bounce off cleanly. The wave pushes into the wall, dying off rapidly the deeper it goes. If you were to graph this out, you'd see the rippling wave hit the barrier and then just smoothly curve down towards zero.
Right, but here is the kicker. It decays, but if the barrier is thin enough, the wave doesn't hit zero before the barrier ends.
Wait, really?
Yeah. A tiny amount of that amplitude reaches the other side and resumes oscillating as a normal wave. This means the particle has a small but entirely real probability of just, leaking through a solid wall.
Quantum tunneling. Oh man, it reminds me exactly of total internal reflection of light.
Oh, that's a great example.
Like if you shine light inside a block of glass at a sharp angle, it hits the edge and bounces back completely. It won't escape. But the light actually bleeds just a tiny fraction of a millimeter outside the glass. And if you put another piece of glass within that microscopic gap, the light jumps the gap and continues on.
Exactly. The wave nature of the phenomenon bridges a gap that a purely solid object couldn't. It's a perfect macroscopic equivalent.
But just to push back and clarify for you listening, it isn't that the particle is literally breaking through the wall like a wrecking ball. It's that the particle's very existence, its probability, is smeared out in space. And a tiny fraction of that smear just happens to exist on the other side of the unpassable wall, right?
Yes, that is definitely the best way to visualize it.
Hmm.
And, this isn't just a neat theory. It is the fundamental mechanism behind radioactive decay. Take the uranium alpha decay example from the text.
Okay.
An alpha particle sits trapped inside a uranium nucleus, held in by a massive, incredibly strong potential energy barrier.
And the natural oscillations of that alpha particle inside the nucleus are violently fast. It bounces against the walls of its nuclear prison 10 to the 22nd power times per second. That is a 1 with 22 zeros.
But the barrier is so high and thick that the probability of tunneling through that leakage factor we talked about is tremendously small. Mathematically, it's about e to the power of negative 45.
To put that in perspective, e to the negative 45 is a decimal point, followed by about 19 zeros before you hit a real number. It's vanishingly close to impossible.
Oh, it's impossible, yes. But because it's bouncing 10 to the 22nd times a second, eventually it hits the jackpot.
Wow.
But the scale is staggering. Because the probability is so low, the mean life of that alpha particle inside the nucleus is 4.5 billion years.
That's insane.
We are connecting an impossibly fast microscopic timescale with a literal geologic timescale, and it's all governed by the simple exponential decay of a probability wave hitting a wall.
It is just wild to think about a subatomic prison break that takes billions of years. Okay, so we've seen how a straight-on barrier leads to tunneling. But what if a potential energy field pushes the moving particle from the side, like, say, a crosswind?
Well, imagine a particle moving forward, but it encounters a transverse potential gradient. Basically, the potential energy is higher on its right side than on its left side.
Okay, higher potential energy means less kinetic energy, which means smaller momentum.
And as we established earlier, smaller momentum means a longer wavelength.
Hmm.
So the right side of the probability wave now has a longer wavelength than the left side.
Let me try an analogy to visualize this.
Go for it.
So what does this all mean? Imagine a marching band trying to walk straight across a field, but the right side of the field is thick mud and the left side is dry grass.
Okay.
The right side of the band hits the mud and their steps get shorter, or in the quantum case, the phase of their steps gets slower, making the wavelength longer. Because one side is taking longer steps than the other, the entire line of the marching band naturally wheels to the right.
Right. And because those steps get longer on one side, the wave nodes, the lines where the wave hits zero, actually start to tilt. This bending of the wave nodes physically redirects the trajectory of the entire probability wave.
It curves the path of the particle.
Exactly. And the most beautiful part of this section in the text is the math. If you calculate this quantum phase bending, it matches exactly with the classical angle of deflection you would get if you just used Newton's old reliable F equals ma.
That is just incredible.
Once again, in the classical limit, when the potential variations are slow and smooth over large distances, quantum mechanics perfectly agrees with Newtonian mechanics.
So the invisible microscopic phase shifts that are stretching and compressing are the classical macroscopic forces that you feel every day, like gravity, magnetism, physical pushing. It's all just the bending of wave nodes.
Everything is waves.
The forces we feel are just wave refraction, which is the perfect lead-in to our final act. We've looked at motion through space, hitting walls head-on and being pushed by crosswinds. Now we need to look inside the particle itself. What happens to the internal property of spin when you subject it to a magnetic field over time?
Well, spin is a purely quantum property. It's an intrinsic angular momentum. For spin one-half particles, like electrons or muons, they can align their spin with a magnetic field or against it.
Okay.
And here is the key. They have different potential energies depending on that alignment.
And as we've learned, different potential energies mean their internal clocks tick at different rates.
Right. The amplitude of the spin-up state and the amplitude of the spin-down state will have their phases change at the exact same rate, but in opposite directions. Like one clock hand spins clockwise, the other spins counterclockwise.
Feynman outlines a brilliant experiment using muons to prove this. Muons are these heavy, unstable cousins of the electron.
Yeah.
They only live for about 2.2 microseconds before they decay into an electron and 2 neutrinos. And when they decay, they preferentially shoot that electron out in the direction exactly opposite to the muon spin.
So the electron essentially acts like a tracer flare, showing us exactly where the spin was pointing at the exact moment of the muon's death.
Right. So picture this. You have a block of material, and you shoot a beam of muons into it. They enter with their spins pointing perfectly horizontally along the x-axis. Then you turn on a strong magnetic field pointing vertically along the z-axis.
And because of that vertical magnetic field, the spin-up and spin-down states start changing their phases in opposite directions.
Okay.
When you mathematically recombine those states to ask, what is the probability the spin is still pointing horizontally along the x-axis? The math gives you a cosine squared function.
Meaning the probability of finding the spin on the x-axis oscillates over time. It starts at 100%, drops to 0, goes back to 100% over and over.
Exactly.
This means the spin is physically precessing like it is rotating around the z-axis like a wobbling gyroscope at a very specific frequency.
Yeah, that frequency is called the precession frequency, and it is directly proportional to the strength of the magnetic field and the magnetic moment of the mu1.
Here's where it gets really interesting, though. Let me push back, because this is a wild concept to measure. We can't actually see the spin rotating inside the block, right? Like, we can't watch it wobble.
Nope, we can't.
We only know it's precessing because when the muon finally dies and shoots out its electron, the direction that electron shoots tells us exactly where the hands of the clock were pointing at that exact microsecond.
That is exactly how it works. You can't watch a single muon wobble. But if you shoot millions of muons into the block and measure the macroscopic spray of electrons coming out over time, you see a perfect oscillating wave in the data.
Oh, wow.
The number of electrons shooting out horizontally pulses up and down, and that pulse maps exactly to the cosine squared probability function.
We use the explosive decay of millions of particles to take stop-motion snapshots of their internal phase clocks.
Yeah. If we connect this to the bigger picture, this muon experiment beautifully encapsulates everything we've talked about today.
It really does.
You have an internal property of a particle sitting at rest. That property is influenced by a potential, the magnetic field. That potential causes the probability amplitudes to vary over time at different rates. And those interfering variations lead directly to a macroscopically measurable result.
It is just a masterpiece of logical physics. So let's sort of summarize the journey we just took you on. We started with a coffee cup and stripped it down to the invisible clocks of resting atoms, spinning endlessly but staying stationary.
Right. And we realized that physical motion, like a baseball flying through the air, is just the group velocity of interfering quantum beat notes moving across space.
We saw how an imaginary momentum stops away from rippling and turns it into an exponential decay, leading to a 4.5 billion year nuclear prison break for an alpha particle.
And we saw how the refraction of probability waves creates the perfect illusion of Newtonian forces.
And finally, we saw how the magnetic precession of a dying muon reveals the invisible ticking clockwork of the quantum world.
It fundamentally changes how you view the universe, doesn't it?
It really, really does. And I want to leave you with one final mind-expanding idea to ponder on your own. If our entire macroscopic reality, the solid walls we can't walk through, the physical forces we feel pushing against us, and the steady forward march of moving objects, if all of that is ultimately just the emergent result of invisible probability waves constantly shifting their phases and interfering with one another, then is the solid world you interact with every day just an illusion created by a cosmic symphony of intersecting frequencies? Just, keep that in mind the next time you look at a coffee cup or try to walk through a wall. Imagine looking at a physical object, let's say a tiny pyramid-shaped molecule, and you're just watching its central atom do something completely, illegal.
Right. Illegal according to classical physics anyway.
Exactly. I mean, according to every fundamental rule we're taught, this atom is trapped. It just doesn't have the energy to move.
But if you watch it closely enough, it vanishes from one side of a solid barrier and just instantly materializes on the other side.
Yeah, it simply ghosts its way through solid matter over and over again in this really rhythmic, impossible dance.
And, it sounds like pure science fiction, but that impossible dance is actually happening inside almost every object around you right now.
Which is wild.
Yeah.
And to truly grasp how that happens, you really have to fundamentally change the way you think about reality.
You do. You have to abandon the whole idea of a solid, permanent universe and embrace a landscape that's defined by shifting probabilities.
Which brings us to our mission for this deep dive. We are taking on some of the most profound, seemingly impenetrable mathematical concepts in quantum mechanics.
The really dense stuff.
Yeah, the heavy stuff. And we're going to translate them into an intuitive, hopefully awe-inspiring understanding of how our universe actually changes from one tiny fraction of a moment to the next.
And to guide us, we're turning to an absolute masterclass of physics. We're looking at an excerpt from the legendary Feynman Lectures on Physics, specifically Volume 3, Chapter 8.
Right, and the main focus of this chapter is a concept known as the Hamiltonian matrix.
Which is a heavy term.
It is. Now, if hearing the words Hamiltonian matrix makes your eyes instantly glaze over, just stay with us. Even if complex math usually feels like hitting a brick wall, we are going to walk through this together.
Step by step.
Exactly. We're going to start by decoding a brilliant, almost poetic mathematical shorthand, and then follow it all the way down to that physical, real-world example of an ammonia molecule doing the impossible.
So the journey begins with what is actually a deceptively simple question.
Okay, lay it on me.
Well, before we can even begin to talk about how the universe changes over time, we have to figure out how to describe the universe when it is completely paused.
Like freezing a frame in a movie.
Right. If you freeze time, how do physicists actually write down the state of a quantum system?
Because, I mean, you obviously can't just take a microscope and a tape measure to an electron. You can't just pin it down like a butterfly on a board.
No, the classical tools completely fail us at that scale.
Yeah.
So quantum mechanics handles this by leaning heavily on an analogy to something much more familiar.
Which is?
Ordinary three-dimensional vectors. So picture a standard arrow drawn in 3D space.
Okay, got it in my head.
You can describe the exact position and direction of that arrow by breaking it down into 3 coordinates: an x direction, a y direction, and a z direction.
Right, the basic geometry stuff.
Exactly. Physicists call those the base vectors. If you know how far the arrow travels along x, y, and z, you know absolutely everything about the arrow.
Okay, let's unpack this. If I'm trying to describe a quantum state to you, it feels a lot like describing a specific color on a computer monitor.
Oh, that's a great way to think about it.
Yeah, because you don't just say, oh, it's a weird purplish blue. You give the exact RGB values. You say it is 40% red, 20% green, and 80% blue.
Right, you break it down into its fundamental parts.
So instead of colors, though, the base states in quantum mechanics are the fundamental physical possibilities of the system we are looking at.
That analogy holds up beautifully. Any quantum state, no matter how bizarre it seems, is essentially a mixture.
A cocktail of states.
Exactly. It can be completely described by its amplitudes, which, you can think of as the exact mixing proportions to be found in those various base states.
So if I give you that list of mixing proportions, I've basically handed you the complete identity of that quantum state.
You have. But when you look at the Feynman lectures, the way physicists actually write down those mixing proportions doesn't look like a simple RGB value.
No, it looks incredibly strange.
It does. And that brings us to the physicist Paul Dirac. He invented a piece of notation called the bracket notation.
Bracket?
Yeah. Now, usually when we write out an amplitude in physics, it's enclosed in a bracket. You have a starting state on the right, an ending state on the left. They're separated by lines, and the whole thing is enclosed by angle brackets.
Just standard math notation.
Right. But Dirac looked at that symbol and had this absolute stroke of genius. He literally chopped the mathematical symbol right in half.
He just split the equation down the middle.
He did, leaving these dangling, unfinished symbols. He called the left half a bra and the right half a ket.
Put them together, you get a bracket. Okay, physicists love their puns.
They really do.
Yeah.
But this wasn't just a clever joke. By chopping the symbol in half, Dirac created a way to represent an abstract, unfinished quantum state.
Unfinished how?
Well, a ket by itself isn't a measurable number. It's basically a puzzle piece waiting to be connected. It's a physical state looking for a destination.
Oh, I see.
Only when you snap a bra and a ket together do you complete the calculation and get a real physical probability that you can actually measure in a lab.
That feels almost linguistic, like writing half of a sentence. A ket is like a subject wandering around without a verb. It needs the bra to make a complete mathematical thought.
Consider it an alphabet of reality. In fact, our source material enthusiastically points out what it calls the great law of quantum mechanics.
Which sounds very dramatic.
It is. On the page, it's just a string of these half symbols that looks entirely alien to most people. But conceptually, it's this profound reminder.
What does it tell us?
It tells us that absolutely any state in the universe can be expressed as a sum of these foundational base states. Underneath the infinite, swirling complexity of nature, there's a fundamental alphabet we can use to spell out any physical situation.
I love the idea of a universal alphabet, but man, that brings up a massive conceptual hurdle. Well, if this math requires us to map out these base states, the letters of this alphabet, What actually are the base states of the real physical world? I mean, what level of detail does the universe demand we care about?
That is the ultimate headache for any physicist trying to model nature. And, well, the answer entirely depends on scale.
Okay, let's start small.
Let's start with something incredibly basic, a single electron. To completely define the state of an electron, you really only need to track its momentum and its spin.
Spin being whether its invisible magnetic compass is pointing up or down.
Exactly. That's your base state. It's very manageable.
Two properties, a momentum value and an up or down spin. I can wrap my head around that.
But watch what happens when you scale up just slightly. Introduce a second electron.
Okay, 2 electrons.
Now, you don't just have 2 spins. You have 4 possible combinations. Both up, both down, first up and second down, first down and second up.
Plus the momentums.
Right. You have 2 entirely different momenta to track and calculate interactions for. Now, imagine a system with 7 electrons. The math gets exponentially heavier.
And I have to jump in and push back here because this seems to lead to a completely impossible scenario.
What do you mean?
If we are trying to track particles, we know particles have inner parts. A hydrogen atom is an electron and a proton isn't even a solid ball. It's a bag of quarks and mesons, and what the text literally refers to as strange particles.
Yes, the subatomic zoo.
Right. So doesn't this base state mapping become an endless, unnavigable fractal of complexity? Do we seriously have to map out the inner gears and wheels of every single microscopic strange particle just to calculate basic everyday chemistry?
What's fascinating here is that nature actually gives us a way out.
Oh, thank goodness.
We don't have to map the fractal depths of every particle thanks to something called a low-energy approximation.
The low-energy approximation. Walk us through how that saves us from the math.
Think about a beaker of water sitting on a table, or 2 hydrogen atoms bumping into each other during a standard chemical reaction.
Just everyday stuff.
Right. These are incredibly gentle events on a cosmic scale. The kinetic energy of these collisions is very low, usually well below 10 electron volts.
Okay.
At that low energy, an amazing thing happens to the internal gears and wheels of the nucleus. Absolutely nothing.
Wait, really? They just sleep through the collision. The energy isn't high enough to wake up the internal part.
That is the perfect way to visualize it. The internal components of the proton, the mesons, the strange particles, they require massive amounts of energy to get excited or change their state.
So it's like a fender bender where the people inside the car don't even spill their coffee.
Exactly. Because a normal chemical collision doesn't provide anywhere near that much energy, those internal states remain completely frozen.
And because they don't change.
We can entirely ignore them in our math. We can treat a wildly complex multi-part hydrogen atom as just one single simple object.
Wow.
It vastly reduces the alphabet we need to use, making the mathematics of everyday reality actually solvable.
That is a massive relief for anyone trying to do chemistry. So by sticking to these low-energy environments, we can define our base states without spiraling down into the subatomic guts of the universe.
Right.
We have our frozen, paused picture of reality.
You have the photograph.
Yeah.
But, the universe is a movie. It doesn't stay paused.
No, it keeps moving.
The next monumental task is figuring out how these carefully defined quantum states evolve the moment you hit play.
And to figure that out, the Feynman text introduces what might be the strangest scientific instrument ever conceived.
Oh, it's brilliant.
It isn't a laser or a massive subterranean particle collider. To see how the universe changes, the text introduces the apparatus of simply waiting.
Waiting as an active physical operation. It's so counterintuitive, but it works. You prepare your quantum state in the lab, you step back, and you just let time pass.
You wait from time 1 to time 2.
Exactly. During that delay, you might have magnetic fields turned on, or outside forces, or perhaps just the silent ticking of the clock.
Yeah.
Whatever the conditions, the quantum state you have at the end of the wait will not be exactly the same as the one you started with.
Because even if you do nothing, the probabilities of where things are and what they are doing inherently shift.
Yes. The universe is restless. Physicists describe this act of waiting using a mathematical concept called the U-matrix.
The U-matrix.
You can think of the U-matrix as a massive calculation engine. You feed it your starting state and the amount of time you waited, and it turns out the exact amplitudes for every possible state your system could have evolved into.
There's a really fun detail in the text about this. It talks about the high-class theoretical physicists pacing the halls, obsessing over something called the S-matrix.
Yes. The S-matrix is basically the white whale for high-energy particle physicists.
The ones smashing protons together at near light speed.
Right. But the secret is, the S matrix is just our weighting apparatus, the U matrix, stretched out to infinity.
To infinity.
Yeah, they're trying to calculate the ultimate weight, starting from the infinite past, long before the particles collide, all the way to the infinite future, long after the debris has scattered.
So what does this all mean for us? We aren't smashing particles at light speed. For the everyday physics we care about, we don't need to wait for infinity.
Not at all.
Instead of stretching time out, we're doing the exact opposite. We are chopping time down into microscopically tiny frame-by-frame slices to see exactly how probability leaks from one state to another over a fraction of a microsecond.
We're taking the slice of time and shrinking it closer and closer to zero. And when you run the math on an infinitesimally small slice of time, a new set of values emerges. Physicists label these values with the letter H.
The Hamiltonian matrix.
The Hamiltonian. This is the holy grail of a quantum system. You can picture the Hamiltonian matrix as a vast control board of dials.
A control board of tiles. I like that.
Every possible base state has a dial connecting it to every other base state. The Hamiltonian tells you exactly how fast probability is flowing from one state to another at any given moment.
Wow.
It's the fundamental dynamical equation of quantum mechanics.
Right.
If you know the Hamiltonian of a system, you have the source code. You know exactly how that system will behave forever.
The text actually mentions that calling it the Hamiltonian is just a historical quirk. It really should be called the energy matrix.
Because the dials on that control board, the rates at which these probabilities shift, are directly tied to the fundamental energy levels of the physical system.
Okay, let's pause and look at where we are. We have used Dirac's chopped up puzzle pieces to define our quantum alphabet.
Right.
We've avoided the fractal complexity of strange particles by keeping the energy low. And we have taken our weighting apparatus, chopped time into near-zero slices, and uncovered this Hamiltonian control board that dictates the rules of the universe.
It's quite a journey.
It is majestic, but it is also incredibly abstract. It feels like we are just floating in a void of pure math right now.
Which is exactly why the source material doesn't leave us floating. It takes this abstract Hamiltonian engine and forces it to drive a real physical object you can hold in a laboratory.
The ammonia molecule.
Yes, NH3. One nitrogen atom bonded to 3 hydrogen atoms. If you look at its geometry, it forms a tiny pyramid.
A molecular period.
The 3 hydrogen atoms make a flat triangular base, and the single nitrogen atom sits up at the top, forming the peak.
Now, earlier we talked about how a real molecule is wildly complex. It tumbles, it spins, it vibrates in a dozen different directions.
Right, but to test our math, we freeze all of that noise. We assume the molecule is completely locked in place in space.
So it's not spinning.
It's essentially frozen, leaving us with only one moving part to care about the position of that central nitrogen atom. Geometrically, there are only 2 stable places for that nitrogen to be.
Where are they?
It can sit above the flat plane of the hydrogen atoms, we will call that state 1, or up. Or it can sit below the plane of the hydrogen atom, state 2, or down.
By stripping away the noise, we have built a pure 2-state system. State 1 is up, state 2 is down.
Exactly.
Let's say you prepare this molecule in a lab. You measure it, and you know with 100% certainty that the nitrogen is currently pointing up in state 1.
You have locked in your initial conditions.
Here's where it gets really interesting. If you apply the rules of classical physics, the physics that govern baseballs and brick walls, that nitrogen atom is physically trapped.
Completely stuck.
To get from up to down, it has to pass straight through the flat base of the 3 hydrogen atoms. Classical mechanics calculates the energy required to push through that dense floor of atoms and concludes the nitrogen simply doesn't have it.
It's a wall it can't break.
It's an impossible movement, energetically illegal. The nitrogen should be stuck in state 1 until the end of time.
Under classical rules, yes, it hits a solid wall. But when we look at the Hamiltonian dials for this quantum system, the dial connecting state 1 to state 2 is not set to 0.
Wait, really?
Quantum mechanics dictates that the atom has a continuous ability to bypass the barrier entirely. It tunnels.
Wait, stop. I need to admit genuine confusion here because this breaks my brain a little bit. It just tunnels. It goes through a solid floor of atoms. How is that even physically possible?
It forces us to abandon the idea that the nitrogen atom is a hard, solid little sphere. In quantum mechanics, particles also behave like spread-out waves of probability.
Okay, waves.
The nitrogen isn't a pinpoint. It's a wave that smears out across space. And when a wave hits a barrier, a tiny bit of that wave inevitably bleeds through to the other side.
It just leaks through.
Exactly. Because the wave exists on both sides of the impossible barrier, the atom has a real physical probability of simply appearing on the other side without ever having pushed its way through.
So because it's a wave, it doesn't have to break down the door. It just inherently exists a little bit on the other side of the door.
Precisely. And because it can sneak through, the two states up and down are continuously talking to each other. They're coupled.
If these two states are constantly bleeding into one another across an impossible barrier, how does that affect the molecule's actual existence? What does that do to the energy?
It changes the fundamental structure of the molecule's reality. You would naturally assume that a resting molecule has one baseline energy level.
Sure.
But because the nitrogen is constantly leaking back and forth, the resting energy actually splits. The interaction creates a doublet.
A doublet?
The molecule now possesses two distinct energy levels, one slightly higher than expected and one slightly lower.
That's crazy. The mere ability to do this impossible trick fundamentally alters the energy of its existence.
Yes, and it entirely dictates its existence in time. Let's return to our weighting apparatus. Start your stopwatch.
Tick-tock.
The molecule is in state 1. As the clock ticks forward, the Hamiltonian control board goes to work. If you graph the probability of finding the nitrogen in state 2, the math doesn't spit out a straight line.
What does it do?
It generates a perfect rhythmic sine wave.
Meaning the probability rises and falls like a tide. It starts at 0 probability, smoothly swells up until it is absolutely certain to be in state 2, and then receding smoothly back to 0.
While simultaneously, the probability of finding it in state 1 does the exact inverse. It's a continuous, mesmerizing rhythm.
The Feynman text uses this incredible analogy to help visualize this. Imagine two heavy pendulums hanging side by side.
Okay.
If you connect them with a very weak, flimsy spring, you couple them together. You pull the first pendulum back and let it go. It swings normally at first, but because of that flimsy spring, it starts bleeding its kinetic energy over to the second pendulum.
The second pendulum slowly wakes up and begins to swing.
Right, and as the second one swings wider and wider, the first one starts losing momentum. The swings get shallower, until eventually the first pendulum comes to a complete dead stop.
Just hanging perfectly still.
Yes, while the second pendulum is doing all the swinging. But it doesn't end there. The weak spring is still attached, so the entire process reverses. The energy sloshes backward.
Just beautiful physics.
That mathematically is exactly what is happening to our ammonia molecule. The actual physical reality of where that nitrogen atom exists is endlessly sloshing back and forth across a solid barrier.
Sloshing captures it beautifully. And we should point out, this rhythmic sloshing isn't just a fun mathematical quirk on a chalkboard.
No.
No, it's a highly precise, measurable frequency. In fact, scientists harnessed the exact quantum beating of this ammonia molecule to invent the first maser.
The microwave precursor to the laser.
Exactly, and to build the very first highly accurate atomic clocks. This impossible trick is literally the heartbeat of modern precision technology.
It is staggering to step back and look at the path we just walked. I mean, we started with Dirac's chopped up brackets floating in a void of pure math.
We learned to isolate our quantum alphabet by ignoring the inner chaos of strange particles.
Right. We turned the simple act of waiting into a scientific apparatus.
We chopped time into microscopic slices to uncover the Hamiltonian control board, the true engine of quantum change.
And we used that exact engine to watch an ammonia molecule completely shatter the rules of classical physics, endlessly sloshing its central atom through a solid wall of hydrogen.
It demands that you visualize the microscopic universe not as a static painting, but as an endlessly churning ocean of probabilities.
Which leaves us with one final, deeply provocative thought for you to take away.
Yeah.
Toward the very end of our source text, Feynman points out a fascinating irony.
What's the irony?
The classical physics formulas that we use to describe the macro world, like calculating how light bends through a glass window, actually work best when we replace our standard model of atoms with harmonic oscillators.
Meaning?
Our everyday math works perfectly when we pretend that the atoms making up solid objects are just vibrating, oscillating pendulums.
Even though, from a purely classical standpoint, treating solid matter like a collection of swinging pendulums makes absolutely no sense.
Right, so think about the implications of that. We just proved that a freezing cold stationary ammonia molecule is actually vibrating back and forth, sloshing its very existence across an impossible barrier.
It's not sitting still.
No. So could it be that everything around you, the desk you were sitting at, the screen you were looking at, the floor beneath your feet,
Even the atoms making up your own body.
yes, Could it be that all of this solid matter is better understood not as a collection of fixed, permanent objects, but as a vast, unimaginably complex, interconnected network of probabilities endlessly sloshing back and forth their own invisible quantum rhythms? It is definitely something to ponder the next time you lean your hand against a solid brick wall.
Every time you look at the GPS on your phone, to navigate to a new coffee shop or whatever, or every time you successfully connect to a satellite signal, you are actually relying on this incredibly bizarre, almost impossible geometry of a single microscopic molecule of ammonia.
Yeah, it really does sound like science fiction when you phrase it that way.
It does. I mean, the entire infrastructure of our modern, hyper-connected world hinges on this weird quantum quirk that happens inside a cloud of gas.
It's just, well, it is one of the most beautiful translations of pure theory into physical reality that we have, because for decades, quantum mechanics was treated as this purely abstract realm.
Like just equations on a chalkboard.
Exactly. It was Schrödinger's cat, or thought experiments that felt completely disconnected from the heavy mechanical world of, gears and levers that you and I actually live in.
But the source material we are diving into today completely shatters that wall between the chalkboard and the real world.
Yeah.
We are using notes and texts from the legendary Feynman lectures on physics, specifically Volume 3, Chapter 9 as our map for this deep dive.
Yes, a really classic text.
Okay, let's unpack this, because if we want to take quantum mechanics out of the theoretical realm and see how it actually powers a physical machine, we need to understand the moving parts.
Right, we have to start at the absolute bottom.
Yeah, the structural architecture of ammonia. So if you were to zoom in on an ammonia molecule right now, what does it actually look like?
Well, it's deceptively simple. Just one nitrogen atom and 3 hydrogen atoms. But imagine a tiny pyramid. The 3 hydrogen atoms sit flat, right? They form a triangular base.
Okay, I'm picturing the triangle.
And then the single nitrogen atom sits right on top of that triangle, forming the peak. It looks perfectly stable, kind of like a tripod.
Right.
But in the quantum world, it is anything but stable.
Because that nitrogen atom at the top doesn't just sit there, right?
Yeah.
It has this relentless habit of jumping.
Continually jumping. Yeah, the nitrogen atom physically pops back and forth. One moment it's sitting on top of the hydrogen plane, and the next it punches straight through that plane and sits on the bottom.
Oh, wow.
Yeah, flips up and down over and over again.
Wait, this sounds exactly like a reversible umbrella getting caught in a heavy windstorm.
Oh, that's a brilliant way to visualize it.
Like, you were walking down the street, a gust hits, and the canopy violently pops inside out. The handle, the center of gravity hasn't really moved, but the shape is inverted. And then the wind shifts, and it pops back. So the nitrogen atom is just, popping inside out.
That is exactly it. And physicists refer to these two positions as the base states. So state 3 is the umbrella pointing up, and state 3 is the umbrella pointing down.
Got it. Up and down.
Now, here is where the physics gets incredibly counterintuitive. Because this nitrogen atom is constantly tunneling back and forth between these two states, the energy of the entire molecule does something very strange. It splits.
Wait, so instead of just having one baseline energy level, it suddenly has 2.
Yeah. What's fascinating here is, if the nitrogen couldn't flip, right, if it was just rigidly glued to one side of that triangle, the ammonia molecule would only have a single static energy level.
Like a normal object.
Right. We call it E0. But it's the very act of the quantum flip itself, that dynamic movement, that forces the energy to split into 2 distinct stationary states. So you get a slightly higher energy state and a slightly lower energy state.
And the gap between those 2 states is what we really care about, right?
Right.
Because the notes mention this gap is tiny. It's something like 10 to the negative 4th electron volts.
Yes. Practically microscopic.
But that sounds almost negligible.
It is a minuscule amount of energy, which the math represents as 2A. But in physics, every specific energy gap corresponds to a very specific frequency of electromagnetic radiation.
Right.
So if a molecule drops from the high energy state to the low energy state, it releases that exact chunk of energy as a wave. And for ammonia, that specific energy difference translates to a frequency of exactly 24,000 megacycles.
24,000 megacycles.
Yes.
Which puts it right in the microwave region of the spectrum, right?
Exactly.
It's a wavelength about 1.25 centimeters. So it isn't emitting light that you or I could see with our eyes. It is emitting invisible microwaves.
And that number, 24,000 megacycles, is really the heartbeat of this entire deep dive. Everything revolves around that.
Yeah.
But to actually harness it, To build a machine that uses this microwave energy, we run into a massive engineering roadblock.
Right, because if you just have a canister of normal ammonia gas sitting in a lab, it's a completely chaotic mix.
Total tear.
You have billions of molecules. Half of them are in the high energy state, and half of them are in the low energy state. If you want to extract energy from them, you can't just use the raw gas. You have to, sort them out.
Yeah, you have to separate the wheat from the chaff, so to speak. And to do that, physicists exploit another quirk of the ammonia molecule, which is its electric dipole moment.
Okay, let's break that down for the listener, because electric dipole moment sounds incredibly dense. This just means the molecule is electrically lopsided, right?
Essentially, yes. In an ammonia molecule, the electrons, which carry a negative charge, of course, they tend to cluster closer to the nitrogen atom at the peak of our pyramid, rather than the hydrogen atoms at the base.
So the umbrella has a slightly negative charge on the canopy and a slightly positive charge on the handle.
Right. It acts like a tiny microscopic magnet, but, for electricity instead of magnetism. And ammonia is highly polarizable, meaning it is incredibly sensitive to external electrical forces. So physicists realized that if they expose this gas to a strong static electric field, those two energy states we talked about react very differently.
Oh, so?
Well, the high energy state gets pushed even higher, and the low energy state gets pushed lower. You actually see this in figure 9-2 of the notes. It creates this sort of hyperbola shape on the graph.
Okay, so knowing that, we can physically sort them. The source text describes this brilliant physical setup. You shoot a narrow, high-speed beam of ammonia gas out of a jet in a vacuum.
Right.
It passes through a pair of slits to make it a perfect straight line. And then it flies into a region with a massive transverse electric field. But it isn't just a uniform field. The notes emphasize it has a huge gradient.
Yeah, the gradient is the secret sauce here. Imagine the beam flying down a tunnel. If the electric field was exactly the same everywhere in the tunnel, nothing would happen.
Right, it would just pull evenly.
Exactly. But a gradient means the electrical pull is wildly uneven. It is incredibly strong on the walls of the tunnel, but very weak directly in the center.
Because of that uneven pull, and because our ammonia molecules are those tiny electrical magnets we talked about, physical forces actually start yanking on them as they fly at top speed.
Yes, and the molecules in the upper state, the high-energy ones, are physically repelled by the strong parts of the field, so they get pushed toward the center, where the field is weakest.
Oh, I see.
Meanwhile, the lower state molecules are attracted to the strong parts of the field, so they get yanked outward toward the walls.
It is a physical sorting hat. You shoot a mixed beam in, and the electric gradient literally bends their flight paths. The high-energy molecules fly straight down the middle, and the low-energy ones get pulled away and discarded.
Exactly.
But wait, I have to push back on this. Wait, why are we tossing away the lower-energy molecules completely? Doesn't the system need both to work? I mean, usually you need positive and negative, right?
It does feel wasteful, I agree, but it is an absolute necessity. Remember, the goal of the maser is to extract energy.
Right.
If we let that unfiltered beam into our final chamber, the low-energy molecules would act like highly efficient quantum sponges.
Sponges.
Yeah, because the moment a high-energy molecule released its microwave energy, a neighboring low-energy molecule would instantly absorb it so it could climb back up to the higher state.
Oh. They would just trade the energy back and forth internally.
Exactly. You would end up with zero net power leaving the machine. It would just be self-contained. To get a surplus of energy out, you must banish the sponges. You need a pure, unadulterated beam of only high-energy molecules.
Okay, that makes perfect sense. So now we have it. We have this isolated, purified beam of high-energy ammonia flying through a vacuum. Now comes the main event, right?
Yep.
We have to wring the energy out of them. We have to force them to drop from state I down to state 2, so they actually hand over that microwave energy.
And we do that by aiming our pure beam straight into a highly engineered metal box. It's called a resonant cavity.
But if they just fly into an empty metal box, nothing happens, right? They'll just keep flying.
No.
We need some sort of trigger.
The trigger is an oscillating electric field inside the cavity. Now, unlike the static, unmoving field we use for the sorting, this field is pulsing. It is waving back and forth.
Okay.
And crucially, it is pulsing at exactly 24,000 megacycles, the exact frequency of the ammonia molecule's energy gap.
This sounds exactly like pushing a kid on a playground swing.
Oh, that's a good comparison.
Like if you just walk up to a swinging kid and shove them randomly, you might actually stop them. You might push when they are swinging backward toward you, and you just kill all their momentum.
Right, it's clumsy. But if you time your pushes perfectly.
Right. If the frequency of your push exactly matches the natural rhythm of the swing, you transfer maximum energy. You force the swing higher.
Exactly.
So in this case, the oscillating field in the metal box is timing its electrical pushes perfectly with the natural quantum wobble of the ammonia molecule. It like bullies the molecule, forcing it to flip and drop its energy.
That is resonance in a nutshell. It is all about perfect synchronized timing. And the Feynman text really delves into the transition probability here. It shows that the chance of a molecule dropping its energy oscillates like a wave. It's a sine wave, actually.
Oh, interesting.
Imagine a chart where the probability rises from 0 up to 100% and then falls back down.
And there is a mathematical sweet spot, right? Like a Goldilocks duration for how long it stays in the box.
Precisely. The math shows that if the molecule stays inside that pulsing cavity for an exact perfect fraction of a second, a duration defined by the strength of the field, where the math actually equals pi over 2, the transition probability hits exactly 100%.
Wow.
It is practically guaranteed to drop from the high state to the low state.
And when it drops, we see the beautiful conservation of energy at work. I mean, the molecule enters the box, holding that tiny chunk of high energy.
Yes.
It leaves the box in the low energy state. But that missing chunk of energy didn't just vanish. It was injected directly into the external electromagnetic field that's pulsing inside the cavity.
The molecule feeds the field. And if you have a constant stream of these purified molecules flying through, each one dumping its payload of energy, they deliver enough power to not only maintain the cavity's pulsing field, but to generate excess microwave radiation that you can draw out and actually use.
Which gives us the maser.
Right.
Microwave amplification by stimulated emission of radiation.
Yeah, that's the one.
We took a weird theoretical quirk of nitrogen jumping through a hydrogen hoop and turned it into a tangible machine that spits out a continuous beam of microwaves. The math is flawless.
The math is flawless, but the physical world is messy.
We aren't operating in a frictionless vacuum of pure theory anymore.
Exactly. When you actually build this in a lab, you run into the chaotic reality of thermodynamics. The molecules in that jet of ammonia gas aren't identical soldiers marching in perfect lockstep. They have what physicists call a Maxwell distribution of velocities.
Meaning they are all traveling at slightly different speeds. Some are zooming through the cavity and some are lagging behind.
Which completely ruins our perfect math. If they are moving at different speeds, they don't all spend that exact Goldilocks duration, that perfect time t, inside the resonant cavity. Some exit too early before the probability wave peaks. Some stay too long and actually reabsorb the energy they just released. You can never achieve 100% efficiency for the whole beam at once.
That is frustrating for an engineer, but there is an even bigger, more fatal real-world complication waiting for us. What happens if the pulsing field inside the cavity isn't perfectly tuned? What if it isn't exactly 24,000 megacycles?
If you chart the physics of this, it's figure 9 to 7 in the text, something dramatic happens. The transition probability completely falls off a cliff. It drops to 0 so quickly.
Here's where it gets really interesting. Because the sensitivity we're talking about here is almost unfathomable. The notes calculate that if an ammonia molecule is inside the cavity for just 1 millisecond, and your frequency is off by just 4 parts in 10 to the 8th power, the transition drops to 0.
4 parts in 100 million. If your cavity is detuned by that microscopic fraction, the molecules absolutely refuse to drop their energy. The maser just goes dead.
It is incredibly unforgiving. You build this brilliant machine, you sort the gas perfectly, but if your tuning dial is breathed on the wrong way, the whole thing breaks.
Yeah.
It sounds like a nightmare.
This raises an important question. Why would anyone want a machine with such a crippling limitation? How do you use something that only functions at one hyperspecific, utterly unchangeable frequency?
You use it to define time.
Precisely. Think about how we historically kept time. We used the swing of a pendulum, right? Which can be altered by temperature changes expanding the metal, or by slight variations in the Earth's gravity.
Yeah.
Or we used quartz crystals, which drift and degrade over time. All of those are macroscopic and subject to the messy environment.
But the ammonia molecule's energy gap, that exact 24,000 megacycles dictated by the quantum flip of the nitrogen atom, never ever changes. It is a fundamental constant of the universe.
So physicists realized that this extreme finickiness wasn't a bug, it was the ultimate feature. Because the maser will only operate at that exact frequency, you can use the output of the maser to constantly correct and tune your electronic oscillators. You literally lock your electronics to the unyielding rhythm of the ammonia molecule.
and that is the birth of the atomic clock. The exact same microscopic sensitivity that makes the maser so hard to build is what allows us to synchronize global GPS satellites to the nanosecond today.
Exactly.
Your phone can pinpoint your car on a map because an atomic clock somewhere is strictly keeping time to the unchangeable quantum wobble of a gas molecule.
It is the ultimate fixed point in a chaotic universe. But if we pull back, the deep dive into the source material reveals something even more profound.
Oh.
We started by looking closely at ammonia and microwaves, but the math Feynman walks us through actually holds the secret to how the entire universe interacts with light.
Right, because the maser isn't the end of the road. The text touches on variations, like the three-state maser. Instead of physically sorting the molecules with an electric gradient, you can use intense light to, pump the atoms up to a high energy level before they drop back down.
And that pumping mechanism is the foundational principle of the laser. A laser is essentially just a maser operating at optical frequencies.
Right, light amplification instead of microwave.
Yeah. Instead of a metal cavity for microwaves, you use plane mirrors to bounce visible light back and forth, stimulating the emission of more light.
But what really ties this all together is the universal formula behind it. The equation that dictates whether our ammonia molecule will drop its energy relies on three main variables.
Let's list them.
The time the molecule spends in the field, the intensity of that pulsing electric field, and that electric dipole moment we talked about earlier, which the final math formalizes as the electric dipole matrix element.
And we really need to pause and appreciate that specific term. The electric dipole matrix element, or mus squared in the equations, isn't just a quirky variable for ammonia.
No.
It is the mathematical measure of how strongly any quantum state couples to an electromagnetic field.
So what does this all mean?
It means that the formula derived for this one simple gas molecule is actually the universal quantum mechanical proof for how any atomic system absorbs or emits light.
Woo.
Decades earlier, Albert Einstein developed his theory of radiation. He figured out the macro-level statistics of how light is absorbed and emitted, creating what we call the Einstein B coefficient.
So Einstein knew that light was being absorbed and released, but he didn't have the microscopic mechanics of exactly how the atom was doing it.
Exactly. Einstein had the brilliant statistical overview, but Feynman's math here provides the actual gears inside the machine. By working through the simple two-state system of the ammonia molecule, physicists unlocked the quantum procedure for computing Einstein's coefficient.
They found the master key. It doesn't matter if you're looking at ammonia in a laboratory in New Jersey or a supergent star emitting ultraviolet radiation in the Andromeda galaxy.
Yep.
The underlying mechanics are perfectly identical. An atomic system transitions between two states separated by a specific energy gap, triggered by an oscillating field, governed by that exact same electric dipole matrix element.
It is stunning in its elegance. What started as an incredibly niche study of a single molecule's geometry expands outward to become the universal law of light and matter.
If you are listening to this right now, I really hope you can appreciate the sheer scale of the journey we just took.
It's a huge leap.
We started with a tiny nitrogen atom acting like an umbrella caught in the wind. We saw how physicists used an uneven electric tunnel to sort those molecules, throwing out the low-energy sponges.
Right.
We saw them wring the energy out in a pulsing metal box, perfectly timed like a push on a swing.
And we saw how the frustrating real-world realities of different gas speeds and hypersensitive frequencies were flipped into the greatest timekeeping mechanism in human history.
And finally, we saw how the equations running that humble microwave machine turned out to be the exact blueprints for how light functions across the cosmos. It takes quantum mechanics off the abstract chalkboard, out of the thought experiments, and places it directly into the beating heart of reality.
It forces you to realize that the physical world you interact with every day is just the macro expression of these bizarre, invisible quantum rules.
Which leaves you with a pretty wild thought to mull over. If scientists could take the predictable microscopic wobble of ammonia and use it to redefine how humanity measures time and navigate the globe, what other strange hidden quantum rhythms are happening right now? Look around the room you are in. What invisible atomic dances are happening in the materials on your desk or even inside your own body, just waiting for someone to figure out how to harness them for the next world-changing technology? Keep wondering about that. We will see you on the next deep dive. Welcome to today's deep dive into the source material. We're going straight to the good stuff today. We're pulling from a really fascinating collection of notes and text from Chapter 10 of Volume 3 of the legendary Feynman Lectures on Physics.
Oh, yeah. It is such a classic, rich piece of text to dig into.
It really is. And our mission for this deep dive is to show you how nature's simplest possible trick, which is basically just a system jumping back and forth between two distinct states, is actually the secret glue holding the entire universe together.
Which is a huge claim, I know.
Right, because, usually when we look around the physical world, we expect solidity. You look at a wooden table or a glass of water or even your own hand, and it really feels like reality is made of tiny, static Lego bricks just snapped tightly together.
Yeah, we find a lot of comfort in that idea. I mean, the human brain evolved to interact with a universe that feels solidly bolted together.
Obviously.
But when we look at the underlying structural landscape presented in these lectures, well, those bolts kind of vanish. The reality at the bottom is entirely dynamic. It's all moving.
Exactly. We live in a world of just overwhelming complexity, with millions of variables interacting every single second. But by spotting these fundamental binary patterns, what physicists call a two-state system, we can suddenly start to read the underlying code.
Which is wild to think about.
It is. By mathematically pretending a complex system has, only two main choices, we can understand everything from the really rigid rules of quantum mechanics to the everyday chemistry that gives, your clothes their bright colors.
So let's jump right into it. Let's start with the absolute bare minimum required to make a piece of reality actually stick together. We are looking at the simplest molecule imaginable, which is the hydrogen molecular ion.
Right. Written out as H2+.
Exactly. So picture this in your mind. You have two positively charged protons and a single solitary electron just kind of buzzing around them in a cloud of probability.
And if those two protons are separated by a really large distance, the base states of this system are very straightforward. The electron's either going to form a cloud around proton A,
which we can call state 1. Right. Or it's going to form a cloud around proton B, which is state 2. Now, in classical physics, an electron in that situation is completely trapped.
because of the energy barrier, right?
Yes, exactly. To pull an electron away from a single proton requires a pretty massive amount of energy for a subatomic particle. It's about 13.6 electron volts.
So classically speaking, the electron shouldn't be able to cross the empty space between the two protons unless you physically pump, 13.6 electron volt into the system to rip it free. It's basically trapped in a deep well.
But quantum mechanics completely changes the rules here. The electron doesn't actually need to climb the wall of that well. It can just tunnel right through it.
It just bypasses the wall entirely.
Exactly. There is a mathematical amplitude. The source material simply labels it as A for the electron to literally bypass that empty space and instantly flip-flop back and forth between state 1 and state 2.
Okay, let's unpack this for a second. I want to give a visual. It's like two kids standing 100 yards apart on a field, right?
Correct.
Just throwing a single baseball back and forth.
That's a great way to picture it.
But wait, that creates a massive logical problem. If those two kids represent positively charged protons, they naturally repel each other with extreme force.
Right. Positive repels positive.
So throwing a single baseball back and forth shouldn't really stop them from flying apart. How does this quantum flip-flop actually act like glue?
Well, the secret lies in the Heisenberg uncertainty principle.
Oh, okay.
And we often think of the uncertainty principle as just a rule about measurement, right? Like that you can't know a particle's exact position and momentum at the same time.
Yeah, that's how it's usually taught in school.
But it has very real physical consequences. When an electron is stuck to a single proton, it's confined to a really small space. And because its position is so tightly constrained,
Its momentum has to go crazy.
yes, its momentum, and therefore its kinetic energy, has to be highly uncertain and extremely energetic. It's buzzing around violently just to stay in that tiny space.
Okay, so it's like a hyperactive dog trapped in a tiny crate. It's just going to be bouncing off the walls, expending a ton of energy.
Exactly. But the moment you bring a second proton nearby, you offer that electron a second crate.
Oh, wow.
By tunneling back and forth between the two protons, the electron effectively expands the total volume of space it occupies.
So it has more room to breathe, basically.
Exactly. It's no longer violently confined. Because its position is spread out over a much larger area now, its momentum can actually settle down. The kinetic energy of the entire system drops significantly.
And since physical systems always naturally seek the lowest possible energy state, the universe naturally favors this arrangement.
Spot on. The flip-flopping creates a brand new, lower energy stationary state. At large distances, the electrostatic repulsion between the two protons still totally dominates, but as you bring them closer...
The tunneling kicks in.
Right, this tunneling amplitude gets stronger and stronger. The electron spends more time spread out, which pulls the total energy down, creating an attractive force. And at a very specific microscopic distance, this attractive quantum force perfectly balances out the static repulsion. They hit an equilibrium point.
And that equilibrium point is what we literally call a chemical bond.
Yes, a one-electron bond.
Which is so wild because the electron isn't acting like a physical piece of tape holding the protons together. The movement itself, like the mere possibility of the exchange, is the binding force.
The dynamic exchange is the bond.
So, okay, this flip-flop works perfectly for one single electron. But nature rarely gives us just one. What happens when a second electron crashes this delicate two-state party?
That's where things get really interesting.
Right, so let's upgrade to a normal everyday hydrogen molecule, just your basic H2. We have two protons, and now we throw a second electron into the mix. We have this symmetrical dance now. Electron A is with proton 1 and electron B is with proton 2, and then they completely swap places.
And that basic setup creates an even stronger binding force. They flip-flop just like before, but now the amplitude of that double exchange pulls the system into an even deeper well of stability.
But wait, here's where I have to push back a bit, because the strict mathematical rules of quantum mechanics say that no two identical electrons can occupy the exact same quantum state, like they are Fermi particles.
Yes, they are.
And if they're perfectly identical, the math actually interferes with a negative sign. The probability amplitude basically reverses and cancels out entirely.
That is exactly what the math says.
Doesn't adding a second electron completely break this beautiful two-state flip-flop game then? Because if the math cancels out, the atoms should just repel each other, and the bond shouldn't exist at all.
What's fascinating here is that this is where the concept of spin becomes the crucial workaround.
Okay, spin.
Right. If both of those electrons are spinning in the same direction, say they both have a quantum spin pointing up, then the lower energy symmetrical state we just described is strictly forbidden.
Because of the Pauli exclusion principle.
Exactly. The Pauli exclusion principle takes over. If you try to force them into that state, the amplitudes cancel, the energy spikes, and the atoms aggressively push each other away, no molecule forms.
So if they spin the same way, the universe just flat out refuses to let them share the space.
Refuses. To form the bond, which, we should note, is the fundamental mechanism holding the proteins and water molecules in your own body together right now, the two electrons absolutely must have opposite spins, one spin up, one spin down.
Okay, I want to clarify something here, because it's so easy to just visualize two magnets snapping together. Are they forced to be opposite because they're acting like tiny magnetic poles attracting each other?
Actually, no, and that's a very common misconception. It is entirely separate from magnetic forces.
Oh, really?
Yeah, the magnetic interaction between the electrons is incredibly weak. They are forced into this anti-parallel condition solely because of the quantum exclusion principle. By having different spins, they are no longer completely identical in their quantum state.
Oh, so it's just a loophole to not be identical.
Exactly, it's a quantum loophole. Only then does the universe allow them to share that lowest energy flip-flop state. And when they do, at a separation of about 0.74 angstroms, which is a tiny, tiny fraction of a nanometer, they find perfect chemical harmony. It is literally the most common valence bond in all of chemistry.
That is amazing. So if exchanging a lightweight electron gives us the chemistry of our bodies, what happens if we swap something heavier? Can we apply this exact same flip-flop logic to other forces in the universe?
Oh, absolutely.
Because, say I swap a tennis ball back and forth, and that represents chemistry. What if I swap a bowling ball? Does that make a different force?
It does. And scaling this up leads to one of the most profound realizations in modern physics. This was first proposed by Hideki Yukawa. He realized that the insanely strong nuclear forces, like the forces holding the actual nucleus of an atom together against the massive repulsion of all those tightly packed protons.
Which should blow themselves apart.
Right, they should, but they're playing the exact same two-state game.
But wait, protons and neutrons inside a nucleus aren't exchanging electrons, right?
No, they are exchanging a much heavier subatomic particle called a pion, or pi meson. Inside the nucleus, a proton can literally emit a positively charged pion. And the moment it loses that positive charge, the proton physically becomes a neutron.
Wait. They're swapping actual identities.
Yes. The proton becomes a neutron, and the neighboring neutron that catches the positive pion instantly becomes a proton.
That is mind-blowing.
They are flipping identities back and forth at just incomprehensible speeds. And the mathematical equation for the amplitude of this exchange, which creates what physicists call the Yukawa potential, is completely, perfectly analogous to the math of our single electron jumping between two protons.
So it's the exact same equation, just with a heavier ball.
The exact same.
And a heavier ball means a shorter range, I'm guessing?
Exactly. Because the pion has significant mass, the force only operates over incredibly short distances, confined strictly to the inside of the nucleus. But the underlying mechanism is identical. You can even apply this to the Coulomb force.
Like basic static electricity.
Yeah, like the shock you get from a doorknob. That force is transmitted by electrons exchanging virtual photons. So whether you are looking at organic chemistry or the static electricity in a balloon or the literal nuclear physics powering the sun.
They call the same game.
All these wildly different physical phenomena are just the universe playing the exact same two-state quantum game with different particles.
That completely reframes how you look at the fundamental forces.
Yeah. Okay, let's bring this down from the invisible subatomic space to the macro world, to things you can actually see and touch in your daily life. Because the source material spends a lot of time on organic chemistry, specifically benzene.
Right, benzene. So the chemical formula is C6H6. Benzene has a ring of 6 carbon atoms, and they are sharing a total of 30 electrons to hold the ring together. Now, chemists traditionally draw this ring with alternating single and double bonds.
Right, it's that familiar hexagon diagram where every other side of the hexagon has an extra line indicating a double bond.
Yeah, exactly. But here is the classic mystery. If you take that benzene ring and you replace 2 of the hydrogen atoms with bromine atoms, which makes a chemical called orthodibromo-benzene, you would logically expect to find 2 totally different versions of this chemical in reality.
Because of the alternating bonds.
Right, because those 2 bromines could either be separated by a single bond in the ring or by a double bond, depending on exactly where they attached.
But when you actually synthesize it in a lab and observe it, there is only one version of the molecule. There aren't 2.
So what does this all mean? How does the two-state system solve this? Did the early chemists just draw the picture wrong?
Well, they eventually discovered that the entire benzene ring is, itself, a massive two-state system.
The whole ring.
The whole thing. The cloud of electrons isn't sitting still in static single and double bonds. The arrangement is entirely fluid. The whole structure is simultaneously flipping back and forth between the 2 different bond configurations.
So the entire carbon ring is just oscillating back and forth.
Yeah, and because electrons are so light, this structural flip rate is incredibly fast. This hyperfast oscillation creates a massive energy gap between the 2 states. It's about 3 electron volts.
Which is huge.
It is. That massive gap acts as stabilization energy. It's the reason the benzene ring is notoriously tough to break apart chemically.
And a gap of 3 electron volts happens to fall right in the range where it interacts with ultraviolet light.
Exactly.
Which brings us to something highly visible, which is dyes. We just talked about benzene absorbing UV light, which obviously we can't see. But let's look at a bright dye, like the color magenta, which you see in dry clothing or printer ink all the time.
Right, a very intense color.
Magenta is a massive, complex molecule made of multiple rings, but it has a very asymmetrical electric charge.
And just like benzene, the magenta molecule has 2 base states it can rapidly flip between. But because of its asymmetrical structure, when the electrons flip-flop in magenta, the entire center of electric charge drastically shifts from one side of the giant molecule to the other.
So the molecule's center of gravity is violently throwing its weight from side to side.
Yes.
It creates like a giant electromagnetic paddle that just swats at incoming light.
That massive shifting of electric charge interacts powerfully with external electric fields. Specifically, the oscillating electric fields of incoming visible light.
Oh, I see.
As it throws its weight back and forth, it absorbs very specific optical frequencies of light to fuel that transition.
And the light it doesn't absorb is what bounces back to your eye.
Exactly.
That is literally why the brightly colored clothes in your closet have color. It's billions of dye molecules playing microscopic ping pong with their charge.
It's beautiful when you think about it.
And the source material points out that if you tweak the molecule, if you change a couple of hydrogen atoms on the edge of the dye to a slightly heavier CH3 group, you change the mass of the molecule.
And altering the mass changes the flip-flop rate.
which changes the energy gap, which shifts the frequency of light it absorbs, giving you a totally different color. You go from bright magenta to malachite green just by slightly weighing down the paddles.
It perfectly illustrates how sensitive the visual world around us is to this underlying quantum math.
It really does. So we've covered everything from the nuclear force holding atoms together to the bright magenta dyes in our clothes. But reading through the final sections of the source material, Feynman drops just a massive punchline here.
He does.
He says there is a master skeleton key to solve all of these two-state problems at once.
And the elegance of this final synthesis is just incredible. The lectures show that if you write out the Hamiltonian, which is simply the master equation governing the total energy of a system, for a single lonely electron spinning in a magnetic field, you get a set of mathematical equations that describe the electron's spin precessing.
Precessing. Wait, so like a toy top wobbling as it spins on a table?
Exactly like a wobbling top. The spin axis rotates around the invisible magnetic field lines at a very specific, measurable frequency, and the math required to track that wobbling is purely geometric. You are just tracking the changing angles of the top.
Okay, I understand a wobbling top. That's easy to visualize. But how does the geometry of an electron wobbling in a magnetic field help me calculate the color of a dye molecule or the exact strength of a hydrogen bond?
This is the genius of it. Every single two-state system in the universe can be mathematically mapped onto that exact same geometric model.
Really? Every single one?
Everyone. You take your complex chemistry problem about an ammonia molecule or a benzene ring, and you just pretend it's a single electron spinning in a magnetic field.
But how do you map a chemistry problem onto a fake magnetic field?
It's simpler than it sounds. You set the average energy of your two chemical states to 0. Then you take the energy difference between state 1 and state 2, and you map that value onto the z-axis of your imaginary magnetic field.
Okay.
Next, you take the amplitude of the flip-flop, basically the speed of the exchange, and you map that value onto the x-axis.
Wait, so you've just turned energy levels and jump rates into physical coordinates on a graph?
Yes. Once you do that, solving the complex quantum chemistry problem becomes an exercise in simple geometry. The rate at which your theoretical top wobbles around this fake magnetic field gives you the exact energy states and transition rates of the actual molecule.
That is unreal.
If you can solve the geometric problem of tracking a spinning top, you have automatically solved every two-state problem in physics and chemistry.
You literally turn abstract quantum algebra into a pure three-dimensional geometric shape.
You do.
Let's bring all of this together, because what an incredible journey through this source material. We started with a single tiny electron hopping between two protons. And we discovered that the mere possibility of that jump just spreading out to lower its kinetic energy is the actual glue of a chemical bond.
Right.
We found out that this exact same identity swapping mechanism, just using a heavier pion, is what holds the atomic nucleus together against impossible odds. We saw that the rapid-fire flip-flopping of an entire electron cloud is the reason benzene is chemically stable. And it's the reason the giant asymmetric molecules in our clothes absorb light and give us brilliant shifting colors.
And most incredibly, we realized that all of this chaotic, messy reality boils down to the exact same geometric math of a single wobbling top. I would really encourage you, wherever you are right now listening to this, to just look around your room.
Yeah, look around.
The colors you see on your wall, the solid objects you're touching, the very DNA coiled up inside your own cells, it all feels so static and solid, but is actually being actively held together, right this second, by a microscopic, high-speed game of quantum flip-flop.
It completely shatters the illusion of the static Lego bricks we started with.
Completely shatters it.
And it leaves us with a final, really profound thought to ponder. If the chemical bonds holding your body together, and the nuclear forces holding the sun together, and the interaction of light and color can all be perfectly translated into the exact same purely geometric math of a wobbling axis,
Yeah.
is the physical universe actually made of solid stuff? Or is reality ultimately just pure abstract geometry interacting with itself?
That is the ultimate question physicists are still wrestling with today. I mean, the deeper we go, the more the material world just dissolves into pure mathematics. Thank you so much for joining us as we explored these foundational concepts from the lectures.
We'll catch you on the next deep dive. Imagine throwing a baseball and halfway to home plate, it just spontaneously turns into a tennis ball.
Right.
Then, just before it hits the catcher's mitt, it morphs right back into a baseball. I mean, in our everyday world, that sounds like a glitch in the Matrix, right? or some kind of weird street math.
No, absolutely. It sounds impossible.
But, in the quantum world, this kind of mid-air shapeshifting isn't magic at all. It's actually just math. So today, we're taking a deep dive into how quantum physicists use this incredibly simple concept, a two-choice math system, to unlock some of the most profound mysteries of the universe.
Yeah, and it's a completely fascinating topic to dig into.
We're going to explore how a single, elegant logical framework unites everything from the way your polarized sunglasses work at the beach all the way to particles that suffer literal identity crises as they fly through space. So, okay, let's unpack this. Because while quantum mechanics sounds deeply intimidating, at its core, it's really just a story about how nature makes choices.
Exactly. It is a story of choices, and the underlying logic is surprisingly consistent. What we're exploring today with this deep dive is a shift in perspective.
A shift in perspective. I like that.
Right, because by the end of this conversation, you'll see that the strange behavior of exotic particles isn't just, random quantum weirdness. It is the direct, unavoidable result of a very specific set of rules.
Right. Rules that kind of dictate everything.
Yes, and the beauty of these rules is that once you understand how they govern a simple two-state system, you suddenly possess the key to understanding the hidden architecture beneath the world you interact with every single day.
I really love that idea of a hidden architecture. So let's start right at the foundation, because before we can get to particle swapping identities, we need to understand the engine driving those choices, right?
We do. We need the basics.
And in quantum physics, one of the most classic examples of a two-state system is a particle, like, say, an electron, sitting in a magnetic field. According to the quantum rules, its spin, which you can kind of think of as its internal compass, doesn't have infinite directions it can point.
No, it's highly restricted.
Right. It only has two options. It can point spin up or spin down. That is it. Just two states.
The restricted nature of those choices is exactly what makes it a two-state system. And because it is so wonderfully constrained, physicists needed a clean, compact way to write down the equations describing how this electron behaves when you apply different magnetic fields to it.
Because you don't want to reinvent the math every single time you rotate the magnet.
Right.
That sounds exhausting.
Exactly. It would be a nightmare. So this necessity both what we call the polyspin matrices.
The polyspin matrices.
Yes. Think of them as a sort of mathematical shorthand. They are essentially little grids of numbers, and there's one grid dedicated to the x-axis, one for the y-axis, and one for the z-axis.
Right. And instead of getting bogged down and writing out massive complex equations for every possible angle, you just plug in these little grids.
Precisely. And these grids allow physicists to calculate the total energy of the system. There is an equation for this called the Hamiltonian.
Oh, the Hamiltonian.
Yeah.
Now, I'm not going to read out a string of Greek letters and math variables to you, but conceptually, you can picture this Hamiltonian equation as a cosmic balancing scale.
That's a great way to visualize it.
Right. On one side, you input the strength and direction of your magnetic field, and then on the other side, you input these polygrids representing the particle's spin, and then the equation basically crunches those inputs together and spits out the exact energy state of the particle.
That is a highly accurate way to put it. The Hamiltonian is the ultimate ledger. It tells you how the state of your particle will evolve over time based on that energy.
The ledger of the universe.
Yes. Now, what really stands out when you look at this quantum equation is how eerily similar it looks to the classical physics equation for a simple magnet.
Oh, really? Like they look the same?
Structurally speaking, almost identical. Classically, the energy of a magnet is just its magnetic strength multiplied by the magnetic field it's sitting in. The quantum version just swaps in those rigid two-choice polygrids instead of the smooth, continuous properties of a classical magnet.
Okay, wait, hold on. This is where I have to push back a little because this brings up a massive philosophical question for me.
Go for it.
If the classical equation and the quantum equation look so incredibly similar, why do we treat them like totally different worlds?
Yeah.
We all learned classical physics first, right? Apples falling from trees, magnets pulling iron filings.
Right, the everyday stuff.
Yeah. So if the equations match up, doesn't that imply quantum mechanics is just a logical, maybe slightly more complex extension of classical physics? Like, why can't we just build up the quantum rules from the classical stuff we already know and are comfortable with?
It is a very tempting assumption, and frankly, it's one that frustrates a lot of first-year physics students, but working from classical up to quantum is a trap.
A trap? Really?
Yes. To understand why, imagine a three-dimensional object, let's say a solid cylinder. If you shine a light on it from the top, the shadow it casts on the floor is a perfect circle.
Right. Okay. But picturing it.
But if you shine a light on it from the side, its shadow on the wall is a rectangle.
Right. Same exact object, totally different shapes depending on the angle of the light.
Precisely. Now imagine you are a two-dimensional being who only lives on the wall. All you ever see, your entire reality, is the rectangle.
Oh, wow.
You could study that rectangle for centuries, you could measure its corners, write laws of physics about it, but from that two-dimensional shadow, you could never, ever logically deduce the three-dimensional cylinder. You wouldn't even have the vocabulary for depth.
That is mind-bending.
Yeah.
So we're the beings on the wall.
In this analogy, yes. Nature inherently operates in the deep, complex reality of quantum mechanics. The classical world of apples and magnets that we observe every day. That is just the flat, two-dimensional shadow cast by the quantum world.
That is such a wild way to look at reality. So when the quantum equations happen to look like the classical ones, we shouldn't think, oh, quantum is acting classical. We should think, oh, we are just looking at the shadow of the quantum truth.
Exactly. We were just lucky that the shadow resembles the object in that specific instance. But we always have to accept the quantum formula as the fundamental ground truth. You simply cannot reconstruct the universe from the shadow up.
Okay, let's take this abstract idea of the shadow and apply it to something we can actually see and touch. Because otherwise, my head's going to spin.
Let's do it.
Something you, the listener, probably interacted with this morning, actually light. Because a single photon of light is another perfect example of this two-state system.
It is. Light is a brilliant way to see this math in action. When we talk about the polarization of a single photon, we are essentially talking about the direction its electric field is vibrating.
Okay.
And we can define any photon's polarization using two base states. It can be polarized horizontally, let's call that the x direction, or vertically the a direction.
So let's bring this to life for everyone listening. Imagine you are at the beach, and the sun is just glaring off the ocean. So you put on your polarized sunglasses.
A classic scenario.
Classically, we think of light as a smooth, continuous wave, right? So when that wave of glare hits the polarized lens of your sunglasses, the classical view says the wave just gets squeezed. It gets weaker.
Right, it dims.
Yeah. If your sunglasses are tilted at an angle, the classical math says the energy of the light beam dims by a very specific mathematical factor related to that angle. You turn the dimmer switch down, and the world looks a little darker. But the quantum reality is totally different, isn't it?
It is a fundamentally different mechanism. In the quantum view, that beam of sunlight is not a smooth wave at all. It is a barrage of billions and billions of individual, indivisible packets of energy photons.
Indivisible. Like, you can't break them apart.
Exactly. And here's the crucial rule. You cannot slice a single photon into pieces. A photon cannot be dimmed. When a single photon hits the lens of your sunglasses, it faces a binary choice. It either passes all the way through completely intact, or it gets completely absorbed by the lens and turns into a tiny bit of heat.
But wait. If a photon can't be sliced or dimmed, how does it end up matching that classical dimming rule we just talked about?
Through the sheer power of statistics and probability. If you send one single photon at a tilted polarized lens, it doesn't get partially blocked. Instead, the angle of the lens determines the probability that the photon makes it through.
So it's all about odds.
Right. Let's say the angle creates a 75% probability of passing. That single photon essentially rolls a quantum die. But when you are at the beach, you aren't dealing with one photon. You are dealing with trillions of them.
Okay, I love this. So quantum mechanically, your sunglasses aren't a dimmer switch at all. They're acting like a ruthless bouncer at an exclusive club.
A bouncer? I like that.
Every single photon of sunlight steps up to the velvet rope, and the bouncer rolls invisible dice for every single one. You pass, you absorb, you pass.
That is exactly what is happening.
Because there are trillions of photons, the math smooths out.
Right.
75% make it into the club, 25% don't. To your human eye, the overall effect looks like a smooth dimming of the light. But at the microscopic level, there's no smooth wave. It's just a frantic series of trillions of binary two-state choices happening every millisecond.
That bouncer analogy perfectly captures the transition from the quantum probability to the classical shadow. The bouncer is strictly enforcing the rules of a two-state system.
There is one part of this light behavior from the source material that completely baked my noodle, though.
Oh, which part?
We said the two base states are horizontal and vertical. But physicists have another way to describe light circular polarization. Instead of vibrating strictly up and down or left to right, a photon can be right circularly polarized or left circularly polarized. You can kind of picture it like a corkscrew of energy spiraling through space.
Yes, and what's fascinating here is that circular polarization is completely independent of your choice of horizontal or vertical axes.
Independent, meaning it doesn't care.
Right. A right-spinning corkscrew is still a right-spinning corkscrew even if you tilt your head or rotate your entire coordinate system.
Exactly. And this is where my brain just hit a wall.
Hmm.
If right and left circular polarization don't care at all about the horizontal x-axis or the vertical y-axis, how is it possible that if you combine a right polarized photon and a left polarized photon, they miraculously reconstruct a perfectly horizontal x-polarized photon?
It seems like magic, doesn't it?
Where did the geometry come from if neither of the ingredients knew about the horizontal axis to begin with?
It completely feels like a paradox. The secret here lies in how quantum mechanics stores hidden information, specifically through a concept called phase.
Phase, okay.
To visualize phase, let's step away from light for a second and imagine a circular running track.
Okay, I'm at the track, got my running shoes on.
You have two runners. One runner goes clockwise, representing right circular polarization. The other runs counterclockwise, representing left circular polarization. They run at the exact same speed.
Got it. Clockwise and counterclockwise.
Now, if they start at the exact same time from the starting line, they will always meet and cross paths at that same starting line, and then again at the halfway mark on the opposite side of the track.
Makes sense.
If you draw a straight line between those two meeting points, you get a perfectly horizontal line across the track. That horizontal line is your x-polarization.
Oh, wow. Okay, so the combination of their movements creates the horizontal geometry. The line connecting where they crash into each other.
Yeah.
But what about the vertical U polarization? How do we get that?
To get the vertical U polarization, you don't change the runners, and you don't change their speed. You change their timing.
Their timing.
Right. You delay one runner. Let's say you make the clockwise runner wait a fraction of a second, like a quarter of a lap before they start running. Now, because their timing is shifted, they won't meet at the starting line anymore. They will meet at the top and bottom of the track.
But let's see where this is going.
Yes, if you draw a line between those new meeting points, you get a perfectly vertical line, the axis.
That is incredible.
Yeah.
So the phase is just the relative timing between the two states.
Yeah.
The right and left states themselves don't carry a map of the axes, but the delay between them acts as this hidden memory of the geometry.
The timing dictates the geometry. It's a beautifully elegant solution, and it perfectly demonstrates how flexible this two-state math really is.
Well, if you think the timing of a photon is weird, we are about to take this exact same two-state logic and apply it to something far more bizarre. We are officially leaving the beach, and we're heading to a high-energy particle accelerator in the 1950s.
Yes, we are entering the domain of the K-meson. But to really appreciate the sheer weirdness of the K-meson, we need to quickly establish the environment it lives in.
Right, the nuclear neighborhood.
Exactly. In nuclear physics, particles interact through different fundamental forces. The two we care about right now are the strong interaction and the weak interaction.
And these are pretty aptly named, aren't they? Strong interactions are really fast and violent. Like when particles smash into each other at high speeds, the strong force takes over and instantly produces this spray of new exotic particles.
Yes, almost instantaneous.
And then the weak interaction is basically the opposite. It governs how particles slowly fall apart or decay over time. It operates on a completely different, much slower timescale.
That timescale difference is absolutely key. Back in the 1950s, physicists were using early particle accelerators to smash protons and pions together, utilizing that fast, violent, strong interaction. But they ran into a glaring mystery.
A mystery.
The math of the time predicted that certain particles should be created in these collisions, but the detectors were coming up empty. Nature was simply refusing to make them.
They're kind of like trying to bake a cake with all the right ingredients, but the oven just straight up refuses to bake it.
That's a good way to look at it. To solve this mystery, two brilliant physicists, Murray Gell-Mann and Kazuhiko Nishijima, did something truly audacious. They realized that if nature wasn't allowing these particles to form, there must be an invisible rule, a hidden ledger that was stopping it.
The bouncer again.
Yes. So they invented a brand new property of matter, just like mass or electric charge, and they called it strangeness.
Strangeness. I genuinely love that physicists, when faced with the unknown, just lean into the absurdity and call it strangeness.
It was certainly strange at the time. They essentially assigned a strangeness score to every subatomic particle. Common particles, like protons and neutrons, got a strangeness score of 0.
Normal stuff is 0.
Right. But the newly discovered exotic particles got a score of +1 or -1, and Gell-Mann proposed a strict new law of physics. In any fast, strong interaction, the total strangeness of the universe must be conserved.
Conserved. Like energy.
Exactly. It is an unbreakable cosmic accounting rule. Whatever strangeness score you start with before the collision, you must end with after the collision.
So let's trace one of these collisions to see how the accounting works. Let's say you take a negatively charged pion, a particle with 0 strangeness. You smash it into a proton, which also has 0 strangeness. 0 plus 0 is 0.
Simple enough.
The total strangeness going into the crash is 0. Out of the debris of that violent collision, 2 new particles emerge. A lambda particle, which Gell-Mann assigned a strangeness of -1, and a neutral K-meson, the K0, which has a strangeness of +1. -1 plus 1 equals 0. The books balance perfectly.
The books balance, so nature allows the interaction to happen. Now, let's look at the antimatter version of the K-meson, the anti-K0. It has a strangeness of -1.
-1, okay.
This completely changes how it interacts with the world. Because of these strict accounting rules, an anti-K0 can crash into a proton and successfully create a lambda particle. The math works out. But a regular K0, with its +1 strangeness, cannot. It is physically forbidden from creating a lambda particle by the law of conservation of strangeness.
Okay, so the K0 and the anti-K0 have totally different identities. They have totally different capabilities in a collision. But here comes the twist. We've been talking about the fast, violent, strong interactions. What about the weak interactions? The slow decays?
Ah. This is where the universe pulls a fast one on us. It turns out the weak interaction does not care about the strangeness ledger. It ignores it completely.
It bypasses the bouncer.
It totally ignores the bouncer. When particles are left alone to slowly decay via the weak force, strangeness is not conserved. And because of this loophole, both the K0 and the anti-K0 eventually decay into the exact same end product 2 pions.
Wait, hold on, let me process this. If the K0 decays into 2 pions, and the anti-K0 also decays into 2 pions.
Yes.
Okay, let's unpack this. Doesn't that mean they are fundamentally connected? I mean, if they share the exact same doorway out of the universe, what stops them from crossing over into each other's lanes?
That is the exact question that led to a Nobel Prize. Because they share that decay path, quantum mechanics dictates that there is a probability for them to transition into one another. They are not isolated, independent particles. They are intrinsically linked by this weak decay doorway, forming a coupled two-state system. Sound familiar?
It's the exact same underlying math as the electron spin or the polarized light. Okay, so this brings us to the climax of the deep dive. What happens when you apply our trusty two-state math to these interconnected K-mesons?
You get a prediction that completely defies common sense. Gell-Mann and his colleague Abraham Pace analyzed this two-state system. Using the math, they realized that the pure K0 and pure anti-K0 weren't the true foundational states.
Wait, they weren't.
No, the math naturally defined 2 new combined states, which they called K1 and K2.
Okay, K1 and K2.
The K1 state decays very rapidly into 2 pions. It survives for about a 10/1000th of a second. The K2 state is a different mixture, and it decays much slower into 3 pions, lasting about 600 times longer.
Okay, I want you to picture this experiment in your head. Physicists fire up a bubble chamber, which is basically a vat of liquid hydrogen used to track particle paths. A collision happens, and a brand new, pure K0 is born. It starts flying through the hydrogen. At the exact millisecond of its birth, according to this new math, it isn't just a K0.
No, it's not.
It is a perfectly balanced 50-50 superposition of a K1 state and a K2 state.
Correct. It is both states simultaneously. But remember the lifespans. As the particle flies forward, the K1 part of its identity is incredibly unstable. It decays and vanishes almost immediately. But the K2 part of its identity is robust. It persists and continues flying.
And here's where it gets really interesting. Because one part of its internal mixture dies away while the other survives, the balance of the particle shifts. The quantum interference between the two states constantly morphs as time ticks by.
The math practically demands an oscillation.
So as this particle toots along through the bubble chamber, If you were to test it at different points along its path, the probability of it acting like an anti-K0, meaning the probability of it being able to smash into a proton and produce a lambda particle, wobbles.
Yes, it oscillates.
It goes up and down in a wavy pattern over time. It's exactly like my baseball analogy from the beginning of the episode.
Yeah.
You throw a K0, but halfway down the chamber, the probability shifts, and it essentially becomes an anti-K0. Then it shifts back. It is literally shape-shifting its fundamental identity in midair.
And we really must pause to appreciate the magnitude of this achievement. Gell-Mann and Pace didn't have microscopes powerful enough to see the inner gears of the K particle. Nobody did. They had no physical mechanism to explain how it was doing this.
It was all on paper.
Exactly. By ruthlessly trusting the foundational logic of the two-state system, they successfully predicted the existence of a shape-shifting particle before anyone had ever actually observed that oscillation in a lab. It was a triumph of pure theoretical deduction.
It gives me chills, honestly, just thinking about it. But this raises a huge question. We spent this whole time talking about two-state systems. Spin up, spin down, right, left, K0, anti-K0. If just two choices can create a particle that swaps matter and antimatter identities as it flies, what happens when we zoom out?
What do you mean?
Well, the universe isn't just made of two states, right? What happens when you have millions of states?
The real power of this framework is that it scales. The math that governs the shape-shifting K-meson scales up to what we call an n-state system, where n can be any number. Thousands, millions, billions.
Just massive amounts of choices.
Exactly. When you add more states, you simply use larger grids of numbers, larger matrices.
Yeah.
By running this matrix algebra, physicists calculate what are called eigenstates. You can think of an eigenstate like the resonant frequency of a guitar string. It's a stable, stationary mode where the system finds a definite, distinct energy.
Oh, wow. So whether you are calculating the two states of a photon hitting your sunglasses at the beach, or the billions of states interacting inside a complex molecule, you're essentially turning the exact same mathematical crank.
Exactly. You are just using a larger ledger. This matrix algebra is the fundamental arithmetic of the quantum world. By finding the roots of these complex equations, we decode the stable architecture of everything around us. As long as the energies are different, these states remain orthogonal, distinct, and independent.
Let's take a breath and look at the journey we just went on. We started with the realization that the classical world of falling apples and magnets is just a two-dimensional shadow cast by a deeper quantum truth.
A huge paradigm shift.
Right. And then we learned how to read that truth using simple grids of numbers. We saw how those numbers explain the hidden phase and timing of polarized light. And finally, we saw how trusting that exact same logic unlocked the mystery of a particle that alters its own identity on the fly. It really goes to show that if you take the time to understand just a few foundational rules of nature, you hold the keys to the entire castle.
It is a profound realization, but I want to leave you, the listener, with a slightly unsettling thought to mull over. We've seen today that at the deepest, most fundamental level of reality, particles do not possess a single, fixed, permanent identity.
They really don't.
Their nature is inherently probabilistic, a shifting superposition of multiple states. Now consider that you, your home, and the device you are listening to this on are built entirely out of these shifting, uncertain particles.
Oh, man.
So what does that imply about the complex, seemingly solid, unshakable world you interact with every day? The next time you look at your own reflection in a mirror, ask yourself, are you really seeing the true nature of reality? Or are you just looking at the classical shadow of a deeply quantum universe?
Right now, radio telescopes all over the world are tuned to this highly specific, really faint hum. It's exactly 1,420 megahertz.
Yeah, which is just the sound of atomic hydrogen gas floating out there in the freezing void between stars.
Right. But, to understand how astronomers actually use that exact number to track the spiral motion of our whole galaxy, we have to look inside the absolute smallest, quietest room in the universe.
And the sources for today's deep dive materials from a pretty renowned physics lecture series on quantum mechanics, specifically Chapter 12, take us straight into that room.
Yeah.
We're looking intimately at the ground state of a single hydrogen atom.
Okay, let's unpack this.
Okay.
Because, we all know the classical model of the hydrogen ground state, right? Like from high school chemistry.
Right, the absolute basics.
Yeah, one proton, one electron, sitting at the lowest possible energy level. It's usually taught as this single, indivisible baseline, like the absolute bottom floor of the atom.
Foundation, yeah.
But when you look closely at the quantum mechanics, that quote-unquote single ground state actually fractures. It breaks into this microscopic architecture of 4 distinct substates.
It totally does. And the mechanism driving that fracture is something called hyperfine splitting.
Hyperfine splitting.
Yeah, it happens because both the electron and the proton have this intrinsic quantum property called spin. You can sort of visualize them as tiny, unimaginably weak bar magnets that can point either up or down.
So because you have 2 particles,
Right.
and each can be either up or down, the math just dictates 4 possible base states, right?
Exactly.
Both spins up, both spins down, electron up while proton is down, and vice versa. But what always strikes me when looking at these sources is the sheer scale of the energy we're talking about here.
Oh, the scale is wild.
Right. Because if an atom wants to jump from this ground state to the very first excited state, it takes about 10 electron volts of energy.
Which, I mean, is a massive leap on the atomic scale. It's huge.
It is. But the energy shifts between our 4 microscopic spin states down here in the ground state. We're talking about differences of, like, maybe 10 millionths of an electron volt. It's a ratio of 1,000,000 to 1.
Yeah. And that scale difference is everything. It's the entire reason physicists can treat the ground state as its own isolated, mathematically closed universe.
How so?
Well, imagine you're studying the tiny millimeter-high ripples across the surface of a puddle. You don't need to factor in the gravitational pull of the moon causing ocean tides just to understand those ripples, right?
Oh, I see.
The 10-electron volt jump to the next energy level is the ocean tide. The hyperfine splitting is the ripple. Because the gap to the next energy tier is so astronomically huge compared to these 10 millionth of an electron volt shifts, we can just completely ignore higher energies.
We just lock ourselves in the basement.
Exactly. We define these 4 spin states as our base states, our unit vectors, essentially, and just study how they interact with each other.
It's like you think you're standing on the lowest floor of a building, the ground state, only to discover there's like a trapdoor leading to a microbasement with 4 slightly different floor levels.
That is a perfect way to picture it.
Okay, so we have our 4 spin combinations, but how do we actually map out the energy between them? Because, I mean, if I'm thinking about 2 magnets interacting, classical physics says I just measure the physical distance between them and calculate the magnetic force. Can we do that here?
What's fascinating here is that is the exact trap of classical thinking. In a classical system, yes, you just measure the distance, but quantum mechanically, the electron doesn't have a single fixed location.
Right, it's a cloud.
Exactly. It's moving constantly in a probabilistic cloud around the proton. You just cannot track an exact moment-to-moment physical distance between them to plug into a standard force equation.
Because the concept of distance itself gets totally fuzzy at that scale.
Right. As the text phrases it, the atom has already worked itself out just by settling into the ground state. So instead of a simple distance formula, we need a mathematical engine that can calculate the average interaction energy across all those overlapping probabilities of where the electron might be.
And in quantum mechanics, that engine is called a Hamiltonian.
Spot on. Yes.
But because we have a 4-state system, the Hamiltonian isn't just a basic algebraic equation, right? It has to take the form of a 4x4 matrix.
Yeah, it gets a bit complex.
A bit. The sources detail how setting up that matrix means you have 16 possible mathematical operators to deal with.
True. It's a lot of pieces on the board.
You've got the x, y, and z directional axes for the electron spin, the x, y, and z axes for the proton spin, the 9 possible products of those multiplying together, plus a unit operator. That's 16 operators. Honestly, needing 16 operators to describe a single atom sitting alone in a vacuum feels, I don't know, overly complicated.
It would be an absolute nightmare to calculate if we actually had to use all 16. But, and this is key, we don't.
We don't.
No. And the reason we don't is one of the most elegant concepts in physics, which is spatial symmetry.
Okay, walk me through that. How does symmetry just delete operators?
Think about the physical reality of this hydrogen atom. It's sitting completely alone in empty space. There is no external magnetic field pulling on it. The universe hasn't imposed a north or south on it, It possesses perfect, unbroken spatial symmetry.
Meaning, like, if I physically rotate the atom in space, its internal energy shouldn't suddenly change just because it's facing a different direction?
Yes, exactly. So any mathematical engine we build, our Hamiltonian, cannot depend on an arbitrary x, y, or z axis that we just decided to draw on a chalkboard.
Oh, because that would imply the universe cares about our chalkboard drawing.
Right. If an operator relies heavily on the z-axis, it breaks that perfect symmetry. So when physicists look at those 16 possible operators, they have to throw out anything tied to a specific direction.
That clears the board pretty fast.
It really does. The only mathematical combination of those spin operators that remains perfectly invariant, no matter how you rotate the atom in three-dimensional space, is the dot product of the electron spin vector and the proton spin vector.
A dot product.
Okay.
So we take those two directional vectors, multiply them, and we get a single unified scalar number that describes how aligned they are, totally regardless of their orientation in the broader universe.
That's the beauty of it. The incredibly complex 16-operator Hamiltonian collapses into something stunningly simple. It just becomes a constant, which we call A, multiplied by that dot product.
And that constant A simply represents the baseline average magnetic interaction between the two particles.
Exactly.
The source also brings in Dirac's spin exchange operator to solve this, which I found totally fascinating. It shows that mathematically, the dot product of these two spins is intimately tied to an operator that literally just flips the spins of the two particles.
Yeah, Dirac's formula is a brilliant shortcut here. He proved that the dot product of the electron and proton spins is equal to 2 times the spin exchange operator minus 1.
Okay, 2 times the exchange operator minus 1.
Right. This operator essentially tests the system by swapping the spin states. And when you actually run that math to find the final energy levels of the atom, it reveals a profound split in the ground state.
This is where we get the positive A and negative 3A energies, right?
That's the result, yeah. When you solve the equations, you find that 3 of our 4 states group together. They end up sharing the exact same energy level, which evaluates to a positive A.
Okay.
But the 4th state, which is a very specific entangled state where the spins are mixed and opposite, drops down to an energy of negative 3A.
Wait, I have to pause on the math here. I understand why the 3 parallel states might share an energy of positive A, but why specifically minus 3 for the lowest state? Where does the number 3 actually come from?
It goes right back to Dirac's formula. 2 times the exchange operator minus 1. For the 3 states that are perfectly symmetric, where the spins are cooperating, the exchange operator just spits back a value of 1.
Right.
You plug that in. 2 times 1 is 2, minus 1 leaves you with 1. So you get an energy of positive 1A.
Oh, I see. That's so clean.
It is. But that 4th, lowest state is an antisymmetric combination. Because of the quantum rules governing opposing spins, applying the exchange operator to that state spits back a value of negative 1.
Ah,
Yeah.
so you plug that into Dirac's formula.
Exactly. 2 times negative 1 is negative 2, minus another 1 gives you negative 3. The internal mathematics of the quantum spin states absolutely forces that specific, distinct energy drop to negative 3A.
That makes complete sense.
Yeah.
It's not just some arbitrary drop the universe decided on. It's baked directly into the arithmetic of how those quantum states mirror each other.
Completely baked in.
So we have 3 states sitting up at an energy of positive A and 1 state sitting down at negative 3A, which means the energy difference between that upper tier and the lowest state is exactly 4A.
Yes. And in quantum mechanics, the energy difference between 2 states dictates exactly how the atom interacts with the outside world.
Because it has to shed energy to drop down.
Right. If a hydrogen atom is sitting in one of those upper positive A states and it naturally decays down into the negative 3A state, it has to shed that exact 4A amount of energy. It does that by emitting a photon.
But because that 4A energy difference is so incredibly tiny, the photon it emits doesn't have nearly enough energy to be visible light. It's a very specific microwave photon.
Very specific. When you take that energy difference of 4A and convert it into a frequency, the math predicts a highly specific radio wave.
And this brings us right back to that radio telescope hum we started with.
It does?
Here's where it gets really interesting. The frequency of that emitted photon is 1,420,405,751 cycles per second. But what blows my mind isn't just the number, it's the error margin.
Oh, the precision is staggering.
Physicists measured this to an accuracy of 0.028 cycles. We are talking about a precision of 2 parts in 100 billion.
It is arguably one of the most precise measurements in the history of human science.
And it creates the 21 centimeter line, right?
Yeah.
Because the wavelength of a 1420 megahertz signal is exactly 21 centimeters. Astronomers scan the cosmos for this exact frequency just to locate atomic hydrogen clouds.
Yeah, and by measuring the Doppler shift of that wave-like, whether it arrives slightly squished or stretched out, they can track the speed and direction of the gas.
They literally mapped the swirling arms of our galaxy by listening to the microscopic spin flips of isolated hydrogen atoms. It's almost poetic.
And it's worth noting the dynamic between theory and experiment here, too. The theorists using the Hamiltonian math were thrilled when they could predict this energy gap to an accuracy of 3 parts in 100,000.
Sounds pretty good.
Right. But the experimentalists building the physical detectors absolutely blew them out of the water. They measured it 1,000,000 times more accurately. Today, theoretical physicists don't even try to derive the exact value of the constant A from scratch. They just take that insanely precise experimental number and plug it backward into their foundational equations. Observing the universe passively is what perfected the math.
That's incredible. But we established this delicate, perfectly mathematically balanced 4A gap based entirely on the premise of a vacuum.
Right.
Perfect spatial symmetry.
Yes, a lone atom.
But space is rarely empty. I mean, it's full of stellar magnetic fields. So what happens to this incredibly precise internal structure when an outside magnetic field washes over the atom?
The symmetry breaks entirely. When you apply an external magnetic field, say, running along the z-axis, the space around the atom suddenly has a definite up and down dictated by that outside field.
Right.
Our Hamiltonian engine needs an immediate upgrade to account for this new reality.
Because now the electron and the proton aren't just interacting with each other. They're each being physically pulled on by the external magnet.
Yes, exactly. And we have to add 2 new terms to the matrix. One for the electron interacting with the external field, and one for the proton. And crucially, they react differently.
Because the electron's intrinsic magnetic moment is, what, about 1,000 times stronger than the proton's?
Yep, roughly 1,000 times.
So the outside field grabs onto the electron much harder than it grabs the proton. How does that impact our 4 states?
This creates the Zeeman effect. Those pristine energy levels we just calculated begin to shift. That single lowest negative 3A state. At low magnetic fields, it remains quite stubborn. Its energy stays virtually flat, just ignoring the outside world.
Okay.
But those 3 positive A states that were all happily sharing the exact same energy level, the external magnetic field literally rips them apart.
Whoa.
Yeah. They split into 3 distinct separated energy tiers based on whether their specific spin configurations are fighting the external field, ignoring it, or aligning with it.
So instead of just one transition like from the top tier to the bottom tier, creating that single 21-centimeter line, we suddenly have a staircase of different energy levels.
Exactly. Transitions can now happen between any 2 of those newly separated states. The atom can absorb or emit energy in up to 6 distinct spectral frequencies, depending on which step the electron drops down to.
Okay, let me see if I can visualize the mechanism of what's happening as that external field gets stronger and stronger. Imagine the electron and the proton are an acoustic duo.
Okay, I like where this is going.
When they're alone in a quiet room, meaning 0 external magnetic field, they listen to each other intensely.
Yeah.
Their rhythm, their entire performance, is based purely on their internal interaction with one another.
Right, the internal constant A is dominating the system.
But then a massive heavy metal band sets up right next door and starts playing. That's the external magnetic field. At first, it just sort of distracts them, splitting their harmony.
Zeeman effect.
Right. But if you crank that heavy metal band up to 120 decibels like a massive magnetic field, it completely overpowers them. The acoustic duo can't even hear each other at all anymore. They stop trying to play together, and they both just start headbanging to the incredibly loud rhythm of the heavy metal band.
That is a brilliant analogy. In physics terms, we say the electron and proton become completely uncoupled. At extremely high magnetic fields, the internal interaction between the 2 particles becomes mathematically irrelevant.
They just don't care about each other anymore.
They don't. They stop acting as a combined unit and simply align their individual spins strictly with the external field.
And the sources point out that understanding this decoupling isn't just about passively watching a star's magnetic field distort an atom, right? We can actually use this mechanism to actively manipulate matter.
If we connect this to the bigger picture, that's where the Rabi molecular beam technique comes in. Once a steady external magnetic field splits those states apart, we can introduce a second, very weak oscillating magnetic field. By tuning the frequency of that secondary oscillation to match the exact energy gap between 2 of those new separated states, we can actively force the atom to transition on command. We transition from just observing the quantum architecture to actively piloting it.
It's incredible, but as fascinating as the high field manipulation is, the sources use this Zeeman effect to reveal something arguably more profound about the atom at low magnetic fields. It fundamentally redefines what a hydrogen atom is on a macro scale.
We are definitely crossing from standard chemistry into deep quantum structural theory here. Let's look back at the atom before the heavy metal band gets too loud. Very low external magnetic field. We have the negative 3A state that stays completely flat, and the positive A state that cleanly splits into three distinct paths.
Right, the flat baseline and the three diverging upper paths.
If you take a hydrogen atom resting in that lowest negative 3A state and you shoot it through a Stern-Gerlach apparatus, which is a device that uses magnetic gradients to test how particles deflect based on their spin, that atom travels perfectly straight.
It doesn't deflect at all.
Yeah. Not up, not down. To the apparatus and to the outside universe, that hydrogen atom behaves exactly, flawlessly, like a fundamental particle with a total quantum spin of 0.
But if you take a hydrogen atom in the positive A state and shoot it through the same machine, because that state naturally wants to split into three under a magnetic field, the apparatus physically separates the beam of atoms into three distinct clean lines.
Yes, it acts perfectly like a fundamental particle with a spin of 1. In quantum notation, it has a total angular momentum of J equals 1 with three substates, positive 1, 0, and negative 1.
This is where Richard Feynman does some serious mathematical heavy lifting in the text. He uses the behavior of these hydrogen-based states to mathematically derive the complex transformation matrices for a pure spin-1 particle.
And he does it entirely by using the simpler amplitudes of the spin-1/2 electron and proton.
Right.
It is an absolute masterclass in mathematical synthesis. He proves that the mathematics governing a complex spin-1 system are built entirely from the mathematical combinations of simpler spin-1/2 systems.
I have to pause and just process the gravity of this. Are we saying that if you take two entirely separate, distinct spin-1/2 particles, an electron and a proton, and you bind them together, they don't just act like two individual particles tethered by a string?
No, they don't.
They physically and mathematically merge to form a single, unified entity that is utterly indistinguishable from a pure spin-1 or spin-0 particle.
That is the counterintuitive, beautiful truth of quantum scaling. It basically answers the question of how we get from a universe of blurry subatomic quantum fields to the solid, predictable, macroscopic world we live in.
Wow.
The complex behavior of larger systems is flawlessly built from the combined properties of smaller systems. When the electron and proton bind in that ground state, the new system inherits their combined properties so completely that the original boundaries just disappear.
That's wild.
To the rest of the universe, the hydrogen atom is just a spin-1 or spin-0 particle. The math scales perfectly, preserving the structural rules no matter what level of reality you are looking at.
It's like the universe is built of Lego bricks, but with a bizarre twist. The electron and proton are the small bricks. But when you snap them together, the new structure doesn't look like two bricks glued together. It instantly behaves according to the exact same fundamental rules as a single, larger, solid brick.
Exactly. It's seamless.
What an incredible journey through the sources today. I mean, we started by dismantling the high school myth of a single, boring ground state. We look closely at the 10-electron volt cap that allows us to isolate the microstructure of the atom.
The trapdoor.
Yeah, the trapdoor to the microbasement. We walked through the spatial symmetry that forces the Hamiltonian into a simple dot product and saw how Dirac's spin exchange math perfectly dictates that negative 3A energy drop. We explored how external magnetic fields break that symmetry, ripping the states apart into the Zeeman effect. And we saw how binding two spin-1/2 particles creates an entirely new spin-1 reality.
And, of course, the 21-centimeter line. The fact that all of this complex quantum math results in a specific radio frequency that allows us to map the spiral arms of the galaxy.
Exactly. The fact that the largest structures in the known universe are mapped just by understanding the smallest, quietest interactions. It's amazing.
As we wrap up this deep dive into the sources, I want to leave you with one final thought to explore on your own. We just saw how the math of hydrogen spin states gives us a radio frequency to map distant galaxies, right?
Right.
But those exact same mathematical rules of spin flipping, the way protons align, uncouple, and transition between these exact energy states when exposed to strong magnetic fields and radio frequencies, are the foundational mechanism of an MRI machine.
Wait, really?
Really, the exact same quantum mechanics that locate clouds of gas in deep space are quietly being used in hospitals every single day to map the soft tissues and structures inside your own body. The macroscopic tools that save human lives are simply the quantum mechanics of the ground state, scaled up. I want you to take a second and just look at any electronic device you have near you right now.
Like your smartphone or your laptop?
Yeah, exactly. Maybe the smartwatch on your wrist. Because physically, on a microscopic level, the core of what you're looking at is essentially just this solid, incredibly dense block of crystals.
Mostly silicon.
Right, mostly silicon. And here is the paradox we are starting with today. Inside that solid block, the atoms are massive, and they're packed together so tightly that there is practically zero empty room.
It's incredibly dense.
Right. So if you think of an electron as a tiny, solid physical object, like, I don't know, a billiard ball, and it's trying to navigate that dense atomic forest, it should theoretically crash immediately.
Yeah, I mean, classical physics dictates that it shouldn't be able to move even a fraction of a nanometer without just hitting a wall.
It's like trying to sprint full speed, blindfolded, through a dense crowd of people standing shoulder to shoulder.
You wouldn't make it 2 steps. Classical mechanics tells us the distance an electron can travel before colliding with an atom in that scenario should be practically nothing.
But it does work. I mean, those electrons flow through those solid, densely packed crystals as easily as if they were flying through an entirely empty vacuum.
That is to collide right through.
They glide right through. And that is exactly what we are exploring in today's deep dive. We are jumping into some truly brilliant source material today, specifically Chapter 13 of the legendary Feynman Lectures on Physics, Volume 3.
Ah, yes. Propagation in a crystal lattice.
That's the one. Our mission for this deep dive is to solve the mystery of how solid matter somehow acts as this frictionless superhighway for quantum particles.
And it's such an important mission, too.
It is, because the math behind this doesn't just explain your smartphone, it scales out to explain literally everything, from the mechanics of human vision to the fundamental subatomic particles of the universe.
Well, the transition from classical thinking to quantum thinking here basically changed the modern world. The text sets the stage with a really great historical parallel.
Oh, about the vacuum tubes.
Yeah, exactly. This precise quantum behavior, this frictionless gliding through a crystal, is what allowed engineers to invent the solid-state transistor.
Which was huge.
It's revolutionary. Before that, early computers and radios relied on these incredibly fragile, bulky vacuum tubes. We literally had to boil electrons off a filament into an artificially created vacuum just to get them to move freely.
That sounds wildly inefficient.
It was, but figuring out that they can move just as freely inside a solid chunk of crystal, well, that is what allowed us to shrink a room-sized computer down to something that fits in your pocket.
Okay, let's unpack this. Because to understand how the electron survives this impossible obstacle course, we kind of have to completely abandon our common sense.
Yeah, the billiard ball analogy has to go entirely.
Right, throw it out. We have to start thinking of the electron as a quantum wave. And the source gives this great mechanical analogy to help visualize this.
The coupled pendulums.
Exactly, or like a long line of heavy, tightly coiled springs, all hooked together in a row. If you pull on the spring at the very end and let go, the energy doesn't just snap back and stay there.
No, it travels.
Right, that vibration, that irregularity, it propagates down the entire line of springs as a continuous wave.
And that's exactly what happens when you place an extra electron at one specific atom in a crystal lattice. It isn't permanently stuck in that particular atomic pit, so to speak.
It can move.
Yes, quantum mechanics tells us there's a specific mathematical amplitude for it to jump to the neighboring atom. And because all the millions of atoms in the crystal are coupled together in this infinite repeating chain, just like those springs.
That potential to jump creates a wave of amplitude that ripples through the entire crystal. But wait, I want to push back on that visualization just a bit, because the text is very specific in its warning here. It explicitly says this is not like water leaking between two tanks.
Right, Feynman makes a huge point of that.
Yeah, like if I have 2 buckets of water connected by a tube, the levels just kind of slowly, lazily even out. Why is a quantum wave of amplitude moving through a crystal fundamentally different from probability just leaking from one atom to the next?
What's fascinating here is that the distinction between probability leakage and amplitude leakage is the entire engine of this phenomenon.
How so?
Well, if it were just probability, like water leaking between tanks, the math would result in an exponential decay.
Just a slow leveling out.
Right. The electron would just slowly ooze from one atom to the next until the probability was flat and static everywhere. But the quantum mechanical equations governing this have a very specific, weird feature.
The imaginary term.
Yes, an imaginary term. The math incorporates the square root of -1.
And that imaginary number fundamentally alters how the wave behaves in physical reality.
It completely transforms it. It changes what would be a boring, oozing decay into a dynamic, continuous oscillation.
Okay, so it's not oozing, it's oscillating.
Exactly. The electron's amplitude to be at any given atom is oscillating. Feynman describes it beautifully as going pip, pip, pip from one atom to the next.
Bip, bip, bip. I love that.
It is a complex oscillation where the overall magnitude might be the same everywhere, but the phase of the wave advances progressively from one atom to the adjacent one.
So it's the phase that's moving.
Right. And because it exists as this advancing phase, it completely bypasses the physical bumping of the dense atomic forest. It navigates the base states of the atoms as this continuous orchestrated dance.
Here's where it gets really interesting. Because the electron is moving as a wave of amplitudes, it becomes bound by the mathematical rules of waves.
Yes, and that leads to some incredibly bizarre physical properties.
Totally bizarre. The text breaks down the idea of wave packets. When an electron is localized somewhere in the crystal, it isn't just one pure single frequency.
No, it's actually a superposition.
Right, a mixture of several waves with slightly different frequencies overlapping each other.
And when you mix waves of slightly different frequencies together, they interfere with one another. I mean, if you've ever tuned a guitar and heard that kind of wah-wah pulsing sound as two strings get close to the same pitch.
Oh yeah, I know exactly what you mean.
You are hearing this exact interference. They create a beat pattern.
So those overlapping frequencies create a beat pattern, and the peaks of those beats form a condensed clump, a packet.
Exactly.
And that localized clump moves through the crystal at what physicists call a group velocity. But here is my absolute favorite part of this entire concept, and it requires a bit of a mental leap for you listening.
The big leap.
It is. Because the electron moving through the lattice is essentially a wave packet, its energy is strictly tied to how its amplitude varies in space. And because of that, the crystal lattice acts almost like a funhouse mirror for the electron's mass.
That is a phenomenal way to visualize it. Because if you run the mathematics on that wave packet moving at its group velocity, you arrive at something astonishing.
What does the math show?
The energy of the electron turns out to be proportional to the square of its velocity.
Wait, which is exactly the classical equation for kinetic energy. 1/2 mass times velocity squared.
Exactly. So to an outside observer measuring it, this bizarre phase-shifting quantum wave packet acts exactly like a regular classical particle with a defined mass.
But it's not its real mass, right?
No, its mass is not its actual inherent mass. The text refers to this as the effective mass.
Effective mass.
Right. This effective mass has virtually nothing to do with what a free electron weighs when it's just floating in a vacuum. Instead, it is entirely dictated by two geometric factors.
Which are?
The physical spacing between the atoms in the crystal and the amplitude for the electron to jump from one atom to the next.
So the environment itself, the actual crystal, is deciding how heavy the electron feels. That's crazy. If the lattice is spaced out differently, the exact same electron could feel sluggish and heavy or incredibly light and agile.
Depending on the specific material, this effective mass can be 1/10 of the electron's normal mass, or it can be 30 times heavier. The geometry of the crystal literally creates the illusion of mass.
Let's ground this for a second, because this is why your devices behave the way they do. Like, when you complain that your smartphone is running incredibly slow and getting hot.
You've all been there.
Right. What's literally happening on a quantum level is that the effective mass of those electron wave packets is interacting with the specific crystalline structure of your processor.
Exactly. The engineers who built that microchip spent years choosing materials with the perfect atomic spacing to manipulate that effective mass.
They're creating the exact speed limit they need for the circuitry to function.
The environment controls the particle. And the environment also sets strict boundaries.
What kind of boundaries?
Well, the mathematics dictate that the electron's energy follows a cosine curve based on its wave number. This creates strict minimum and maximum speed limits. The electron can only possess energies within a specific permitted band.
Like an allowed zone.
Right. If an electron tries to exist with an energy outside that band, the math physically breaks down. It would require an infinite amplitude, which is impossible. The crystal simply refuses to let it happen.
It's like the crystal is a heavily policed highway with a strict minimum and maximum speed, and absolutely nothing else is allowed.
That's a great way to put it.
But if we establish that the math allows a wave packet to move with an effective mass to essentially masquerade as a new particle entirely dictated by the geometry of its environment,
Yeah.
we can apply this exact same framework to things that aren't even electrons.
Oh, absolutely. The underlying math of these coupled waves is entirely agnostic to what is actually moving.
Okay, so before we get to the really strange moving nothings, let's just look at a three-dimensional lattice. In 3D, an electron can jump in the X, Y, or Z direction. If it's a perfectly symmetrical cubic crystal, the amplitude to jump is the exact same in all directions.
Right, it's uniform.
But what if it's an asymmetrical crystal? The text points out that the amplitude to jump might be different depending on the direction.
Yes, it can be.
Which means an electron could literally have a different inertia, a completely different effective mass if it moves left to right compared to moving up and down.
The resistance it faces changes purely based on its trajectory through the atomic geometry. It requires what physicists call an effective mass tensor, just to track how heavy the electron behaves depending on which way it turns.
That is completely mind-bending.
It is incredibly mind-bending.
It really is. But here's the pivot. This is the question that blew my mind when I was reading this source. If this math is so universal, does it only apply to adding an extra electron to a crystal? What if we do the opposite?
Ah, yes. This is where the genius of quantum mechanics really shines. Let's say you have a neutral crystal. Every atom has its proper number of electrons. Now, instead of adding an extra one, you pluck one out. You remove it entirely. You are left with an empty void where an electron should be.
But the surrounding electrons are still jumping around, right?
Yes, there is a mathematical amplitude for a neighboring electron to jump into that new empty spot. And when it does, the empty space effectively moves to where that neighbor used to be.
Right. Think about the traffic jam analogy.
Oh yeah, that's a good one.
If you have a line of cars at a red light, completely gridlocked, and the car in the very front moves forward, it leaves an empty space.
Right.
Then the car behind it moves into that space. The cars are moving forward, but the empty space is traveling backward down the line of traffic.
Exactly.
The void itself is traveling.
That is a perfect visualization.
Yeah.
In the equations, it is mathematically identical to say that the missing electron, which the text calls a hole, jumped in the opposite direction.
A hole?
Right. And because the quantum equations are the same, that empty space propagates through the crystal as a wave packet. It has its own group velocity.
So it acts like a particle, too.
It acts exactly like a physical particle with its own effective mass.
Okay.
And because it's defined as the absence of a negative charge, it acts exactly like a particle with a positive charge.
That is wild. A piece of literal nothingness defined purely by the math of the atoms around it, acting like a heavy, positively charged particle roaming through the crystal.
And it gets even stranger than moving nothingness.
How could it get stranger than moving nothingness?
Well, what if nothing is added and nothing is removed?
Mm-hmm.
What if we just take one single atom in the lattice and excite it? We give it a little bump of extra energy, so one of its electrons jumps to a higher state, but stays attached to the atom.
Okay, so it's just energized.
Right. There is an amplitude for that atom to hand its extra energy over to its neighbor and return to its resting ground state.
So the atom itself doesn't move, and the electrons don't leave their atoms.
Wow.
Just the pure energy is jumping from one neighbor to the next.
The mathematics are completely identical yet again. That pure excitation moves through the crystal as a wave packet. Physicists call this an excitant.
Exciting.
Yeah. It behaves like a discrete, neutral particle moving through the crystal, carrying the energy with it. And this raises a massive question. Where else in nature does this exact wave packet mechanism happen outside of silicon computer chips?
Oh, right. The text points directly to human biology.
Yes, the human eye.
That part was amazing.
It hypothesizes that when a photon of light enters your eye and hits your retina, it doesn't just trigger a localized chemical reaction on the spot. It produces an excitant.
So the light creates this wave packet of energy.
Exactly. The cellular structure of the rods in your eye act like a periodic crystalline structure.
Yeah.
That tiny bundle of pure energy, the excitant, propagates through the structure of your retina.
It's literally surfing the cellular geometry.
Surfing the geometry just like a quantum particle until it reaches a specific neural station where its energy is deposited to trigger the electrical impulse of vision.
So the exact same quantum math that makes a semiconductor run the microprocessor in your laptop is potentially how the biology of your eyeball is processing the light from the screen right now.
We're talking about a universal mechanism.
The universality of these equations across vastly different physical systems is staggering.
It really is.
So what does this all mean? We've been talking about these beautiful, perfect scenarios, perfect crystals, infinite identical atoms stretching out endlessly.
Right, the ideal world.
But reality is incredibly messy. What happens when our electron, cruising along as a happy little wave packet with its effective mass, encounters a flaw.
A defect.
Yeah, a wrong atom or a missing one. Because this is where our deep dive transitions from the practical world of solid-state physics into the fundamental fabric of the universe itself.
Well, the introduction of an imperfection fundamentally breaks that beautiful, endless symmetry we've been relying on to keep the wave moving smoothly.
Let's visualize the setup. Imagine a perfectly uniform line of identical atoms, but right in the middle, there's a heavy, stubborn impurity atom.
A completely different element.
Right. And the energy required to exist there is slightly different from the rest of the crystal. When our electron wave packet hits that weird, stubborn atom, the wave splits.
It scatters.
Yeah. Part of the wave manages to continue forward, that's the transmitted wave, but part of it bounces backward, the reflected wave.
It acts just like a wave of water in an ocean hitting a sudden, shallow sandbank. You get a reflection bouncing back and a transmission continuing over the bank.
But I want to zero in on the strangest outcome here, the trapping phenomenon.
Oh, this is fascinating.
If the energy state at that impurity atom happens to be strictly lower than the allowed band of the rest of the crystal, the electron doesn't just scatter and bounce away, it gets caught.
It becomes a trapped electron.
Bound to that impurity. The text explains this using barrier penetration, but I want to push back on simply calling it a math trick.
Here?
Because if the impurity creates an energy well, and the electron classically does not have enough energy to climb out of that hole, how on earth does it leak out into the neighboring atoms at all?
Well, this is the magic of quantum tunneling. And to understand it, we have to look at the physical reality of the wave. Remember that the electron isn't a marble trapped in a steep physical bowl. It is a wave of amplitudes.
Right.
Think of a loud sound wave hitting a thick wooden door. The sound wave doesn't just instantly vanish the moment it touches the wood.
It gets muffled.
It gets violently muffled, and its amplitude drops off incredibly rapidly inside the dense material of the door. But if the door is thin enough, a faint whisper still makes it to the other side.
The wave decays, but it doesn't just cleanly hit zero.
Exactly. The equations governing the electron's position don't just abruptly hit zero at the boundary of the impurity. Instead, the math requires us to introduce an imaginary wave number to solve for the trapped state.
There's that imaginary number again.
Yep. And when the parameter k becomes imaginary, the wave stops its continuous pip-pip-pip oscillation. Instead, the probability drops off exponentially the further you get from the impurity.
Just like the sound dying out inside the wooden door.
Exactly. So the highest probability is finding the electron exactly on the impurity atom. But there is a non-zero, exponentially decaying probability of finding it on the atoms right next door.
It is literally leaking through an energy barrier that it classically does not have the kinetic energy to cross.
Yes, exactly.
That is an incredible visualization. But the text takes this trapping phenomenon one step further, and this absolutely blew my mind.
Oh, the connection to high-energy physics.
Yes, we just solved how an electron gets trapped in a microscopic piece of silicon. But to understand why physicists care so much about this trapped electron, we have to scale up from a microchip to a multi-billion-dollar particle accelerator like the Large Hadron Collider.
Because the math used to find that trapped electron isn't just for crystals.
Right.
If we connect this to the bigger picture, this exact mathematical technique is a foundation of high-energy particle physics.
So if this math works for a single impurity in silicon, you're saying physicists take the same mathematical framework and scale it up to figure out how fundamental particles are formed.
They do. It has to do with the profound mathematical relationship between scattering and bound states.
How so?
When the electron hit our impurity atom, we calculated a scattering amplitude, the exact proportion of the wave that bounced back. Now, earlier we established that the electron's energy has to stay within a specific permitted band, right? The speed limit of the crystal.
Right. It can't exist outside those maximums and minimums.
Well, physicists asked a seemingly ridiculous mathematical question. What if we take that formula for the scattering amplitude and we deliberately plug in energies that are completely outside the permitted band?
Wait, energies that are physically impossible for a free-flowing electron to ever have?
Yes. This is a process called analytical continuation. They're essentially pushing the math into impossible, unphysical regions.
Let's give that a solid analogy. That's like looking at the ripples bouncing off a rock in a pond and running the math of those ripples backward into utterly impossible imaginary scenarios just to see what the equations do.
Yes, that's exactly it. And when they do that, they find something miraculous. They find that at certain specific unphysical energies, the denominator of the scattering equation suddenly becomes zero.
And in math, dividing by 0 means the scattering amplitude becomes infinite.
Infinite. Now, what does an infinite scattering amplitude physically mean?
I don't even know.
It means you have a wave that exists purely on its own, tied infinitely to a single point in space without any incoming incident wave needed to bounce off the rock to start it.
Which is a trapped particle, a completely bound state.
The math proves that a bound state will exist exactly at the specific energy level where that extrapolated scattering amplitude goes to infinity. We found our trapped electron by looking for the infinite pole in the scattering equation.
Wow.
And in high-energy physics, they use this exact same logic. Let's say physicists at the Large Hadron Collider are watching pions scatter off of protons. They measure the ripples, the scattering amplitudes. Then they take those mathematical formulas, analytically continue them into unphysical, mathematically impossible energy regions, and search for where the amplitude goes to infinity.
They push the math of the ripples backward until they find the mathematical proof that a completely invisible fish must be hiding next to the rock.
And when they find that mathematical infinity, they discover an entirely new particle in reality. They find a new strange particle that is actually a bound state of a pion and a proton held together at a lower energy state.
That is just, it's breathtaking, honestly.
The humble math that dictates how an electron bounces off a flaw in a piece of metal is the exact same mathematical key used to discover the fundamental subatomic building blocks of the entire universe.
It really is incredible. So let's bring this all together for a moment and look at the sheer scale of what we've covered today.
We covered a lot of ground.
We did. We started this journey by just looking at a simple piece of metal, or silicon, the phone in your hand, the watch on your wrist. We zoomed into the dense atomic forest and realized that an electron doesn't bounce through it like a classical pinball.
No, it navigates it as a quantum wave.
Right, hopping like a continuous ripple down a line of infinite, tightly coiled springs. We discovered that because it moves as a wave of varying amplitudes, the geometry of the crystal can trick the electron into acting like a heavier or lighter classical particle.
Its effective mass.
Right. And we saw that the math is so beautifully universal that if you remove an electron, the void itself travels, creating a phantom particle of empty space called a hole.
Which is still wild to think about.
Totally. We saw that pure energy can ride this crystal highway as an excitant, which might be the very reason the cells in our eyes can process light from the world around us.
Bridging physics and biology.
Exactly. And finally, we saw that when that wave hits a stubborn flaw in the crystal, it gets trapped. And the mathematical tricks we use to calculate how it gets muffled and stuck are the exact same equations that govern the strange, fundamental particles born inside the world's most powerful particle colliders.
It's all connected.
The device you are listening to this deep dive on right now is functioning at this exact millisecond because billions of electrons are doing this quantum pip-pip-pip dance through a crystal lattice, perfectly engineered by manipulating their effective mass.
It really changes how you view the mundane, solid objects around you. I mean, they aren't static blocks of matter. They are dynamic arenas for these incredibly complex universal wave mechanics.
Which leads me to one final thought for you to take away. Something the text doesn't explicitly spell out, but practically screams when you put all these disparate pieces together.
What's that?
If the exact same mathematical equations perfectly describe water waves in a tank, the effective mass of electrons flowing in silicon, bundles of pure excitation traveling through the human retina, and protons smashing together in a multi-billion-dollar particle accelerator.
Right.
Is the universe actually made of different physical stuff, or is all this stuff just an illusion, a temporary effective mass created by a single underlying universal geometry of waves? Think about that the next time you simply turn on a light.
So right now, the device you are using to listen to this, your phone, your laptop, maybe a smart speaker, it's actually powered by billions of pieces of literal nothing, just empty space.
Yeah, which is honestly, it's one of the most bizarre concepts in physics.
It really is. Today's deep dive is an attempt to figure out how scientists took the literal absence of an electron, like an empty void, and somehow used it to build the entire modern digital world.
Right. I mean, we essentially took something that isn't even a physical object and mathematically tricked the universe into treating it like one.
Exactly. And whether you're prepping for a big meeting or just insanely curious about how your phone actually works, you are definitely in the right place. To understand how we did this, we are diving into a single extraordinary source today. Chapter 14 of the legendary Feynman Lectures on Physics, Volume 3.
A class.
Total classic. But look, Our mission here isn't to just read a textbook to you. The goal is to fundamentally demystify semiconductors. These highly engineered magic rocks that run everything from satellite solar cells to AI arrays. Feynman himself points out that technology changes super fast, but the fundamental physics of silicon and germanium, that's forever.
Yeah, that foundation hasn't changed.
Right. Okay, let's unpack this. To really grasp what a semiconductor is, we have to strip away all the complexity and just picture a simple crystal lattice. Think of silicon or germanium. They have this rigid diamond-like structure, every atom holding hands with four others.
And we need to imagine that crystal at absolute zero. Total, absolute thermal stillness.
No heat at all.
None. Under those conditions, a silicon crystal is just a perfect, pristine insulator. Every single electron is tightly locked into a structural bond with a neighboring atom.
So no movement.
Right, there's zero free agents. If you hook a battery up to that crystal at absolute zero, absolutely no current flows. It is basically a dead piece of rock.
But then we introduce the concept of a hole. Let's say you manage to forcefully rip one electron out of that perfect crystal structure. You just kick it out. What remains in that structural bond is an empty spot. Now, a nearby electron can, jump over to fill that spot, but when it does, it leaves a new empty spot behind it.
Yeah, it cascades.
Exactly. It's like an empty seat in a completely packed movie theater. Say someone in the front row gets up to buy popcorn. There's a gap. If the person behind them moves forward into that seat, the empty space shifts back one row.
Right.
And if everyone keeps shifting forward, that empty seat effectively glides all the way to the back of the theater.
That theater analogy actually captures the core mechanic perfectly. Because mathematically, you do not want to track 100,000 people shifting seats.
That sounds like a nightmare.
It is. You just want to track the empty chair. So in quantum physics, that empty seat behaves as a real physical particle. We treat it as an electron's exact opposite, a particle with a positive charge.
Which is such a wild way to look at reality.
It gets stranger, too. That empty space even has its own effective mass and momentum.
Wait, really? Mass?
Yeah. Think of an air bubble rising through a tank of water. The bubble isn't a thing, right? It's just the absence of water.
Right, it's just air. Or empty space relative to the water.
Exactly. But as water rushes downward to fill the void, the bubble moves upward. It bounces off things. It acts like a physical sphere with its own measurable mass and velocity. Our positive hole wandering through the crystal acts exactly like that bubble.
Okay, that makes sense. But to get that first bubble, to rip that initial electron out of its tight structural bond and create the empty seat, that requires a very specific amount of energy, which Feynman refers to as the gap energy.
Yes, the gap energy. When you deliver that precise amount of energy to the crystal, you kick an electron completely free. It begins wandering the crystal as a negative charge.
And simultaneously, it leaves behind a wandering positive hole.
You've got it. You've just created what physicists call an electron-hole pair. And the source text outlines a few incredible ways to actually deliver that gap energy kick.
The examples are genuinely fascinating. You can kick them with pure light. If a photon hits the crystal, and that photon carries enough energy, it forcefully pops an electron out of its bond.
Boom, pair created.
Exactly. That creates an electron-hole pair. This is the underlying mechanism for photoconductivity. Like, it's exactly how the light meter in a digital camera detects brightness.
It is. Or if you prefer brute force, you can use high-energy particles. The lectures mention that if a proton or, say, a pion from a nuclear accelerator zooms through the crystal at hundreds of millions of electron volts.
That's massive energy.
Yeah, its massive electric field just shreds the bonds as it passes. It can knock out hundreds of thousands of electrons per millimeter of travel.
And early physicists actually used literal diamonds to do this.
Yes.
Because a diamond is essentially just a semiconductor with a massive gap energy. They used diamonds as nuclear particle counter.
It really did. It's brilliant. But for our everyday electronics, we don't rely on lasers or particle accelerators. The most common source of that gap energy is just ambient heat, just thermal vibrations.
Just from the room being warm.
Right. At room temperature, the atomic lattice of a silicon crystal is constantly jiggling. Randomly, that thermal energy will concentrate at one specific atomic site with just enough force to snap an electron out of its bond. A pair is spontaneously created just by heat.
Wait, okay, if the heat of a normal room is constantly popping electrons out of their bonds, creating more and more wandering pairs, why doesn't the crystal eventually just break down or, fill up with infinite charge and explode?
Well, because the universe demands balance. As those free electrons and holes wander randomly through the lattice, they inevitably crash into each other.
Or they meet up again.
Exactly. When a free electron finds a positive hole, it drops back into the empty bond. They annihilate each other, and the extra energy is released back into the crystal as a tiny pulse of heat. So the rate at which heat creates pairs is perfectly balanced by the rate at which they annihilate.
Okay, so it stabilizes.
It does. It reaches a thermal equilibrium. The number of free carriers wandering around at any given moment is dictated by a mathematical rule called the Boltzmann factor.
The Boltzmann factor, right?
Yeah, it's essentially a statistical formula that predicts exactly how much thermal chaos, and therefore how many free carriers you'll get at a specific temperature.
So a pure germanium block at room temperature conducts a tiny, unpredictable amount of electricity based on random heat jiggles. But if you're trying to build a reliable microprocessor, waiting for random thermal chaos is a terrible foundation.
It's basically useless for computing.
Right. You need to control the electricity. You need permanent, reliable carriers.
Which brings us to the process of doping. To gain control, scientists realized they actually had to ruin the perfect crystal. They had to intentionally pollute it.
I found the mechanics of this so elegant when reading the text.
Yeah.
So you melt the germanium crystal down. Germanium atoms have a valence of 4, meaning they each have 4 outer electrons to lock hands with 4 neighbors. But as it cools, you sprinkle in a tiny amount of an impurity, like arsenic. And arsenic has a valence of 5.
Right, 5 electrons. An arsenic atom forces its way into the crystal structure, taking the spot of a germanium atom. It uses 4 of its electrons to lock perfectly into the grid.
But it has that 5th electron left over.
Exactly. It's just awkwardly hanging there, not really participating in any structural bond.
And because it's the odd one out, its binding energy is incredibly weak. The text notes it only takes about 1/100th of an electron volt to knock it loose.
Which is nothing.
Nothing. The standard room temperature jiggling of the crystal is vastly more than enough to snap it off. So that 5th electron instantly wanders away, becoming a permanent, free-floating negative carrier. And because the arsenic atom donated an electron to the cause, this is called an N-type semiconductor. N for negative.
On the flip side, you can create a P-type semiconductor, P for positive. Instead of arsenic, you pollute the crystal with an element that has a valence of 3, like aluminum.
Okay, so now the aluminum atom is sitting in the grid trying to hold hands with 4 germanium neighbors, but it only brought 3 electrons to the party.
Right, it's short one.
It is violently desperate to complete its structural bonds, so it steals an electron from a neighboring germanium atom.
And by stealing that electron, the aluminum atom creates a permanent empty seat, a positive hole in the neighbor's bond.
Oh, wow.
Yeah, that hole is now free to wander the entire crystal. The aluminum acts as an acceptor, giving us a P-type material permanently packed with positive holes.
Hold on, I'm stuck on something regarding the N-type material. If I have a crystal stuffed with extra free-floating negative electrons from all that arsenic, wouldn't they all violently repel each other? Like, why doesn't this thing just act like a battery of static electricity and shock me the second I touch it?
What's fascinating here is that you're only looking at the wandering electron and you're forgetting the atom it left behind.
Oh.
Yeah. When that neutral arsenic atom gives up its 5th negative electron to wander the crystal, the core of the arsenic atom itself becomes a positively charged ion, and it is physically locked into the crystal lattice. It cannot move.
So for every free negative electron zipping around, there is a fixed positive arsenic atom holding its ground.
Precisely. The entire body of the crystal remains perfectly electrically neutral overall. If you attach a battery and sweep all those free electrons out one side, those fixed positive arsenic atoms immediately pull brand new electrons in from the battery's negative terminal.
Just to maintain their neutrality.
Exactly.
And as those electrons flow through, they don't just accelerate instantly to light speed. The text details how they obey Ohm's law. As the electric field pulls them, they are constantly crashing into those fixed impurity atoms and bouncing off the thermal vibrations of the lattice. It's like an obstacle course.
That scattering effect is critical. Instead of infinite acceleration, the electrons achieve a steady, measurable drift velocity. That resistance is why semiconductors have a predictable conductivity that we can actually engineer and use in circuits.
Okay, up to this point, we've been talking about these holes in the P-type material as if they are definitively real positive particles. But if I'm a skeptical student, I'm thinking, well, the only physical things moving in that lattice are electrons shuffling backward. Treating the empty space as a positive particle is just a math trick. How do we definitively prove they act like positive particles?
This raises a very important question, and physicists answered it with one of the most elegant experiments in solid-state physics, the Hall effect. It's a method to definitively prove the sign of the charge carriers moving inside a material.
Walk us through the setup.
Okay, so imagine a solid block of our semiconductor sitting on a table. We hook up a battery to run a current horizontally through it, directly from left to right. Then we take a strong magnet and point it directly into the front face of the block.
So current is flowing sideways, and the magnetic field is pushing straight inward, perpendicular to the current.
Exactly. Now, a magnetic field acts like a bizarre sort of crosswind for moving charges. It deflects them. Let's assume the current is being carried by standard negative electrons. To create a positive current flowing to the right, those physical negative electrons must actually be traveling to the left.
Right, because a negative charge moving left equals a positive current moving right.
You've got it. So we have negative particles traveling left, hitting this magnetic crosswind. The fundamental physics of electromagnetism dictates that this specific combination will push those electrons upward, toward the ceiling. They will literally deflect and pile up on the top surface of the block.
Okay, so if the carriers are electrons, the top of the block gets negatively charged. But what if our theoretical positive holes are the ones carrying the current? To make a rightward current, a positive hole would actually travel to the right.
And here is the beautiful twist of magnetic deflection. If you take a positive charge moving to the right and subject it to that exact same inward magnetic crosswind.
Oh, I see it. It also gets pushed upward. The charge is reversed, but its physical direction of travel is also reversed. So the two changes cancel out. The magnetic wind blows them up to the ceiling either way.
Exactly. Both the left-moving negative electrons, A and D, the right-moving positive holes, will be shoved to the exact same top surface of the block. All we have to do is take a voltmeter and measure the top of the block. If it reads negative, the physical things moving inside are electrons. If it reads positive, the physical things moving are holes.
That is just brilliant.
And historically, scientists assumed the current in metals was always carried by electrons. They tested various metals with this Hall effect experiment, measured a negative charge on top, and considered the case closed.
Until they didn't.
Right, until they decided to test a metal called beryllium.
What happened with beryllium?
The top of the block charged up positive. It had the wrong sign. The scientific community was initially completely baffled, but it proved conclusively that even in certain metals, the conduction is genuinely being carried by these positive holes. The literal absence of an electron can carry an electric current.
Proving that positive holes exist is a great theoretical victory, but it doesn't really help us build a computer. To actually control electricity, we have to make those holes interact with the electrons. So what happens if we literally mash a hole-rich crystal and an electron-rich crystal together?
You get a p-n junction, the absolute bedrock of all modern electronics. You take a crystal that is n-type on the left and p-type on the right, creating a distinct boundary between them.
Like a border crossing. And initially, it's absolute chaos, right? You have a dense crowd of wandering electrons on the n side and a dense crowd of wandering holes on the p side. Natural diffusion takes over.
Yep. Electrons wander across the border into the p side, and holes wander across into the n side.
But that diffusion can't last forever. Because remember those fixed, positively charged arsenic ions left behind on the n side. As the free electrons wander away, those fixed positive charges are completely uncovered.
Exactly.
And as the holes leave the p side, fixed negative aluminum ions are uncovered there.
So just by diffusing across the border, they are building up a massive electrical barrier. The border itself becomes highly charged.
Wow.
This creates a built-in electric field, a steep potential hill right at the junction. Very quickly, this hill gets so steep and powerful that it forcefully repels any more electrons trying to cross over from the inside. The border just slams shut. Equilibrium is reached.
So what does this all mean? If I have this junction sitting on my desk and it has a permanent built-in voltage difference right at the border, could I just take a copper wire, attach one end to the n side, the other end to the p side, and let that built-in hill push a current through the wire forever? Did we just stumble into infinite free energy?
Thermodynamics would like a word with you. Sadly, no. Because to connect that wire, you have to physically attach a metal contact to the n-type side and another metal contact to the p-type side. You aren't just completing a circuit, you are creating two brand new junctions.
Oh, right. The metal 10 junction and the metal to chem junction.
Correct. And each of those new junctions instantly develops its own miniature potential hill. When you add up the voltages of all three hills around the loop, they mathematically cancel each other out to absolute zero. No current flows. You cannot trick the universe.
Okay, fair enough. Unless you add outside energy, like what if I'm shining a light directly onto the p-n junction?
Ah, yes. Now that is different. If a photon of light hits right inside that steep potential hill at the border and creates a new electron-hole pair, the built-in electric field instantly grabs them.
Because they're right on the hill.
Exactly. It sweeps the electron violently down the hill into the inside and shoves the hole into the p side. Because they were separated by the hill, they can now flow through your external wire to reunite.
Which means we just invented the solar cell. That is exactly how the solar panels on a satellite generate power. The light constantly knocks pairs into existence on the hill, and the junction acts like a slide, sorting them and shoving them out the wires.
It is remarkably elegant. But generating power is really only one trick. The most revolutionary use of the p-n junction is to control the flow of power. It acts as an electrical one-way street, a diode.
Feynman uses this great analogy of a mechanical ratchet and pawl. Imagine a gear with teeth that are sloped on one side and flat on the other. A little mechanical catch lets the gear click forward easily, but if you try to spin it backward, it instantly jams against the flat side of the tooth.
Right.
The p-n junction does exactly this for electricity.
Yeah, by applying an external voltage from a battery, we can manipulate that built-in potential hill. If you apply a forward voltage, so connecting the positive terminal to the p side and negative to the n side, you artificially lower the hill. Suddenly, the dam breaks.
Everything rushes across.
Yep. The electrons and holes flood across the border, recombine, and a massive current flows through the circuit. The gear clicks forward.
But if you flip the battery around, applying a reverse voltage, you are artificially piling more charge onto the border, which raises the hill. You make the barrier so high that absolutely nothing can climb over it. The traffic stops completely. The gear jams.
You have successfully created a solid-state electrical valve with absolutely no moving parts.
A one-way street is incredibly useful. But here's where it gets really interesting. What if we don't just stop at a two-layer junction? What if we add a third layer and make a PNP sandwich?
Then you have constructed a transistor, the undisputed king of modern technology. You take a p-type region, called the emitter, you attach it to an n-type region, called the base, and you attach that to another p-type region, called the collector. Two junctions back to back.
Now, intuitively, if you inject a bunch of positive holes from the p-type emitter into the n-type base, you'd expect them to just flow out the wire connected to the base, or water flows down the easiest, closest pipe.
You would definitely expect that. But here is the miraculous engineering secret of the transistor. That middle n-type base layer is manufactured to be unimaginably thin. We are talking less than 10 to the minus 3 centimeters. It is microscopic.
It is so thin that the holes barely even register they are inside it.
Exactly. When the emitter shoots positive holes into that incredibly thin base, they should turn and exit through the base wire. But they are moving so fast, and the region is so unbelievably narrow that almost all of them just overshoot it entirely.
They just blaze right through.
Yeah, they blunder straight through the base and crash into the second junction.
And remember, that second junction, the base to the collector, is hooked up in reverse. It has a massive, steep potential hill. But from the perspective of the holes overshooting the base, they aren't looking up at a hill, they are standing at the top of a cliff.
Right. They hit that reverse junction and just tumble down the steep potential drop into the collector region. Almost 100% of the holes that leave the emitter fall all the way through the base and into the collector. Only a tiny fraction accidentally bump into an electron in the base or find their way out the base wire.
And this is where the magic of amplification happens, because that tiny trickle of current that does manage to go out the base wire is mathematically tethered to the massive waterfall of current crashing into the collector.
Exactly. If you make a microscopic tweak to the voltage on the base, you slightly adjust the height of that first hill from the emitter. Because the release of holes is exponential, a tiny adjustment at the base unleashes a colossal flood of holes from the emitter, which almost all overshoot into the collector.
So you can use a tiny base current to control a collector current that is 100 times larger. A whisper at the base becomes a shout at the collector. You've amplified the signal.
It's pure leverage.
But wait, hold on, I'm stuck on something. The middle base layer is n-type, meaning it's packed with negative electrons. We just lowered the barrier to let positive holes flood in from the emitter. Why don't the base's negative electrons just flood backward into the emitter? Wouldn't that completely derail the whole one-way flow?
It absolutely would, which is where the brilliant material engineering comes in. You control the doping. You intentionally dope the p-type emitter incredibly heavily, so it is absolutely packed with positive holes, but you only very lightly dope the n-type base.
Ah, so there just aren't that many electrons available in the base to go backward in the first place.
Precisely. The density of negative carriers in the base is so much smaller than the massive density of positive carriers in the emitter that the reverse electron current is statistically negligible. The positive holes do almost all the heavy lifting. The electrons just, well, stay out of the way.
It's just staggering to think about the journey of this technology. We started this deep dive looking at a cold, dead, perfect diamond lattice of an insulator. We learned how to kick an electron out of place, creating a wandering hole, a literal piece of empty space that mimics a physical particle.
If we connect this to the bigger picture, it really highlights the sheer ingenuity of physics. We didn't discover a new magical element in the Earth to build computers. We took common, cheap elements like silicon and germanium. We learned to intentionally pollute them with arsenic or aluminum.
We smashed those polluted rocks together to make one-way electrical streets. And finally, we sandwiched them together, making the middle layer so impossibly thin that particles overshoot it entirely, allowing a tiny trickle of current to control a massive flood.
The transistor.
The transistor, the beating heart of all modern electronics.
By understanding the quantum mechanics of atomic bonds, we harnessed the microscopic movement of literal empty spaces to perform logic, amplify sound, and basically process the data of the modern world.
It is the ultimate case of doing a lot with nothing at all. Which leaves me with a thought I want you, the listener, to ponder today. We've spent this time exploring how humanity learned to harness a hole, the literal absence of an electron, to power the digital age. It makes you wonder, what other absences or empty spaces in physics or even in our daily lives are we currently ignoring, just waiting for the exact right perspective to unlock their hidden power?
Sometimes the empty space is actually the most functional part of the structure.
Perfectly said. Thank you all for joining us on this deep dive into the microscopic magic of semiconductors. Keep questioning, keep exploring, and we'll see you next time.
You know, if you've ever stood at a busy 6-lane intersection during rush hour, you've probably watched the sheer chaos of it all.
Oh yeah, it's just a mess of moving parts.
Right. You have cars swerving, people braking unexpectedly, someone cutting across 3 lanes just to make a turn. And if you had to write a mathematical equation to predict exactly where, like, one specific car would be in 10 minutes.
Good luck with that.
Yeah. Exactly. Especially if you had to account for how every single other driver is going to interact with them, you just go crazy. It is an impossibly complex system.
It really is. I mean, it becomes mathematically intractable very, very quickly. The sheer number of variables and, the interactions between those variables, it just explodes. You simply can't track it.
And yet, scientists routinely look at systems that are honestly infinitely more crowded and chaotic than rush hour traffic.
Oh, absolutely.
Think about billions of electrons zipping around inside a crystal or, the densely packed core of an atom. They somehow make sense of these environments. How?
Well, it involves a pretty massive leap of faith.
Right. So today we are exploring a profound scientific paradox, and we're pulling this from the legendary Feynman lectures on physics. We're looking at a mathematical shortcut that physicists and chemists use to understand the impossible.
And it's a shortcut that Richard Feynman himself bluntly called ridiculous.
Which is such a great word for it. It's known as the independent particle approximation.
Yeah, ridiculous is really the perfect word because the concept asks you to do the one thing your brain tells you shouldn't work.
Which is what?
You take a chaotic, heavily interacting system and you just pretend the interactions do not exist.
Which sounds completely counterproductive. I mean, why even bother?
Right, it feels like cheating.
But by the end of this deep dive, you are going to see how this seemingly dry, ridiculous physics concept connects a whole bunch of things. We're talking the behavior of refrigerator magnets, the changing colors of autumn leaves, the structure of the periodic table, and even the secret magic numbers of nuclear physics.
It really ties the whole room together, so to speak.
Okay, let's unpack this. And we're starting with a concept that sounds honestly like something out of a sci-fi movie, the quantum stadium wave.
Yeah, to really grasp this approximation, we kind of have to start with ferromagnetism.
Okay.
This is fundamentally how a magnet works at the quantum level. So picture a one-dimensional line of atoms in a crystal. Something like, say, metallic nickel.
So just a straight line of atoms standing shoulder to shoulder.
That's the image. Now, imagine this line at absolute zero temperature.
So no heat at all.
Exactly.
Hmm.
In this state, to keep the energy of the system at its absolute lowest possible point, every single electron spin on those atoms is perfectly aligned. Let's say they are all pointing up.
Got it. A state of perfect frozen order.
Right. But what happens if you introduce just a tiny bit of temperature? Heat is essentially thermal jitter.
Okay.
The tiny bit of energy creates a chance that just one of those electron spins flips down.
So out of a line of 10 billion ups, you get one rogue down.
Exactly. Now, because of the interaction energy between the adjacent atoms, what physicists call the Hamiltonian, that single downspin doesn't just sit statically on one atom.
Wait, it moves.
It does. Quantum mechanics dictate that there is a certain probability, an amplitude, for that downward state to jump to the neighboring atom, and then to the next. The localized disturbance actually propagates down the line of atoms.
Ah, okay. This is exactly why I like the stadium wave analogy.
Hey, it's a perfect fit.
Like, if you're at a football game and a wave goes around the stadium, the fans aren't actually running around the stands.
Be exhausted.
Right. They were just standing up and sitting back down in their specific seats. But the wave itself, the pattern moves around the entire arena.
That is precisely the physical mechanism here. The electrons stay tethered to their respective atoms, but the downspin state travels.
But wait, hold on. If I'm visualizing this stadium wave, you're telling me a localized lack of alignment, just a flipped spin, is mathematically treated as a literal physical object.
It is. Because this moving disturbance travels at a specific speed with a specific energy, it actually carries momentum.
Really?
Yeah. It resists changes to its motion, which means it has an effective mass. Physicists give it a formal name. They call it a magnon.
A magnon. Okay.
For all mathematical intents and purposes, it behaves just like a particle. And this is where we take the leap into the independent particle approximation. Imagine what happens if a second bit of thermal energy hits the crystal and a second spin flips down.
So now we have two magnons moving around our microscopic stadium.
Right. Now, common sense dictates that if these two moving disturbances bump into each other, they should interact in some incredibly messy way.
I mean, yeah, they are adjacent magnetic anomalies, right? They should crash.
They should. But the math reveals something astonishing. If you calculate the overall state of having two downspins, their individual amplitudes to move simply multiply, and their energies add together.
Wait, meaning they basically pass right through each other? They don't care about each other at all.
Exactly. They act as entirely independent Bose particles. What's fascinating here is that if you have a massive crystal with billions of atoms, ignoring the messy, complex interactions between these little spin disturbances works remarkably well.
That's wild.
You can calculate the total energy of the system just by adding up the energies of these independent magnons as if each one were completely alone in the universe.
Okay, so treating a ripple in a magnet as an independent particle is a fantastic trick. But what happens if the system is inherently more chaotic than a frozen crystal?
Oh, like a liquid or a gas.
Or like if we move out of solid-state physics and drop right into the electron traffic jams of organic chemistry, does this trick still work?
Well, we can test that by looking at the benzene molecule.
Okay, benzene. For those trying to picture it, benzene is a ring of 6 carbon atoms forming a hexagon.
Right. And the chemical bonds in that ring involve a network of electrons that are essentially shared. They form a sort of cloud across the whole molecule.
So to figure out the baseline energy of benzene, the thought experiment goes like this. Imagine taking that hexagonal ring and momentarily stripping away 6 of its shared electrons.
Just pulling them right off.
Yeah, you're left with just a bare skeleton of carbon bonds. Then you toss those 6 electrons back into the ring, one by one, and let them run freely around the 6 carbon locations.
And this is where the ridiculous shortcut is applied. When we put those 6 electrons back into the ring, we are going to operate under the assumption that they do not affect each other at all.
Okay, my rush hour traffic analogy comes back with a vengeance here.
It really does.
That is like trying to model traffic on a 6-exit roundabout by assuming none of the cars notice each other. Electrons all have a negative charge. They naturally repel each other with the Coulomb force.
Or strongly, yes.
If 2 of them end up near the same carbon atom, they should violently push each other away. Assuming they don't interact isn't just a slight simplification. It actively contradicts the most basic law of electromagnetism.
It absolutely contradicts fundamental physics. The assumption is profoundly flawed.
So why do it?
Here is why chemists do it anyway. Even with this massive theoretical blind spot, if you model that ring like a looped track and let the electrons run around it independently, quantum mechanics spits out a set of specific, allowed energy states.
Oh, like mandated speed limits on the roundabout. You can only drive at exactly 10 miles an hour or exactly 30 miles an hour.
Perfect analogy. And when you drop your electrons into those allowed states, starting with the lowest possible speed limit, the math shows that the total baseline energy of the molecule plummets
It drops.
dramatically. By letting the electrons loop freely, instead of confining them to strict, isolated bonds, the molecule saves a massive amount of energy.
Huh.
And the amount of energy saved is directly proportional to how easily the electrons can jump from one carbon atom to the next.
Which proves mathematically why benzene is so incredibly stable compared to other configurations. So the independent particle model, despite being fundamentally physically impossible, correctly predicts the real-world stability of the molecule.
It works, but it exposes a fascinating cultural difference between physicists and chemists.
How so?
Well, if you try to calculate exactly how easily those electrons jump between atoms based on chemical binding energy, you get one number.
Okay.
But if you measure how benzene absorbs light in a laboratory, you get a completely different number. The constant in the math isn't actually constant.
Oh.
A physicist might look at that discrepancy and say the theory is broken because the electrons do interact, so we must calculate the exact Coulomb repulsion.
But the organic chemist says, look, I don't have time to calculate the exact Coulomb interactions of dozens of electrons.
Yeah?
I need empirical rules to predict if this compound is going to explode in my beaker.
Exactly. They essentially use it as a fudge factor.
Yeah.
They alter the jumping constant depending on what specific property they are trying to predict. It's pure pragmatism.
Pragmatic survival in the lab. And the empirical rules they derive from this shortcut are shockingly elegant.
They really are.
Because if you run this exact same independent particle math on butadiene, which is just 4 carbon atoms in a straight line, it outputs a very specific proportional drop in energy. The baseline energy is reduced by a factor of exactly 1.618.
Right.
Now, I noticed that number immediately.
Oh, I'm sure you did.
For anyone who loves math history, 1.618 is the golden ratio of the ancient Greeks. It's the mathematical proportion found in the spiral of galaxies, the Mona Lisa, sunflower seeds. It's amazing to see that exact ratio pop out of the organic chemistry of a 4-carbon line.
It's a beautiful mathematical coincidence, but, it raises an important question. If this math requires so much fudging and is based on a physically impossible premise of non-interacting electrons, why is it so universally taught and used?
Because taking this shortcut reveals something much deeper. It reveals the ultimate secret of stability, the concept of the energy shell.
Yes. Let's explore the energy shell, because this is where the rules of the universe really start to snap into focus.
Okay.
The overarching rule derived from this approximation is this: molecules, or ions, become exceptionally stable when their available electrons perfectly fill up an energy shell.
Think of it like a parking garage, right?
Exactly like a parking garage.
Mhm.
You can think of an energy shell like a level in that garage. If a level is exactly full, the structure is stable and happy.
But if you have one car forced to park on the level above, or one empty spot left on the main level, the system is volatile and wants to react.
You've got it.
And a brilliant counterintuitive example of this is a molecule that forms a 3-carbon ring, just a tiny triangle of carbon atoms.
Right.
Now, my basic high school chemistry tells me that carbon atoms want their bonds to be at relatively wide angles. Forcing those bonds into a tight 60-degree equilateral triangle creates massive physical stress.
Tons of stress.
It shouldn't exist. It should just snap open like a broken rubber band.
Physical intuition tells you it should snap. But look at what the independent particle model reveals. If you map out the parking garage for a 3-carbon ring, the lowest energy shell has exactly 2 parking spots.
Okay.
A neutral 3-carbon ring naturally has 3 free electrons to park. So you put 2 in the lowest state, and that third electron is forced up to a much higher, highly unstable energy level.
It's the odd one out. It makes the already stressed out triangle incredibly volatile.
But what if you remove 1 electron? You create a positive ion. Specifically, if you attach some surrounding stabilizer rings, you get a structure called the triphenyl cyclopropanyl cation.
I'm so glad you had to pronounce that and not me.
Semifull. But by removing that third volatile electron, the remaining 2 perfectly fill that lowest energy shell.
The parking level is perfectly full.
Yes.
Yeah.
And suddenly, despite the massive physical stress of those tight 60-degree angles, the molecule becomes remarkably stable.
That's incredible.
The mathematical rule of the filled shell literally overrides the physical strain of the triangle.
The math says, this shell is full, lock it down, and the molecule just obeys.
It does.
And we can scale this exact same concept up to biology. Think about chlorophyll, the molecule that makes life on Earth possible.
Oh, chlorophyll relies on this exact principle.
Chlorophyll features this massive closed ring structure with 20 distinct intervals. And just like in the benzene ring, the extra electrons run freely around this giant track.
Right.
Because the track is so large, the independent particle math generates a very specific, spaced-out set of energy levels, a very tall parking garage.
And here is where the how becomes fascinating. When sunlight hits a leaf, the photons of light carry energy. If a photon hits an electron, the electron can absorb that energy and jump to a higher level in the parking garage.
But it can only do that if the energy of the photon perfectly matches the gap between the floors.
Exactly. It has to be an exact match.
And the gaps in chlorophyll's 20-interval ring perfectly match the energy of red and blue light. So it absorbs those colors, leaving only the green light to bounce back into our eyes.
That's why plants are green.
Meanwhile, a very similar molecule called a xanthophyll has a slightly different track size. Its energy gaps absorb different wavelengths, giving autumn leaves their brilliant red and yellow colors.
So the very same ridiculous shortcut that explains a microscopic, stressed-out carbon triangle also dictates the color palette of an entire forest canopy.
Oh, mind-blowing.
If we connect this to the bigger picture, we start to realize that this rule, the stability of filled shells, isn't just a quirk of complex organic molecules. It dictates the foundational building blocks of reality.
Yeah, let's scale it all the way down to the periodic table of elements.
When we apply the independent particle model to a single atom, we imagine the electrons moving independently in the central gravitational-like pole of the nucleus. And again, we find these energy shells.
Okay.
When an atom has exactly enough electrons to perfectly fill its outermost shell, it achieves that ultimate stability.
Those are the noble gases: helium, neon, argon. Their shells are fully packed, so they practically refuse to react or bond with anything else.
They're completely inert. Conversely, if you have an atom with just one extra electron hanging outside a filled shell like sodium, or an atom desperately missing just one electron to complete a shell like chlorine, they become highly reactive.
They will aggressively seek to lose or gain an electron to reach that stable, filled shell state.
Exactly. The independent particle approximation literally draws the architectural blueprint of the periodic table.
But this leads to the ultimate test of the theory. Let's dive into the atomic nucleus itself. The protons and neutrons, the nucleons.
This is where it gets really tricky.
Historically, physicists noticed a mystery they called the magic numbers. They found that atomic nuclei with exactly 2, 8, 20, 28, 50, or 82 protons or neutrons were mysteriously exceptionally stable.
They were essentially the noble gases of the nuclear world.
They exhibited the exact same filled shell behavior we see in electrons. But here is the massive logical hurdle. We established that this entire model is a shortcut where we pretend things don't interact. But protons and neutrons inside a nucleus are packed shoulder to shoulder, pulling on each other with the strong nuclear force, the single most powerful force in the universe.
It is incredibly strong.
How can you possibly pretend that protons packed that tightly aren't interacting? You're talking about a demolition derby inside a phone booth.
It seems like a profound contradiction. I mean, for a long time, physicists assumed the independent particle model would be completely useless in the nucleus for exactly the reason you just stated.
Exactly.
But eventually they tried a variation. They assumed that instead of calculating how nucleon A violently interacts with nucleon B, every single proton and neutron moves independently inside a central potential.
A central potential?
Think of it as a generalized field created by the average effect of all the other nucleons combined.
Oh, okay. So instead of tracking individual collisions, you just calculate how one single particle moves through a generalized fog of strong nuclear force.
That is a brilliant way to conceptualize it. The fog. And when they ran the math on this nuclear fog, the independent particle model successfully predicted the first few magic numbers, 2, 8, and 20.
Wow.
It showed that those numbers perfectly filled the lowest nuclear energy shells.
But it failed on the higher numbers, right? The model didn't predict the stability of 28, 50, or 82?
It didn't. And this raises an important question. What do you do when your incredibly useful but admittedly flawed model finally hits a wall?
You don't throw it out.
No, you don't. If you are Maria Kepler-Mayer and Johannes D. Jensen, you realize the fundamental independent particle approximation is sound. It just needs a mechanical tweak to account for how nucleons spin.
Let's break down how that tweak actually works, because this is what won them the Nobel Prize.
Right. They added a correction for what is called the spin-orbit interaction.
Okay.
Every nucleon has an intrinsic spin, like a top, and also orbits the center of the nucleus. Mayer and Jensen proposed that the strong force interaction changes slightly based on alignment.
Oh, like how magnets attract or repel depending on how you hold them.
Very similar. If a nucleon spin is pointing in the same direction as its orbital motion parallel, it drops into a significantly lower energy state.
Okay, and if it's opposite?
If the spin is opposite to the orbit, it gets pushed into a higher energy state.
So it takes what we thought was one single parking level and splits it into two distinct levels. One drops down, one pushes up.
Yes, and that splitting is the key. The level that drops down actually joins the energy shell below it.
Oh, wow.
Yeah, this completely changes where the major gaps between the shells are located. By introducing this one tiny spin orbit mechanism into the independent model, the new gaps perfectly align to hold exactly 28, 50, and 82 particles.
That's incredible. By ignoring the individual chaos of the strongest force in the universe and treating the nucleus as a collection of independent particles navigating a fog, they unlocked the deepest structural secrets of matter.
It's a triumph of theoretical physics.
So what does this all mean? We started with a mathematical shortcut that Feynman warned us was ridiculous. A shortcut that demands we ignore the basic laws of electromagnetism and the strong nuclear force. We literally pretend that things don't interact.
We do.
And yet, by using that exact shortcut, we can decode the traveling quantum waves inside refrigerator magnets. We can prove why a stressed-out triangle of carbon atoms can actually exist.
Right.
We can explain why leaves change color in the fall, and we can predict the exact architecture of the atomic nucleus.
It is a profound testament to the fact that sometimes truth is found not in perfect microscopic precision, but in the right kind of simplification.
There is a massive lesson here for all of us right now. We live in an era of absolute information overload. Everything is hyper-complex. Everything is interconnected. We are constantly trying to calculate the interactions of a million different variables at once in our daily lives.
It's exhausting just thinking about it.
It really is. But the independent particle approximation teaches us that sometimes, if you want to understand a hopelessly complex system, the absolute worst thing you can do is try to track every single collision.
Yeah.
Sometimes you have to temporarily ignore the chaos. You have to isolate the individual pieces, put them in a vacuum, and just see what they would do on their own.
You find the underlying structure by deliberately quieting the noise of the interactions.
Which leaves me with a final thought for you to mull over. If physicists can decode the atomic nucleus, the densest, most intensely interactive environment in the universe, by temporarily pretending those interactions don't exist, what impossibly complex systems in our human world might we finally understand if we tried the same trick?
That's a great question.
If we looked at the chaos of global economics, or the tangled web of social media algorithms, or yes, even that 6-lane rush hour traffic jam, what hidden magic numbers might we find if we just viewed them through the lens of the independent particle approximation?
You know that feeling when you're looking at a photo on your phone and you zoom in so far that the image just shatters?
Oh yeah, it gets all blocky and distorted.
Right. The smooth curve of a face suddenly turns into these harsh, blocky squares, pixels. And on one hand, it kind of ruins the picture.
Sure.
But on the other hand, there's a certain comfort in those little squares.
Yeah.
You know, it feels safe. It's this highly countable, discrete reality where you can point to a specific spot and just say, there it is. That is a blue square.
Yeah, it gives us this illusion of absolute control. I mean, a universe made of Lego bricks is easy to categorize, it's easy to calculate, and, well, easy to understand.
Exactly. But then you zoom back out and those hard edges disappear. The digital blocks vanish into this seamless, continuous flow, an analog reality.
Which is much harder to wrap your head around.
So much harder. And, well, that is exactly the leap we are making today. Welcome to today's deep dive. Our mission is to finally take the training wheels off our understanding of quantum mechanics.
You really are.
We're stepping out of that pixelated, simplified view of the universe. And we're diving headfirst into the mind-bending reality of how electrons actually behave in continuous space.
And we are pulling our insights from a really dense but incredibly rewarding source today. Chapter 16 of the legendary Feynman Lectures on Physics, Volume 3. We're going to deconstruct the math, the concepts, and, the physical reality that Feynman outlines.
Now, if you're listening to this and you're someone who is intensely curious, Maybe you want to understand quantum mechanics without getting buried under a mountain of chalkboard math. Don't worry. We've got you.
We promise.
Yeah. By the end of this deep dive, you are going to have a massive aha moment about why the physical world, down to the very chair you're sitting on right now, doesn't just collapse into complete chaos.
But to get there, we first have to admit what our earlier quantum models kind of left out. Think about how we typically describe a simple system, like an ammonia molecule or a hydrogen molecular ion.
Right. Those earlier models treat reality exactly like our zoomed-in photograph. They say the electron is just here or there, like it's localized at specific atoms.
Yes, either at atom A or atom B.
Exactly. The electron just jumps between those discrete atomic sites.
And those are two-state approximations, which, to be fair, are brilliant for getting a baseline understanding of low-energy states. But nature isn't a checkerboard.
Right.
The electron isn't just rigidly teleporting from one atomic site to another across some empty void. So to get the real picture, Feynman asks us to imagine taking that lattice spacing, the actual physical distance between those discrete points, and shrinking it.
Okay, shrinking the grid.
Yeah, you shrink the grid smaller and smaller until the distance between the points is literally zero.
Okay, let's unpack this. Because if we shrink the grid down to zero, the electron isn't jumping anymore. We've basically upgraded from a low-resolution video game where a character can only stand on specific tiles to this perfectly smooth analog landscape.
That's a great way to put it.
So the electron could, theoretically, be anywhere along a continuous line.
What's fascinating here is what actually happens to the math when that grid disappears. The chance of an electron moving from point A to point B becomes a continuous distribution.
The continuous wave function.
Exactly. Physicists denote it with the Greek letter CAI. But this is where people usually fall into a huge conceptual trap. They hear continuous wave, and they picture, like, a physical substance smearing out over space.
Yeah, my mind immediately goes to a drop of food coloring spreading out in the glass of water, or maybe a gas expanding to fill a vacuum tube.
Right, but that is classical diffusion. Classical diffusion describes things that eventually smooth out and just stop. The mathematical equations for that kind of physical spreading rely entirely on real numbers.
Okay.
But the wave function for an electron operates on a completely different set of rules. Because its underlying differential equation has an imaginary coefficient, imaginary numbers are fundamentally baked right into the fabric of it.
Let's slow down there for a second, because imaginary numbers usually makes people's eyes glaze over.
True.
We aren't talking about made-up math. Imaginary numbers involving the square root of -1 are the mathematical language of rotation and oscillation.
They are the engine of a wave. Because of that imaginary coefficient, the electron's probability doesn't just spread out and die like heat dissipating in a room. It creates these complex oscillating waves of probability. It pulses.
Wow. So we're not talking about a physical wave of water. We are talking about a waving, vibrating map of probability.
Yes.
And Feynman is very careful with how we extract reality from that map, right?
Yeah.
You take this wave function and you find its absolute square. And that specific calculation gives you the probability density of finding the electron in any small region.
Notice you said in any small region instead of at a specific point.
Oh, yeah.
That's key. In a continuous analog universe, a true mathematical point has zero width. If you ask the math, what is the probability of finding the electron at this exact, infinitely precise, zero-width coordinate?
It's just zero.
The answer is effectively zero. You can only ever calculate the probability of finding it within a small interval.
Which perfectly sets up the ultimate seesaw of physics, because now that we accept the electron is this continuous oscillating wave of probability spread out across space, we really have to ask, what does this spatial smearing mean for its movement? Like, how fast is this thing going?
This brings us to the absolute bedrock of quantum reality. Feynman asks us to look at a specific wave function shaped like a classic bell curve, a Gaussian curve.
Okay, I'm picturing it.
Picture a smooth, symmetrical hill of probability. The peak of the hill is where you are most likely to find the particle. And the width of that hill, the actual spread of the probability, is a value we call sigma.
So sigma is essentially our margin of error. It tells us how smeared out the electron's physical position actually is.
Actually, it's worse than a margin of error. It is the actual physical smearing of the particle itself. Now, using the continuous wave equations, you can calculate the momentum for this exact same state. You basically ask the math, given this position curve, what does the speed and direction look like? And the math yields a second bell curve. It has the exact same shape, but its width, let's call it eta, is dictated by a strict inverse relationship to your position spread, sigma.
Wait, so If I try to cheat this system, like, if I try to perfectly pin down the electron by squeezing its position spread, making that sigma microscopically tiny, does the math force the momentum spread to bulge outwards?
The math forces it, and reality obeys. The equation Feynman derives states that the momentum spread equals Planck's constant divided by 2 times the position spread.
Well,
Yeah, so if you make the distribution in position incredibly narrow, the distribution in momentum becomes massively wide. You squeeze one, the other literally expands.
meaning if I know exactly where the electron is, its momentum is so smeared out that I have absolutely no idea how fast it is going or in what direction. It could be moving at a millimeter per hour or near the speed of light.
Precisely. And this isn't a limitation of our microscopes or our measuring tools. This specific equation, the uncertainty in momentum times the uncertainty in position, is always greater than or equal to Planck's constant divided by 2, is the mathematical proof of the Heisenberg uncertainty principle.
That's a massive shift in perspective, though. We usually hear about Heisenberg as this abstract, philosophical warning that human observers break things by looking at them. You can't know everything at once.
Right, the whole observer effect confusion.
Yeah. But Feynman shows it isn't philosophy at all. It just falls right out of the geometry of continuous waves.
Furthermore, that bell-shaped Gaussian distribution we just pictured, that represents the absolute best-case scenario. It gives the smallest possible uncertainty.
Wait, really?
Yeah. For literally any other shape of wave, the blurriness is even worse. Nature fundamentally will not allow you to know both properties precisely.
But physicists are notoriously stubborn. I mean, if nature refuses to let us pin down a particle, physicists still have to do the math for a theoretical state where a particle is located exactly at position 0. Sometimes you just need to anchor your equations.
You do.
So how do you force a particle into an exact location if the uncertainty principle is actively fighting you the whole time?
Well, you have to invent new math. To make these continuous equations work, physicists need to normalize quantum states.
Normalize.
Yeah, normalizing just means ensuring that the total probability of finding the particle somewhere in the universe adds up to exactly 1 or 100%. It has to be somewhere.
Right.
So if you want to describe a particle that is at one exact point, you need a function that equals 0 everywhere else in the universe, but at that one specific point, it spikes so high that the total area underneath the spike is exactly 1.
But there is no standard mathematical function that can do that.
Yeah.
I mean, you are asking for something that has a width of absolute 0, but somehow still contains a finite area of exactly 1. That breaks classical calculus.
It completely breaks it.
I always like to visualize it like a magic trick with a rectangle of modeling clay.
Oh, I like that. Walk us through that.
So imagine you have a rectangle of clay that has an area of exactly 1 square inch. You start pushing the sides closer and closer together, and to keep the total amount of clay exactly the same, the rectangle has to get taller and taller.
Right, it squeezes upward.
Exactly. And you keep squeezing until the width is basically 0. It is infinitely thin and infinitely tall, yet it somehow still contains exactly 1 square inch of clay.
That infinitely tall, infinitely thin spike is the Dirac delta function, invented by Paul Dirac. By classical standards, it is an impossible contradiction. But Feynman explains that this bizarre tool is the mandatory bridge required to survive in a continuous universe.
How does an impossible spike actually help the math, though?
It acts as a perfect mathematical filter. If you take a messy, continuous wave function that is smeared all over space, and you multiply it by a Dirac delta function centered at position 0.
Let me guess. It zeroes everything else out.
Yes. The delta function annihilates everything except the exact value of the wave at that one microscopic point. It lets physicists extract a single, discrete reality out of a continuous, smeared-out universe.
Okay, so we've left the grid behind for continuous waves, we've hit the brick wall of the Heisenberg seesaw, and we've used Dirac's impossible clay to force the math to behave.
We've covered a lot of ground.
We really have. And we have successfully described one particle moving along a one-dimensional line. But here's where it gets really interesting. Because you, me, and the listener, we live in a three-dimensional universe, and it's crowded. What happens to the math when we add just one more particle?
Well, expanding to 3 dimensions is a logical step. You swap out your 1D line for a 3D space, and instead of measuring the probability along a line, you use volume integrals.
Meaning, instead of scanning a piece of string, we are mathematically scanning every possible 3D box of space in the universe to find the probability.
Checking every cubic millimeter, yes. But your second point, adding a second particle, that shatters the classical worldview entirely.
Let me guess the naive approach here. I would just say, draw a 3D wave for particle 1, and then draw a separate 3D wave for particle 2, and just see how they bump into each other.
That is exactly the trap people fall into. In quantum mechanics, for two interacting particles, you do not have two separate waves.
Really?
No. Their probabilities depend on each other. The wave function must describe the condition of the entire system simultaneously. It becomes a single function of both sets of coordinates.
Wait, are you saying that an electron loses its own independent wave function the moment it interacts with another one?
That is the raw truth of it. It is no longer an oscillation moving through our familiar 3D space. Mathematically, it becomes a single wave vibrating in 6 dimensions.
6 dimensions.
Yes, 3 dimensions track the possible locations of the first particle, and 3 separate dimensions track the second.
6 dimensions, just for 2 particles. So if I have 3 particles, I'm dealing with a 9-dimensional wave function.
And a simple carbon atom with 6 electrons requires an 18-dimensional wave function.
That is just ridiculous.
It sounds absurd, but this counterintuitive leap is the hidden engine behind all those famous quantum paradoxes you read about in the news. Take quantum entanglement, where measuring one particle on Earth instantly tells you the state of a particle on Mars.
Oh, that's the one that always bothers people. They always ask, how is a signal traveling faster than light between them?
Exactly. And they ask that because they are picturing 2 separate objects in a 3D box. They are imagining a radio wave flying from Earth to Mars.
Right, some physical beam connecting them.
But they aren't separate. They are a single combined entity in a higher dimensional mathematical space. When you measure the particle on Earth, you aren't sending a signal to Mars. You are collapsing the entire 6-dimensional reality at once. You cannot describe what happens to one without the coordinates of both.
Okay, my brain is officially stretched.
It's a lot.
I'm trying to picture a 6-dimensional wave vibrating in an abstract probability space. But we really have to ground this, because these waves don't just exist in a vacuum. Electrons get pulled on by physical forces. They get trapped by the positive electric charge of an atomic nucleus. How does a smeared-out continuous wave actually get trapped?
This brings us to the most triumphant part of the source text. The Schrödinger equation, formulated in 1926. What Erwin Schrödinger did was incorporate a potential energy landscape into these continuous waves.
A potential energy landscape. Let's make that visual for a second. Imagine a flat plane of energy, and wherever there is an atomic nucleus, there is a deep crater, a valley. The electric forces from the nucleus are trying to drag the electron down into that valley and keep it there.
That crater is what physicists call a potential well. By mapping how the continuous wave function behaves inside and outside that crater, the Schrödinger equation provided the master key to the internal structure of matter.
Oh, wow.
Yeah, it explained why atoms have specific energy levels and how chemical bonds actually form.
So how does the math actually trap the wave? I know Feynman breaks this down beautifully.
Yeah.
Let's say we have an electron stuck in that deep crater. We need to find a wave function, a probability map that actually fits inside the valley.
The ultimate rule for a trapped particle is that the wave function's amplitude must smoothly fade to 0 when you get far away from the crater. If the probability doesn't drop to 0 outside the valley, it means the particle has a chance of being found at the other side of the universe.
Meaning it isn't trapped at all.
Exactly.
So physicists play a guessing game. You start guessing energy levels for the electron to see what the wave does. Let's say you guess a random arbitrary amount of energy. We'll call it energy A. When you plug energy A into Schrödinger's differential equation, the wave starts out fine inside the crater. It curves nicely.
So far, so good.
But the moment it reaches the edge of the well,
the math blows up. The differential equation dictates that the curvature of the wave depends on the energy. If you pick the wrong energy, the curve doesn't bend back towards 0, it bends away. And the math multiplies the error exponentially, and the amplitude just shoots off to infinity.
Which physically means the electron is infinitely more likely to be found infinitely far away.
Right.
It completely escaped our crater. It is not bound to the atom.
Right, so you try another random energy B, which is slightly higher. This time, the wave starts out okay, but as it hits the edge of the crater, it flips upside down, crosses the axis, and plunges down to negative infinity. Once again, the equation runs away from us. The particle is lost.
You know, it's like swinging a jump rope between two people.
How so?
Well, if you just shake your arm in some random arbitrary rhythm, the rope just flails around chaotically. It's a mess. There's no structure.
Right.
But if you adjust your speed to hit the exact right rhythm, like the perfect frequency, Suddenly the rope forms a beautiful, smooth, standing wave perfectly contained between your hands.
I love that analogy because that perfect standing wave is exactly what the math requires. Somewhere between the failed energy A and the failed energy B, there is a very specific discrete energy. Let's call it energy C. At exactly energy C, the curvature of the wave perfectly balances. It tapers smoothly down to absolute zero just outside the crater.
The wave doesn't blow up. It stays completely contained within the valley. The electron is successfully bound to the atom.
But if we connect this to the bigger picture, this mechanism answers the deepest question of the whole deep dive. How does a continuous, smooth equation suddenly create discrete, stair-step quantum effects?
Right. Because that was the entire point of zooming out. We wanted to leave the pixelated discrete grid behind, but atoms still have discrete energy levels. An electron can have energy level 1 or level 2, but never level 1.5. Why if the math is continuous?
Because of the edges of the crater. The strict boundary condition, the requirement that the wave function must not shoot off to infinity at the edges, is the literal mechanism that forces energy to be quantized.
That's incredible.
You can't just have any decimal of energy. You can only possess the specific discrete energies that happen to perfectly taper off to zero. The continuous universe creates its own discrete restrictions simply by requiring the particle to stay trapped.
That is absolutely stunning. It's literally the geometry of the valley forcing the wave to pick a specific, perfect rhythm. So what does this all mean for you listening right now? Let's trace the journey.
Let's recap.
We started by looking at reality like a zoomed-in digital photo, treating atoms like discrete pixels on a grid. Then we zoomed out and realized that electrons are actually continuous, complex waves of probability pulsing through space.
But accepting that continuous nature comes with strict physical trade-offs. We hit the Heisenberg uncertainty principle, the mathematical seesaw, where squeezing an electron's position inherently forces its momentum to smear out infinitely.
Then we looked at the impossible magic trick of Dirac's delta function, squeezing the clay until it's infinitely tall and infinitely thin, just so physicists could filter out a single point of reality.
And then we stretched our minds into a six-dimensional wave just to describe two interacting particles.
Yeah, realizing that quantum entanglement isn't spooky magic at all, it's just a shared geometric reality.
And finally, we saw how the Schrödinger equation takes these multidimensional waves and places them into the craters of a potential energy landscape. We discovered that the only way these waves survive without blowing up to infinity is if they take on perfectly tuned, quantized energy levels.
The solid world you are interacting with right now, your headphones, the device you are listening on, your own body, only holds together because of those boundary conditions. The pixels of the universe are an illusion, but these continuous waves arrange themselves into perfectly stable, trapped rhythms.
It really is an incredibly elegant mechanism. Nature uses continuous flow to enforce rigid structure.
But, Feynman leaves us with one final, very provocative detail in the text. He mentions that all of these beautiful, discrete energy levels only exist if the particle's energy is lower than the top of the crater.
Ah, yes.
If the particle has enough energy to rise above the potential well, there are no discrete solutions.
None at all. If the energy is higher than the edge of the valley, any continuous energy amount is perfectly permitted. The wave function doesn't get trapped. It doesn't form a standing wave. It just scatters off the atomic nucleus like a free particle flying through the void.
So I want to leave you with a thought to mull over. If the entire universe is essentially one massive system of interacting particles, all described by one incomprehensibly huge, multidimensional wave function,
Which it is.
are we living inside a perfectly tuned bound state? Or, on a cosmic scale, are we just part of an ongoing chaotic scattering event flying over the top of a universal potential well?
Now that is a fascinating question to ponder.
Let that chew on your mind the next time you zoom in on a digital photo. Thanks for joining us on this deep dive.
Imagine you leave a cup of hot coffee sitting on your desk. You implicitly trust that it's not going to just spontaneously gain a billion joules of energy and detonate.
Right, or suddenly launch itself sideways at the speed of sound.
Exactly. You trust that because you were taught the fundamental rules of the universe, the conservation of energy and the conservation of momentum. We picture these concepts as the absolute rock-solid bedrock of reality.
Yeah, they really are taught that way.
Right, it's almost as if the universe was born and the very first thing etched into the fabric of space was, "Thou shalt not create or destroy energy." We treat those laws as the starting point.
And in classical physics, I mean, they literally are the starting point. When you learn physics in high school, you build everything else on top of those unyielding foundation stones. You don't question why energy is conserved. You accept it as a brute fact of nature and run your calculations.
But what if that foundation is actually an illusion? What if those unbreakable laws aren't the starting point at all, but are actually just side effects?
That is the big question.
Yeah, so our mission for this deep dive is to explore an incredible stack of physics notes, specifically drawn from the legendary Feynman lectures, to uncover a massive paradigm shift in how we view reality.
It's a huge shift, yeah.
Because when you zoom down to the quantum level, it turns out conservation laws are the finish line, not the starting block. They are entirely derived from a hidden underlying architecture based on symmetry.
Which is wild to think about.
It really is. The fact that the universe simply doesn't change when you shift your perspective is what prevents your coffee cup from exploding.
It forces us to completely rewire our intuition. I mean, we are going to look at how moving a completely invisible mirror can dictate how the universe behaves.
Yeah.
And while the word quantum usually makes people brace for a flood of dense, incomprehensible math, the relationship between symmetry and conservation is actually surprisingly elegant.
It is, but before we can understand how symmetry actually creates a conservation law out of thin air, we have to define what symmetry means here.
Right, it's not the everyday definition.
Exactly, because I want you listening right now to clear your mind of the usual examples. We're not talking about a butterfly's wings looking the same on both sides or a perfectly round snowflake.
No, to get a grip on the quantum definition, let's pull a very specific physical system from the notes. The hydrogen molecular ion.
Okay.
Picture two identical protons with a single electron buzzing around between them. Now, construct an imaginary plane, a mirror cutting right down the middle, exactly halfway between those two protons.
So two protons, mirror perfectly dividing them.
Yeah, exactly. If you reflect the entire system across that mirror, whatever is on the left swaps to the symmetric position on the right, and vice versa.
Right.
You are physically swapping proton 1 and proton 2. But since protons are absolutely identical to one another, the physical system you are left with looks completely unchanged.
You literally couldn't tell the difference.
Exactly. It is indistinguishable from the original state. And in quantum mechanics, we call this a reflection operation.
Okay, let's unpack this and put it into motion. Suppose the universe is perfectly symmetrical in this way. We can set up a thought experiment, and I want you to visualize this timeline.
Okay, let's hear it.
In scenario A, we start the system, and we just wait. We let the system develop according to the laws of physics for, say, 15 seconds. The electron moves around, the state evolves. Then, after those 15 seconds, we apply that mirror reflection.
Right. And in scenario B, we reverse the order. We apply the mirror reflection first, right at time 0. Then we let the clock run for 15 seconds.
And because the underlying physics of the system are entirely symmetrical, the end result of both scenarios is identical.
Spot on.
Doing the wait and the mirror gives you the exact same universe as doing the mirror and then the wait. When the order of two operations doesn't change the final result, mathematicians say those operations commute.
And commuting is the linchpin of this entire framework. It's so important.
I always picture commuting like doing your laundry. If you put your dirty clothes in the washing machine and then add the detergent, that perfectly commutes with adding the detergent first and then putting your clothes in.
That's actually a great way to look at it.
Right. Either way, at the end of the wash cycle, you have a clean shirt. The sequence didn't destroy the outcome, but if you crack an egg into a pan and then turn on the heat to fry it, that does not commute with turning on the heat, frying an empty pan, and then cracking a raw egg onto a hot plate.
No, you get a completely different breakfast.
Exactly.
That laundry analogy highlights the mechanical truth of the physics. In a symmetrical universe, the passage of time commutes with the act of reflecting the system in a mirror. The order of operations just doesn't matter.
So we have an operation, the mirror reflection, that commutes with time. How does that leap into being a conservation law? I mean, how do we get from the order doesn't matter to a physical property cannot be destroyed?
Well, by looking at what happens to the state of the system over time. If a system starts in a specific state, let's say it has a certain phase or mathematical characteristic at time 0, and the operation defining that state commutes with the passage of time, then the passage of time cannot alter that characteristic.
Wow, okay.
Yeah, the system's evolution is completely blind to it.
Wait, let me make sure I'm translating this correctly. You are saying that if time and the mirror don't interfere with each other, then whatever property that mirror symmetry created is completely immune to the passage of time. It is locked in.
It is mathematically guaranteed to remain true forever, regardless of the chaotic, complex machinery happening inside the system. Even if the electron is doing a million unpredictable things, the overall symmetry is preserved.
That's incredible.
And a property that remains true forever, immutable against the ticking clock. That is the literal definition of a conservation law.
This brings us to the real everyday magic of this concept. Let's look at the holy trinity of classical physics, momentum, energy, and angular momentum. Because now that we know symmetry guarantees certain properties stay the same forever, we can completely rewrite the rulebook of why the physical world acts the way it does.
Let's do the grand translations, starting with space. Imagine taking an entire laboratory, all the equipment, the scientists, the coffee cups, you just displace it. You slide the entire room 3 miles down the road.
Okay, sliding the lab.
If the fundamental laws of physics do not change just because you move to a different spot in the universe, the math dictates that there must be conserved physical quantity, and that quantity is momentum.
Wait, I need to stop you there. Moving a box 3 miles down the road mathematically creates the conservation of momentum. You're going to have to walk me through how A leads to B, because that sounds like literal magic.
It does sound like magic, I know.
I take my coffee cup, I slide it across the desk. How does that dictate that momentum cannot be created or destroyed?
Well, let's strip away the physical cup and look at the invisible rules governing the space it occupies. If the rules of physics are identical at point A and point B, it means there is no underlying physical gradient in the universe. Space itself isn't subtly pushing or pulling on the cup just because it exists in that location.
Oh, I see. There's no hidden current in the void.
Exactly. Because space is symmetric, because it doesn't care where the cup is, there is no net external force generated by the vacuum. And without an external force, an object's momentum cannot change.
Wow.
The symmetry of space is what forbids the cup from spontaneously launching sideways. The conservation of momentum is just the physical manifestation of the universe's spatial apathy.
Spatial apathy. That makes so much more sense. Space doesn't care where you are, so it doesn't push you. No push equals conserved momentum. Let's apply that logic to the next one time. If displacing an object in space means momentum is conserved, what happens when we displace it in time?
Suppose you set up a chemistry experiment, but you delay starting it by 10 hours. If the external conditions in the universe don't change, the chemical reaction will play out identically 10 hours later.
Right.
The laws of physics don't have a calendar. This is the symmetry of displacement in time. And mathematically, this implies the conservation of energy.
Let's test that logic the same way we did with space. If the rules of the universe don't tick like a clock, if Tuesday's gravity is the same as Wednesday's gravity, there is no temporal gradient.
Exactly.
The universe isn't suddenly injecting extra force into my coffee cup just because it's 3.00 p.m.
Right, the Hamiltonian operator, which governs how a system's total energy evolves over time, does not depend on absolute time. Because the rules are constant from moment to moment, energy cannot be created or destroyed.
That's wild.
The conservation of energy is literally just the universe's profound indifference to what time it is.
Space symmetry equals momentum. Time symmetry equals energy. And there's a third pillar here, rotation.
Yeah, take that same laboratory and rotate it 90 degrees. The laws of physics don't care which way is north in an empty void. This rotational symmetry implies the conservation of angular momentum.
Okay, so far, this feels very theoretical. Beautiful, but abstract. Let's take that last one rotation resulting in angular momentum and test it on something tangible to see how the classical and quantum worlds actually collide.
Let's do it.
In the notes, Feynman uses the example of a beam of light. Let's talk about right circularly polarized light.
Light is the perfect arena to watch these frameworks overlap.
Yeah, because in classical physics,
Yeah.
right, circularly polarized light is essentially an electric field moving forward in a spiral, like a corkscrew. If you shine this corkscrew light at a physical wall, the electric field hits an atom in that wall and physically drives the atom's electron in a circle.
Pushing it.
Right. It does work on the electron, putting in energy, but because it's twisting, it's also applying torque. It is pouring angular momentum into the wall.
And the classical calculations show a strict, locked-in relationship here. The amount of angular momentum the light pours into the wall is directly proportional to the total energy it carries. The energy is inexorably tied to the twist.
So classical physics firmly states that rotating light carries angular momentum. How does that translate when we zoom down past the waves to the quantum level, where light is just a stream of individual, localized photon particles?
The translation is flawless, actually. In quantum mechanics, an individual photon is classified as a spin-1 particle. When a beam of light is perfectly corkscrewing, it perfectly matches the quantum mathematical requirement that every single photon in that beam carries exactly one fundamental unit of angular momentum.
Okay, but what if the light isn't corkscrewing at all? What if it's just standard linearly polarized light, like, the glare bouncing off a car windshield or the waves just moving up and down in a straight line? Where is the angular momentum then?
This is where it gets fun. Linear polarization is actually a 50-50 quantum superposition of that right-handed corkscrew and a left-handed corkscrew.
Wait, really? Both at once?
Yep. Every individual photon exists in a state where it has an equal probability of having a positive unit of angular momentum or a negative unit. When you measure a massive beam of this light hitting a wall, the positive twists and negative twists perfectly average out to zero net angular momentum.
Wow. But I need to flag something fascinating in the notes here because this is where the universe gets deeply weird. You mentioned a photon is a spin-1 particle.
It did, yeah.
Based on the quantum math we're looking at, any particle with a spin of 1 is required to have 3 possible states of angular momentum along any given axis. It should be able to spin clockwise for a +1 state, counterclockwise for a -1 state, or have a 0 state, +1, 0, -1, 3 states.
Yet when we measure light, we only ever find 2. We find the +1 and we find the -1. The 0 state is completely missing from reality.
Wait, why does light get a free pass to break a mathematical rule? Where did the 0 go?
This comes down to the physical limitations of mass. Angular momentum is a vector. It has a specific direction in space. For a particle to possess that 0 state of spin along an axis, the mathematics require that there must be a frame of reference where the particle can stand completely still.
Okay.
You have to be able to be at rest to have 0 spin relative to an observer.
But photons have 0 rest mass. By definition, light can never stand still.
Exactly. Because a photon is locked at the speed of light, its reference frame is entirely dictated by its forward motion. It can corkscrew forward or it can corkscrew backward. It is physically impossible for a restless particle to possess a state that represents 0 twist relative to a stationary axis.
So it just doesn't exist.
The universe enforces these rules of symmetry so strictly that if a particle is physically incapable of satisfying the condition to stand still, that quantum state is simply deleted from existence.
That is amazing. The rulebook is flawless. We have a perfectly balanced universe. Time gives us energy, space gives us momentum, rotation gives us angular momentum. It's a pristine, unbreakable mirror.
It is. Until it isn't.
Right. What happens when the universe actively decides to shatter its own mirror? The final section of these notes takes us to a scenario where nature suddenly develops a bizarre, lopsided flaw.
Yeah, we have to examine this strange case of the lambda 0 particle.
Imagine a subatomic particle called the lambda 0. It's highly unstable and it rapidly decays, essentially explodes into 2 smaller pieces of debris, a proton and a pion. This explosion is triggered by what physicists call the weak interaction, which is the weak nuclear force responsible for things like radioactive decay.
We need to carefully set the stage for this explosion to see the symmetry break. Let's take our lambda 0 particle and orient it so its internal spin is pointing straight up along the vertical z-axis. The lambda 0 has a spin of 1/2.
Okay, so the lambda spinning up, it explodes. The explosion shoots the newly created proton straight up along that vertical axis. To conserve momentum, the pion shoots straight down in the opposite direction.
Now we check the rotational books to ensure angular momentum was conserved during the blast. The pion, shooting downward, is a particle with a spin of 0. It carries away absolutely no angular momentum.
No, not at all.
Right. That means all of the rotational responsibility falls entirely on the proton shooting upward.
Since the original lambda was spinning up and the total angular momentum of the universe cannot magically flip directions, the proton must have its spin pointing up as well.
If the proton's spin pointed down, we would have created a massive violation of the conservation of angular momentum. The books balance.
But here is where we bring back our imaginary mirror. We talked about the reflection operation or parity. In the realms of electrodynamics and gravity, if you flip all the coordinates of a physical system to their diametrically opposite positions, like looking at the entire universe through a 3D mirror, nothing fundamentally changes.
Right. The laws of physics work exactly the same in the mirror world. Nature is symmetric.
If we apply that pristine mirror logic to our exploding lambda zero particle, parity dictates that the universe shouldn't have a preference for up versus down. If we run the experiment millions of times, the lambda zero should be equally likely to shoot the proton up as it is to shoot it down.
A perfectly symmetric universe demands a 50-50 split in the debris field.
The Feynman notes detail the exact expected distribution. We'd expect the protons to fly out uniformly. If nature were a perfect mirror, the directional preference would be exactly zero. The protons would shoot up and down in perfectly equal amounts.
But when physicists actually trap these particles and watch them explode in the laboratory, they do not see a perfectly equal distribution.
They measure the directional preference, and it is not zero. It is vastly skewed. The decay is incredibly lopsided, preferring one direction over the other by a massive margin.
The implications of that lopsided explosion are staggering. If the decay vastly prefers one direction, it means the 3D mirror is fundamentally broken. Parity is not conserved in weak interactions.
Which means the mirror universe cannot exist with our physics. If you looked at this decay in a mirror, a left-handed spin would look right-handed, and the particle's behavior would change.
Yeah.
For centuries, scientists assumed the universe was perfectly symmetrical across every force. But this proves that when it comes to the weak nuclear force, the universe actually has a built-in handedness. It is physically left-handed.
It is a profound shock to the system. You build this incredibly elegant framework where time symmetry flawlessly guarantees energy conservation and space symmetry flawlessly guarantees momentum. You watch light perfectly obey the math of angular momentum.
Right.
And then, hidden inside the radioactive decay of a subatomic particle, you find out nature has a subtle, undeniable bias.
It is the ultimate reminder that no matter how beautiful or mathematically perfect your theory is, you eventually have to look at the messy physical universe to see what it's actually doing. Which leads us to a final, slightly haunting concept drawn from these notes.
Oh, this part is great.
We've spent this entire deep dive establishing that symmetry is the hidden engine generating the rules of reality. Time symmetry gives us the conservation of energy. Space symmetry gives us the conservation of momentum.
And Feynman explicitly writes that quantum mechanics contains far more conservation laws than we ever use in classical physics. The rule is absolute. Any invisible operation, any subtle mathematical shift that commutes with the passage of time mandates the existence of a conservation law.
We spend our lives relying on the obvious rules, energy, momentum, angular momentum, because they govern the things we can easily see, measure, and bump into. But if every single quantum symmetry creates an unbreakable law of conservation, I want you to think about the greatest unresolved mysteries in science today.
Like dark matter.
Exactly. Take dark matter or dark energy. We observe galaxies spinning too fast or the universe expanding too quickly, and we assume there must be invisible stuff out there causing it. Invisible mass. Invisible forces.
But what if we were looking at it entirely backwards?
What if dark matter isn't a thing at all? What if the bizarre behaviors we see in the cosmos are simply the strict enforcement of bizarre, undiscovered conservation laws? What if there is a massive, universe-wide symmetry, a mirror we haven't even conceived of yet, that is silently operating right in front of our eyes, locking in physical properties that humanity hasn't figured out how to measure?
The rules of reality might not be etched into stone. They might just be reflections in a mirror we haven't quite learned how to look into yet. You know, if you crack open the back of a mechanical watch, the sheer complexity of it just hits you right away.
Oh, absolutely. It's instantly mesmerizing.
Right. You see these tiny brass gears spinning and the teeth are locking together in this like perfect, intricate dance.
Yeah.
And it just makes total sense to our human brains.
Yeah, one gear turns clockwise, so it physically forces the next one to turn counterclockwise. It's very intuitive.
Exactly. It's mechanical, it's visible, and honestly, it is deeply comforting. But today, we are leaping into a world where all those gears are, well, completely invisible. And yet they are dictating absolutely everything around you.
Right. And unlike a watch where you can, easily see a gear spinning left or right, the gears we are looking at today are entirely abstract.
Yeah, because we are diving into Chapter 18 of the legendary Feynman Lectures on Physics, Volume 3, which is a massive source text, by the way.
It really is. It's a dense, math-heavy exploration of the quantum rules of angular momentum. We're basically looking at how subatomic particles spin, how they interact, and fundamentally how they conserve their rotational energy.
Right. It is definitely a hefty piece of physics to get through. But our mission for this deep dive is to take all of Feynman's brilliant, dense equations and translate them into a conceptual journey.
Exactly.
We're going to explore the hidden rules of this quantum angular momentum. We want to show you how the invisible spinning nature of subatomic particles is actually the master key to understanding reality. I mean, we are talking about everything from why the sky above your head is polarized to the profound, mind-bending paradoxes of quantum entanglement.
And the foundational belief we need to hold on to as we unpack those, the thing to remember is that knowing what the math says is only half the battle. Knowing why these quantum rules physically manifest the way they do, that is what truly unlocks our understanding of the universe.
Okay, so let's start with the absolute simplest interaction possible, just to get a feel for how these invisible gears actually mesh.
Sounds good. Let's imagine a single atom floating in a void.
Okay, a single atom.
Right, and it's sitting there in an excited state, meaning it has extra energy, and let's say it has a quantum spin of 1.
Got it. So it wants to drop down to a more relaxed ground state, which has a spin of 0. And to shed that extra energy, it has to spit out a single photon of light.
Exactly. Now let's give that atom a specific orientation. Say its angular momentum is pointing straight up along what physicists call the positive z-axis.
So its quantum number, the m value, is +1.
Right. When it drops to the spin 0 state, it emits a photon straight upward. And according to the strict quantum rules Feynman lays out, that upward photon absolutely must be, circularly polarized or RHC. It cannot be anything else.
Okay, let's unpack this. Why does it have to be, circularly polarized? I feel like it helps to think of a physical analogy here.
Oh, analogies are great for this.
So imagine an ice skater, right? They're spinning rapidly on the ice with their arms pulled in tight. Suddenly, they pull out a heavy bowling ball and throw it straight up into the air.
That's a great visual.
Right. If that ball leaves their hands with its own spinning motion, the skater's rotation has to physically slow down or even change direction to compensate for the spin that the ball just carried away. The total amount of spin in the ice rink has to remain constant.
And that classical analogy maps beautifully to the quantum rule of conservation of angular momentum. The right circularly polarized photon carries exactly +1 unit of angular momentum away with it.
So because the atom started with +1 and the photon packs up and leaves with +1, the atom is left with exactly 0.
Exactly. The universe's ledger is balanced. If the atom had tried to emit a left circularly polarized photon, which carries -1 unit of angular momentum, the atom would have to end up with a spin of +2 to compensate.
But we already established it's dropping to a state of 0.
Right. The math simply doesn't add up, so the universe forbids it from happening.
Okay, that makes sense. But our sources also dive into how physicists figure out the probability, like the amplitude, for different types of these light emissions. And they don't just measure it, they use symmetry. But they talk about changing the atom's parities. What does that actually mean in a physical sense?
It's a really profound thought experiment. Imagine taking that exact atom emitting a photon and you play it back in a mirror. But you don't just reverse left and right, you also flip up to down and front to back.
Whoa. So you're basically turning physical space inside out.
Precisely. This is what physicists mean by changing parities. Because atomic processes fundamentally conserve parity, meaning the universe should work the exact same way even if it's turned inside out. A beautiful symmetry emerges in the math.
So it's like discovering a hidden mirror world where the rules are reversed but equally strict.
That's a perfect way to put it. In this specific case, the atom goes from an odd initial state to an even final state. So the math reveals that the probability for an atom with a downward spin in m equals -1 state to emit a left circularly polarized photon upward is exactly the negative of the probability for our original upward spinning atom to emit its right-handed photon.
So the universe literally balances its books through this inside-out symmetry. That is wild.
It really is.
Okay, so the math works perfectly for a stable atom spitting out a photon in a void. But this isn't just about isolated particles, right? These exact same invisible gears turning are what give us the blue sky above our heads.
Yes, let's move from an atom emitting light to what happens when an atom gets hit by light.
This is a two-step process called scattering, right? The text references figure 18-4 for this setup.
Exactly. Imagine a photon comes flying in from the bottom, traveling along the negative z direction. It strikes an atom that is sitting quietly in its ground state.
And the atom absorbs the photon, which temporarily knocks the atom into an excited spinning state. So it becomes either m equals +1 or -1.
Right. And almost instantly, the atom spits a new photon back out at some random angle, which we'll call theta.
Now, this is where we have to talk about polarization. If you shine a beam of linearly polarized light, say light polarized flat, along the x-axis at this atom, you might think of it as just a flat wave.
You might, classically. But in the quantum realm, this linear beam is actually a quantum superposition. It is a perfect equal mixture of right circularly polarized and left circularly polarized light, just overlapping.
And when Feynman crunches the quantum amplitudes for these overlapping circular polarizations, the result is kind of stunning. He calculates the probability of where that scattered photon will actually go.
Yes, and he proves that the x-polarized light scatters with an intensity that is proportional to the square of the cosine of the angle theta.
And even more surprisingly, the light that scatters out remains completely x-polarized.
It's a huge triumph in the math.
But wait, I have a question here. If we look back at Volume 1 of Feynman's lectures, the classical model of physics gives us the exact same, completely correct answer for how light scatters and why the sky is polarized.
Right, the old classical model.
Yeah. Back then, they just pretended the electron in the air molecule was a tiny mass attached to a linear spring, just bouncing up and down. If the old classical spring model gives us the exact same answer, why are we dragging you, the listener, through all this intense quantum math?
That is a fair question. It's because quantum mechanics validates why that classical shortcut worked in the first place. Nature isn't actually made of tiny springs, you know.
Obviously not.
The classical model only works by a remarkably lucky mathematical coincidence for this specific type of atom, which happens to have a spin of 1.
Ah, so it's a fluke.
Total fluke. If the excited atom in the atmosphere had a spin of 2 instead of 1, that classical spring model would completely fall apart. It would give you an utterly wrong prediction for the polarization of the sky.
So the quantum math, superimposing the right and left circularly polarized light, that's the actual truth of the machinery.
Exactly.
Like the classical physics is a cheat code that only works on the first level of a video game, but quantum mechanics is the actual source code for the entire universe. They love that.
It's a perfect analogy.
Now let's look at a system where that source code produces something completely bizarre. What happens when the gears are rigged to literally obliterate themselves? Let's talk about positronium.
Oh, positronium is a fascinating system. It is essentially an atom, but instead of a heavy proton in the center with a tiny electron orbiting it, you have an electron orbiting a positron.
And a positron is the exact antimatter counterpart to an electron, right?
Right. It has the exact same mass, but a positive charge.
It's an atom built out of matter and antimatter. That means it is doomed from the moment it is created. It has energy states just like a normal hydrogen atom, but the magnetic interaction between the two particles is incredibly intense. It's like 1,000 times stronger.
And it cannot last. It destroys itself. The matter and antimatter annihilate each other, converting all their mass into pure energy, which bursts outward as photons.
And how fast does that happen?
Well, if the positronium is in its spin-zero ground state, it annihilates into 2 photons in about 1/10,000,000th of a second, just gone.
Wow.
But interestingly, if the positronium is in a spin-1 state, it survives 1,000 times longer before disappearing.
Wait, really? Why does a simple change in spin make it live 1,000 times longer?
It comes back to that strict accountant of the universe, conservation of angular momentum. A spin-1 state simply cannot decay into 2 photons and still conserve its initial spin. To make the math balance, it is forced to decay into 3 photons.
And I'm guessing 3 photons is harder to pull off.
Much harder. Creating 3 outgoing photons is a much more complex and therefore much rarer quantum process. It literally takes the universe longer to make it happen.
Okay, let's focus on that faster 2-photon decay from the spin-zero state, because this is where reality gets genuinely weird. To conserve angular momentum, if the photon shooting upward is, right, circularly polarized, the photon shooting downward must also be circularly polarized.
Right. Or alternatively, they could both be left circularly polarized.
And because the positronium system as a whole has odd parity, the true final quantum state is actually a mathematical subtraction of these 2 possibilities.
Yes.
Hold on. Subtracting possibilities. To a listener, subtracting one pair of photons from another just sounds like abstract nonsense.
Yeah.
How does a physical state subtract itself?
Think of it like destructive interference or, noise-canceling headphones for probability.
Okay.
The universe has 2 options, the right-handed pair and the left-handed pair. Instead of just adding them together, the quantum wave function of one possibility overlaps with the negative wave function of the other.
So they sort of cancel each other out in specific ways.
Exactly. This specific subtracted mathematical state is the only way to guarantee that parity, that inside-out symmetry we talked about, is conserved during the explosion.
And this brings us straight to the climax of this strange behavior, the famous Einstein-Podolsky-Rosen paradox, or the EPR paradox.
Yes, the classic thought experiment.
Right. So if you stand on one side of this decaying positronium atom with a calcite detector rigged to measure X polarization, and you get a hit, you instantly have a 100% probability of knowing that the other guy, standing on the far side of the room with his own detector, will get a hit in his E-polarized detector.
Right. It implies a spooky, instantaneous correlation across space. Measuring one photon seems to instantly dictate the state of the other, no matter how far apart they are.
Now here's where it gets really interesting. Let me play devil's advocate here. Think about a pair of loaded dice.
Okay.
If I rig 2 dice so that they always roll a combined total of 7, and I throw one to you and keep one for myself, if I roll a 3, I instantly know you rolled a 4, even if you're in the next room.
Sure, because the outcome was predetermined.
Right. So doesn't the positronium just create a predefined right-handed or left-handed pair at the very start, like loaded dice? Meaning our observation doesn't actually change anything, we just uncover what was secretly there all along.
It is incredibly tempting to think of it that way. I mean, Albert Einstein desperately wanted it to be that way.
Right, because it makes intuitive sense.
It does, but Feynman uses strict logic in these lectures to completely dismantle the loaded dice idea. In classical physics, yes, the dice have a defined state tumbling through the air completely hidden from us, but nature, at the quantum level, requires a description strictly in terms of interfering amplitudes.
Yeah, they must have a physical spin as they travel through space, right? We just haven't looked yet.
That is our classical brain demanding the universe make sense. But until a measurement is made, those photons do not have a defined polarization. They exist purely as an overlapping wave of probability. They are simultaneously right-handed and left-handed.
So they aren't secretly one or the other.
They are neither and both. The measurement itself is what forces the universe to pick an outcome. Making a measurement actively destroys the interference pattern.
Wow.
Yeah, if they were just loaded dice with hidden states locked in from the start, we wouldn't see the specific shifting interference patterns that quantum mechanics predicts when we change the angles of our detectors. The EPR paradox only feels like a paradox because we expect reality to be locked in before we look at it. Nature doesn't care about our expectations.
Nature plays by her own rules.
Oh.
Okay, so we've been swimming in some deep philosophical waters with antimatter and paradoxes. Let's bring this down to earth a bit.
Good idea.
How do physicists actually use these invisible quantum rules in a laboratory setting? Because they do use them, right? To see the unseeable inside a nucleus.
They absolutely do. The sources detail a beautiful real-world application, J.A. Kuhner's 1962 experiment. This is a masterclass in using applied angular momentum as a forensic tool.
Yes, the text references figures 18-9 and 18-10 for this. Scientists basically set up a subatomic shooting gallery.
That's a good way to describe it.
They bombarded a very thin carbon foil with a high-energy beam of carbon-12 ions. And this massive collision forces the atoms to fuse, creating a highly excited, extremely unstable atom called neon-20.
And this neon nucleus is so unstable that it almost immediately spits out an alpha particle as shrapnel.
Right. But what makes this brilliant is how they control the initial collision.
Yeah.
Carbon-12 and alpha particles both happen to have a quantum spin of exactly 0.
Exactly. Therefore, all the angular momentum in this entire violent system is highly restricted. Because the initial carbon beam comes flying in straight along the z-axis, the resulting tumbling neon-20 nucleus is mathematically forced to have absolutely 0 angular momentum about that z-axis. Its M quantum number is dead 0.
It really is like forensic ballistics. We can't actually see the spinning neon nucleus before it decays. I mean, it is far too small and it disappears far too fast. But by placing a detector at various angles to catch that alpha particle shrapnel flying off, we can reconstruct the exact quantum spin state of the invisible nucleus.
That is precisely what Kuhner did. By plotting the intensity of the alpha particles hitting the detectors at different angles, they created a scatter curve. And the shape of this curve perfectly matched a set of mathematical functions known as the squares of Legendre polynomials.
Wait, Legendre polynomials? That sounds like abstract math trivia. Why do these specific math functions matter to the physical shrapnel?
Well, think of a Legendre polynomial not as an abstract equation on a chalkboard, but as a three-dimensional probability map. For a completely spinless system, the probability map is just a perfect sphere. The shrapnel could go anywhere equally.
Makes sense.
But when the nucleus has a specific quantum spin, the map changes shape. The first Legendre polynomial, which corresponds to a spin 1 state, looks almost like a dumbbell.
Ah, so it physically restricts where the alpha particle can travel.
Exactly. If the invisible neon nucleus has a spin of 1, the math dictates that the alpha particle is highly likely to fly out along the poles of that dumbbell shape and has virtually zero probability of flying out along the equator.
And the data perfectly reflected that. For the neon state excited to 5.80 MeV, the shrapnel pattern perfectly matched that dumbbell-shaped first Legendre polynomial, proving it was a spin 1 state.
Right.
But when they looked at the 5.63 MeV state, the scatter pattern shifted entirely. It matched the third polynomial, which has a much more complex, wavy probability map with multiple lobes. This proved it was a spin 3 state. They essentially read the invisible fingerprints of the atom just by looking at where the pieces landed.
It is a remarkable piece of deductive reasoning. It relies entirely on the strict, unbreakable conservation of angular momentum. We simply couldn't map the strong nuclear forces that hold matter together without using this technique.
So we've looked at single spins, and we've used nuclear spins to solve forensic mysteries. But the universe isn't just isolated particles popping in and out of existence. It is made of massive interacting pieces.
Right, everything interacts.
So to round out this deep dive, we need to look at how these quantum spins combine to build larger structures.
The architecture of particle physics is entirely built on combinations. Let's look at a slightly more complex atom, deuterium. It consists of a single electron orbiting a deuteron nucleus.
Okay.
Now, the electron is a fundamental particle with a spin of 1/2. The deuteron, which is actually a proton and a neutron bound together, acts as a single combined unit with a spin of 1.
So how many total quantum states exist for this new combined deuterium system? The math is actually just simple multiplication. The electron has 2 possible states, spin up or spin down. The deuteron has 3 possible states. 2 times 3 gives us 6 possible combined states for the deuterium atom.
And finding the total z component of angular momentum for the new system, which we call capital M, is also straightforward. You simply add them together. The m of the electron plus the m of the deuteron equals the total m.
Right, so the maximum total spin of the whole system, the J value, is just 1 plus 1/2, which equals 3/2. This spin 3/2 state accounts for 4 of our 6 possible combinations. The remaining 2 combinations group together to form a spin 1/2 state.
But the real magic, the true hidden machinery, reveals itself when we look at exactly how these states mix together. Feynman introduces what are called Klubbs-Gordon coefficients.
Okay, that sounds intimidating.
It sounds worse than it is. These are specific numbers, often involving square roots like the square root of 2/3 or the square root of 1/3, that dictate the exact recipe required to blend the spins. They tell you precisely how much of each original particle state is needed to build the new combined quantum wave function.
So what does this actually mean for reality? Are these Klubbs-Gordon coefficients just complex mathematical bookkeeping to keep the physicists' equations balanced?
No, they are far more profound than just bookkeeping. These coefficients are the fundamental blueprint of the universe. The mathematical rules for adding a spin 1 particle to a spin 1/2 particle are completely universal.
Universal in what way?
It does not matter if you are adding an electron to a deuteron in a laboratory, or combining exotic quarks inside a particle accelerator, or looking at processes happening in the core of a distant star. The underlying recipe, the strict proportions required by the universe to combine angular momentum, remain exactly the same. The math is the physical reality.
That is incredible. The invisible gears are all cut to the exact same universal standard no matter where you go.
Exactly.
So let's take a breath and look back at the sheer scale of the journey we've just been on. We started with a single atom spitting out a photon, and we used an ice skater throwing a heavy ball to physically visualize the conservation of spin.
We did.
And we use that exact same invisible gear turning to explain why the sunlight scattering through the blue sky is polarized. We waded into the antimatter destruction of positronium and dismantled the loaded dissolution of the EPR paradox.
It's been a busy session.
Very. We used angular momentum probability maps to read the spin of smashed neon atoms. And finally, we uncovered the Klubbs-Gordon coefficients, the universal recipes that combine spins to build the universe itself.
It is an expansive amount of ground to cover. And it leaves us with something quite deep to ponder, particularly returning to our discussion of positronium.
Oh, I like where this is going.
Well, if the universe fundamentally operates on interfering amplitudes, if photons literally do not have a defined physical state until they are forced to pick one by a measurement, and if measuring one particle instantly defines the state of another particle far across the room.
Right, because making that measurement physically destroys the interference pattern for both of them.
So then it raises a deeply unsettling question. Is the classical boundary between you, the conscious observer making the measurement, and the universe you are observing just an illusion? An illusion created by the bluntness, the sheer macroscopic size of our tools. Because at the quantum level, the math suggests that the act of interacting with the system is what forces the gears to lock into place and become real.
It makes you wonder what the mechanical watch actually looks like when the back is closed. And absolutely no one is looking at the gears. Thank you so much for taking the time to explore this incredibly complex material with us. Keep questioning the invisible mechanics around you.
You know, when you pour yourself a glass of water, there is this immediate, undeniable expectation of reality. It is heavy in your hand, it splashes, it is wet.
Right, it feels entirely perfectly solid and normal.
Exactly, but if you were to actually zoom in, like past the macroscopic illusion, that solid reality completely dissolves. You realize the seemingly solid world around you is secretly governed by invisible, oscillating probability clouds.
It forces a total shift in how you process the physical world. I mean, we are so accustomed to trusting our classical senses, the things we can actually touch and measure directly.
But the underlying machinery of that water is operating on a set of rules that completely defy those classical instincts. And that is exactly our mission for your deep dive today.
Oh, definitely. We are looking at a truly foundational text today, an excerpt from the legendary Feynman Lectures on Physics, specifically Volume 3, Chapter 19.
And I have to warn you, if you were to open these pages, you'd be confronted with some incredibly dense physics. We are talking complex mathematical proofs, massive integrals.
And figures that look a bit like modern art, honestly.
Very true. But we aren't here to just walk through a textbook or get bogged down in the algebra.
Right, because the goal isn't to memorize the mathematical steps. The goal is to understand the physical reality those steps represent.
Okay, let's unpack this. We are going to decode how a single, highly abstract piece of math, the Schrödinger equation, manages to explain everything. From the layout of the periodic table on your high school chemistry wall to the literal physical angle of the water molecules in your glass.
By the end of this, you're going to look at that simple glass of water with an entirely different perspective.
So where do we begin?
Well, to get to that macroscopic glass of water, we have to start at the absolute baseline. Before we can begin to comprehend a complex system like a carbon atom or a diamond or a human cell, we have to master the simplest possible sandbox in the universe.
A hydrogen atom.
Exactly. One proton, one electron.
But even with just two particles, Feynman points out that to make the math workable, physicists have to make a few clever approximations right out of the gate.
They do, yeah. You simply cannot calculate everything at once.
Right, like, for instance, because the proton is roughly 1,800 times more massive than the electron, the math treats the proton as if it's completely fixed and stationary at the center.
Yes, the infinite mass approximation.
And they also strip away the electron spin and any relativistic effects. They essentially treat the electron like a simple point mass moving through space.
Those approximations are necessary because even in this simple two-body system, the Schrödinger equation is a demanding piece of calculus. It is fundamentally a differential equation.
Balancing the kinetic energy of the electron against the potential energy pulling it toward the nucleus, right?
Exactly. And to solve it, the first thing the math forces us to do is completely throw out the standard Cartesian coordinate system.
Oh, you mean the X, Y, and Z grid we all learned in grade school geometry, up, down, left, right?
Yeah, that grid is useless here. The problem is the electrical pull of the proton radiates outward in a perfect sphere.
Right, so if you try to measure the electron's distance from the center using X, Y, and Z, you end up having to use the Pythagorean theorem inside your calculus.
Which means plugging the square root of x squared plus y squared plus z squared into a differential equation.
Which is a massive algebraic nightmare.
It makes separating the variables practically impossible. So the mathematical solution is to adopt spherical polar coordinates.
And this is shown in figure 19:1 of the Feynman text, right?
Yes. Instead of a rigid grid, you measure the radius labeled r directly outward from the center. Then you use two angles, theta and phi, to locate the specific point in three-dimensional space.
So it maps perfectly to the spherical symmetry of the atom's electric field.
Exactly. And when you run the Schrödinger equation through these spherical coordinates, looking specifically for states where the electron has zero orbital angular momentum, the math spits out these beautifully simple natural atomic units.
Ah, the SES states. With the mayas conveniently standing for spherically symmetric.
Yes, the equation gives us the characteristic distance the electron settles into. That is known as the Bohr radius, which is about 0.529 angstroms.
Which is incredibly tiny.
Very tiny. And it gives us the energy of this lowest state, the Rydberg energy. That drops out as exactly negative 13.6 electron volts.
Wait, negative? What's fascinating here is that the negative sign on that energy value carries profound physical meaning.
It does.
Yeah.
It is not just an arbitrary minus sign on a chalkboard. It literally dictates the existence of matter.
Exactly, because for anyone visualizing this, that negative number simply represents a bound state.
Right. If zero energy is an electron floating freely out in the void, completely unattached to any atom, then as it gets pulled toward the proton, it falls into an energy well.
Its energy goes negative. So at negative 13.6 electron volts, it is stuck at the bottom of a steep quantum hole.
You would literally have to inject 13.6 electron volts of energy into the system just to pull that electron out and set it free.
That energy well is what keeps the universe from just disintegrating into loose particles.
Exactly. But we have to be careful about how we picture that electron at the bottom of the well, because it is not just a tiny marble sitting still.
And it is not orbiting in a neat circle like a planet around the sun either.
Yo, not at all.
Here is the analogy I find most helpful for visualizing this. Instead of a planet on a track, imagine the electron as a probability cloud.
Oh, I like that.
Think of it like a blurry photograph taken with a remarkably long exposure time. The electron is moving so fast, and its position is so governed by quantum uncertainty that it just forms a fuzzy sphere of varying density around the proton.
And the density of that blur at any given spot represents the mathematical likelihood of finding the electron exactly there.
Right. The math of the Schrödinger equation perfectly formalizes that blurry photograph.
It does. If you map the probability density for this lowest energy ground state where the principal quantum number n equals 1, the amplitude is highest directly at the center, right on top of the proton.
But as you move outward, extending the radius r, the probability drops off exponentially. It just fades out into a thinner and thinner fog.
So that is our baseline, a perfectly spherical, dense fog that fades as you walk away.
But that is only when the atom has zero orbital angular momentum.
Right.
The moment the atom does have angular momentum, the moment the electron has quantum spin and movement beyond that baseline state, the math entirely alters the shape of the cloud.
This brings us into the realm of the quantum numbers L and M.
Okay, so let's break those down.
Well, the quantum number L dictates the total orbital angular momentum of the system, and M represents its spatial orientation along a specific axis.
And this is where we get those famous subshell letters, right? Like S, P, D, and F.
Yes, exactly.
The Feynman text actually includes this brilliant piece of historical context. Before physicists had any conceptual model of quantum mechanics, early spectroscopists were looking at the distinct lines of light emitted by different atoms.
And they categorized those lines as sharp, principal, diffuse, and fundamental.
Which is wild because they were completely blind to the underlying physics.
They really were. They were categorizing the shadows on the cave wall, basically assigning letters to the visual light patterns. And this was decades before the Schrödinger equation proved that those letters actually correspond to distinct quantum states.
With different angular momenta, it is amazing that the nomenclature survived.
It is. But when you look at the physical shapes of these higher states, the P states and D states, they are utterly bizarre.
Oh yeah, figures 19 to 5 and 19 to 6 in the text illustrate this perfectly. They aren't spheres at all.
No. The P states look like dumbbells, or like two separate balloons tied together at the nucleus.
And the D states look like four-leaf clovers. And cutting through these shapes are what the text calls nodal surfaces.
Nodal surfaces are vital to the architecture of the atom. These are specific geometric planes, or sometimes cones, in 3D space where the probability of finding the electron drops to absolute zero.
A literal wall of mathematical nothingness cutting right through the probability cloud. And the fascinating detail about these higher angular momentum states, any state where RL is greater than 0, is that the probability amplitude is always exactly 0, right at the center point.
Right at the nucleus.
So the electron is never at the core. The text explains this mathematically by showing how the Schrödinger equation generates a pseudopotential term.
Right, a term that acts like a centrifugal force.
Wait, so the math just invents a pseudopotential centrifugal force?
What's fascinating here is that if we connect this to the bigger picture, it mirrors classical mechanics beautifully, even within a quantum system.
How so?
Think about swinging a heavy bucket of water in a circle on a rope. The angular momentum creates a centrifugal barrier. It physically pushes the water outward, away from your hand at the center.
So the math actually mimics that classical physics concept.
Yes. Because the electron has angular momentum, the equation introduces a term specifically proportional to L times L plus 1 over R squared.
And that essentially functions as a barrier?
It physically forbids the electron from occupying the center point, pushing the probability cloud outward into those dumbbell and clover shapes.
Wow. So that pseudo-potential barrier is the underlying reason atoms have size and structure.
It is. But hydrogen is just the starting line. The moment you drop a second electron into that perfect spherical sandbox, the mathematical elegance shatters.
Right, because the universe isn't a vacuum filled with solitary hydrogen atoms. You and I and the desk and the listener tuning in, we are made of carbon, oxygen, calcium.
But transitioning from one electron to the 100-plus elements of the periodic table represents a massive mathematical wall.
I think physicists call it the many-body problem, right?
It is notoriously known as the many-body problem. Solving the precise Schrödinger equation for a system with 3 or more interacting electrons is analytically impossible.
Impossible. Not just hard.
Practically impossible. You have the nucleus pulling the electrons inward, but you also have every individual electron violently repelling every other electron. The variables become infinitely tangled.
So rather than giving up, physicists rely on what Feynman explicitly calls a sloppy approximation.
And I just love that term in rigorous physics.
It is so good, a sloppy approximation.
But it is a very systematically justified sloppy approximation.
Okay, so how does it work?
Well, instead of trying to calculate the exact instantaneous repulsion between every single electron at every fraction of a microsecond, physicists treat each electron as if it is moving independently within an average central field.
They average out the chaos.
Exactly. They assume a specific electron feels the strong, attractive pull of the central nucleus, minus a blurry, generalized pushback from the swarm of all the other electrons combined.
And when you pair that central field approximation with the Pauli exclusion principle, the entire architecture of the periodic table unlocks.
Right. And for anyone listening, the Pauli exclusion principle is the fundamental rule that you can only fit 2 electrons, one with spin up and one with spin down, into any single quantum state.
No 2 electrons can share the exact same set of quantum numbers.
Right. To see how this sloppy approximation and the exclusion principle build the universe, let's compare 2 early elements, helium and lithium.
Helium is the perfect baseline for this. It has 2 electrons.
Following the rules, they both drop down into the lowest possible state, that spherical one's shell.
And because there are no inner electrons between them and the nucleus, they feel the full, unmitigated positive charge of the protons.
They are bound incredibly tightly. The ionization energy, which is the energy required to tear one of those electrons away, is a massive 24.6 electron volts.
Which means helium is incredibly protective of its electrons. It absolutely refuses to interact or share them.
Which is the physical reason helium is a noble gas. It is completely chemically inert.
But the second you add one more proton and one more electron to create lithium, the dynamic completely shifts.
It has to. Because of the Pauli exclusion principle, that one shell is totally locked. It is full.
So that newly added third electron has nowhere to go but the next energy tier up, the 2's state. Here's where it gets really interesting. A great way to visualize this for anyone listening is to picture these electron shells like a crowded concert venue.
Oh, I like this analogy.
So the one section is the VIP pit, right up against the stage. The stage is the nucleus. That pit only holds 2 people, and for lithium, it is sold out.
Right.
So the third electron is forced to sit in the 2's section, which is a row further back. But the real problem is that the 2 electrons in the VIP pit are negatively charged, just like the 2's electron. So they are actively pushing back against it.
They effectively shield that outer electron from feeling the full attractive pull of the stage.
Yes, that shielding effect, what physicists call the effective nuclear charge, is the driver of all chemistry.
Because that inner layer is repelling it, the third electron in lithium is barely holding on. Its ionization energy plummets from 24.6 down to just 5.4 electron volts,
It requires almost no energy to knock it loose.
which translates physically to lithium being a highly reactive alkali metal. It is constantly looking to ditch that outer electron.
And as you move further across the periodic table, this interplay of energy states and electron repulsion creates some fascinating anomalies, like consider nitrogen and oxygen.
The standard logic says that as you add more protons to the nucleus, the magnetic pull gets stronger and the electrons should be held tighter.
Right, a stronger central magnet should mean a higher ionization energy.
Generally, that holds true, but oxygen actually has a noticeably lower ionization energy than nitrogen, which breaks the expected sequence.
Wait, really? Lower?
Yes, and the reason for that anomaly ties directly back to the geometries we talked about earlier.
Okay, let's walk through that. In nitrogen, you have 3 electrons filling the outer 2p shell.
And because the math of the p state creates 3 distinct spatial orientations, the x, y, and z's axis, each of those 3 electrons gets its own private suborbital.
They don't have to share space.
But when you step up to oxygen, you have a 4th outer electron, and you have run out of vacant axes.
Ah, this raises an important physical reality. That 4th electron in oxygen is forced into a suborbital that is already occupied by another electron.
You suddenly have 2 negatively charged particles confined to the exact same tight quantum space.
They violently repel each other.
Precisely. That mutual repulsion creates a localized high-energy tension. It pushes that 4th electron slightly outward, making it much easier to strip away than the independent electrons in nitrogen.
Wow. So it is all a balancing act to minimize repulsion.
It is. And this identical mechanism, this battle between nuclear attraction, quantum angular momentum, and electron shielding, explains the macro structure of the periodic table.
It is why the 4's shell famously fills with electrons before the 3rd shell, as highlighted in figure 19-8 of Feynman's text.
Which is a detail that always frustrated chemistry students, because it feels like skipping a numerical tier. You would assume the 3 level would completely fill before the 4 level begins.
It seems counterintuitive until you factor in the pseudo-potential centrifugal force we discussed earlier.
Right. The 3rd state has so much angular momentum that the mathematical barrier pushes its probability cloud significantly outward, away from the nucleus.
It is pushed so far out and shielded so heavily by the inner layers that its overall energy level actually ends up sitting slightly higher than the larger but spherically penetrating 4's state.
The electrons simply flow into the path of least resistance, filling the 4's first.
This architecture also explains why elements stacked in vertical columns like neon, argon, and krypton exhibit nearly identical chemical behaviors.
Even though they have vastly different atomic masses, their outermost concert rows have the exact same quantum geometry.
They present the same mathematical face to the universe.
That is a great way to put it.
So we have mapped out the energy architecture of these elements. We understand the shielding, the repulsion, the anomalies, but I want to tie this all the way back to the beginning of the deep dive.
The glass of water.
Exactly. We started by talking about the heavy, wet reality of a glass of water. Feynman takes this theoretical physics and maps it directly onto physical reality. How do these abstract mathematical clouds dictate the tangible geometry of a molecule?
This is the ultimate synthesis of the math. These SP and D probability clouds aren't just abstract ledgers of energy. They are physical maps of three-dimensional space.
The geometry of the wave function determines the literal angles of chemical bonds.
So let's actually build a water molecule from scratch using these quantum rules.
Okay, let's do it. We start with our central oxygen atom. We know it has 4 electrons in its outer 2p shell.
As we established, the math provides 3 available substates for those electrons: the x-axis, the y-axis, and the z-axis.
2 of those electrons pair up and share one axis, but that leaves 2 vacant slots, let's say on the x-axis and the y-axis.
Each of those vacancies represents an unbalanced electrical field. When oxygen encounters 2 hydrogen atoms to form H2O, those hydrogen atoms are drawn in to share their electrons and fill those specific x and y vacancies.
It allows the whole system to settle into a much more stable, lower energy state.
But the key is that mathematically, the x and y axes are strictly perpendicular. They exist at exactly a 90-degree right angle to one another.
So if we strictly follow the geometry of the probability clouds, those 2 hydrogen atoms should lock into the oxygen atom, forming a perfect 90-degree corner.
And you see this same geometric rule govern other molecules too. Take ammonia, for example, NH3.
Nitrogen has 3 vacant slots in its outer shell, one for each axis, X, Y, and Z.
So it bonds with 3 hydrogen atoms, and because the axes are orthogonal, they form a perfect 3D corner, with each bond mathematically set at 90 degrees.
And this structural reality, the fact that ammonia forms a rigid pyramid rather than lying flat, is the exact quantum property that allows the ammonia maser to function.
Which is incredible. But back to water.
Right. The fascinating paradox here is that anyone who has looked at a physical ball and stick model of a water molecule knows it is not bent at a perfect 90-degree angle.
It is actually bent at approximately 105 degrees.
So there is a clear tension between the perfect 90-degree mathematical template of the P state and the physical reality of the water in our glass. Did the math fail?
No, not at all. To resolve that tension, you have to look at the holistic physical system, not just the isolated geometry.
What do you mean?
When those 2 hydrogen atoms attach to the oxygen's X and Y axes, they're sharing their negatively charged electrons with the oxygen core.
Right.
But that leaves the hydrogen nuclei themselves, which are simply naked, positively charged protons, somewhat exposed on the outer edges of the molecule.
Oh, and because they are both carrying a net positive charge, they fundamentally repel each other.
Exactly. You have 2 positive poles sitting 90 degrees apart. Their mutual electromagnetic repulsion physically pushes them away from one another.
That underlying force literally strains the quantum wave functions.
It bends the probability clouds outward, warping the bond angle from the theoretically perfect 90 degrees out to exactly 105 degrees.
The math doesn't fail at all. It perfectly accommodates the competing forces.
The pure probability clouds establish the 90-degree baseline scaffolding, and the subsequent electrostatic repulsion between the exposed protons stretches that scaffolding to the 105-degree reality.
It highlights how chemistry is just applied quantum mechanics. Every physical property emerges from these competing probabilities and repulsions.
Every single one.
So what does this all mean? Let's take a step back and survey the ground we have covered today.
We started with abstract blackboard scribbles, the dense calculus of the Schrödinger equation.
By simply trusting the math through spherical coordinates, negative energy bounds, the centrifugal pseudopotential, and the Pauli exclusion principle, we organically built the entire periodic table of elements.
It is arguably one of the greatest intellectual triumphs of the 20th century. The Schrödinger equation is not merely an academic exercise used to torture physics students.
It is the literal operational source code for atomic spectra, the rules of chemistry, and the precise 105-degree shape of the water molecule sitting in your glass.
Beautifully said.
And that leads me to a final thought I want to leave you with. Something for you to mull over after this deep dive ends.
I love a good final thought.
We began by acknowledging the reassuring, solid reality of a physical glass of water. But if the rigid, directed valences of chemistry, and by extension, the heavy, solid feeling of the desk you are sitting at, or the physical wetness of the water you drink, if all of that macroscopic experience is fundamentally just the result of invisible probability clouds forcefully straining against each other to minimize their negative energy.
What does that mean for the illusion of solidity in our everyday lives?
Exactly. It absolutely challenges the definition of what it means to touch something.
We aren't really touching anything at all.
It is all just math pushing back against math. The solid world is essentially just a web of mathematical boundaries. Think about that the next time you pour yourself a glass. Until next time, keep diving deep.
What if, right now, the solid wall you lean against isn't, a physical object at all, but just a mathematical average of billions of blurry, totally uncertain guesses?
I mean, it is a profoundly weird thought, but it's actually exactly how reality works at the deepest level.
Yeah, and today, we are going to see exactly how that happens. We're taking a deep dive into the hidden grammar of quantum mechanics. Specifically, we're looking at something physicists call operators.
Which is honestly the perfect subject to dissect, because anyone trying to, read up on quantum physics inevitably hits this massive wall of bizarre notation.
Oh, totally.
It doesn't look anything like standard algebra. The rules we rely on to describe everyday reality just seem to, they just vanish.
They literally break down. I mean, the ordinary math we use to calculate, say, the speed of a car or the trajectory of a rocket, it stops functioning when you zoom in on an electron.
Right, it completely breaks.
So to understand what replaces those classical rules, we've pulled a stack of notes from the legendary Feynman lectures on physics. Specifically, Volume 3, Chapter 20.
A classic.
Yeah, absolute classic. Our mission today is to walk through how physicists mathematically describe the impossible.
Okay, let's unpack this. Because before we can even talk about how things move or change in a quantum system, we have to figure out how to, like, describe their existence in the first place, right?
Yeah, that's the foundational hurdle, really. In classical physics, describing a physical system is straightforward. If you want to describe a satellite orbiting the Earth, you just list its coordinates.
Where it is on the X, Y, and Z axis.
Exactly, that and its momentum. You just write down the numbers. But in quantum mechanics, you simply cannot pin down a particle with a tidy list of coordinates. It just doesn't work.
Because it's a probability cloud.
Right. So instead, the entire physical situation is encapsulated in something called the state vector. Mathematically, it's written using a vertical bar, the Greek letter Ci, and an angled bracket. And we should clarify immediately for anyone listening, even though it has the word vector in the name, this state vector has absolutely nothing to do with geometric arrows pointing through three-dimensional space.
Oh, yeah, no.
It does not point up or right or forward.
Nope.
It's a completely abstract symbol. It stands for a physical state encapsulating all the probabilities of a system, but it does not exist on a physical grid.
No, it's essentially a comprehensive mathematical placeholder. But, having a static label isn't enough to actually do physics.
Right. You need to see what it does.
Exactly.
Yeah.
If you have a quantum state and you want to analyze it or, say, rotate it or project it forward in time to see what happens next, you need a mechanism to mathematically process that transition. And that is the job of the operator.
Written with a little hat over a letter, right? Like an A with a tiny triangle on top.
Yep, the little hat.
And the core rule governing this entire system is actually really elegant. Performing an operation on a state produces a new state. That's it. You take operator A, you apply it to state Pi, and you get state Phi.
That is the fundamental sentence structure we are working with here. Operator acts on state equals new state.
I find it helpful to think of it in terms of, like, software.
Oh, how so?
So imagine the state vector is a raw data file, say a
Yeah.
massive uncompressed image file. It's a noun. The operator is a specific software command, a verb, like apply high-pass filter or invert colors.
Okay, I like that.
You start with your raw file, you run the process, and you get a completely new mathematically transformed file as the output. And what's interesting is that this new state, it might just be an artificial intermediate step in your calculation.
Right, it doesn't even have to be a real physical thing.
Exactly. It doesn't have to represent a state you'd naturally find in the physical world, but it provides the necessary bridge to calculate the transition you're analyzing.
If we connect this to the bigger picture, the reason physicists adopted this highly abstract, verb acting on noun notation is precisely because of the freedom it offers.
Freedom from what?
Well, it avoids forcing the physicist to pick a specific coordinate system or a particular set of base states right out of the gate. Think about the leap classical physicists made when they started writing generalized vector equations, like vector cross vector B.
Oh, right. Instead of writing out all the tiny components.
Exactly. They did that to describe the underlying reality of the physics without getting bogged down in writing out massive, messy lists of individual X, Y, and Z components for every single calculation.
So the operator notation is just a highly sophisticated way of writing the underlying logic of the quantum universe.
Without committing to the specific grid lines of physical space.
Exactly. That structural freedom makes total sense. But, it does leave us hanging on the practical side of it.
How so?
Well, we have this elegant, abstract mathematical language of states and operations. Yet eventually, a physicist has to go into a lab and measure a real number. How do we pull actual measurable quantities like the energy of a system out of this pure abstraction?
Well, measuring energy in the quantum realm is notoriously tricky. If a system happens to be in a perfectly stable, stationary state, then measuring its energy will give you a single definite number.
But I'm guessing most things aren't perfectly stable.
No, the vast majority of systems are dynamic and non-stationary.
Which means if you measure the energy of that same system repeatedly, you won't get the same number twice.
Oh, whoa.
You get a completely different result with every measurement, which, that sounds totally unworkable for trying to establish scientific laws.
It would be unworkable if we only measured it once. You might take 1,000 measurements and end up with a wide scattershot of different energy readings. But the quantum framework dictates that if you average out all those varied measurements, you arrive at a highly predictable, consistent value.
Oh, the average stabilizes.
Exactly. We call this the expectation value, which in this case is the average energy. And operators give us a direct mathematical shortcut to find this average without needing to physically perform 1,000 measurements.
And this is where we run into the mathematical setup known as the sandwich.
The famous sandwich, yes.
If you want to extract the average energy out of a given state, you take the state vector and you sandwich the energy operator, which is called a Hamiltonian, right?
Yes, the Hamiltonian.
Right. You sandwich the Hamiltonian right in the middle. You project the state on the left, drop the operator in the middle, and place the original state on the right. Evaluating that expression directly spits out the expectation value.
It's remarkably efficient.
But wait, working through this logic, if a physicist is studying a complex system, they might not know the true energy states to begin with. Like, if we don't already know the exact details of the system, how can sandwiching an unknown state give us a useful average?
That gets right to the heart of why this framework is so powerful in practice. The math provides a loophole, best illustrated by the helium atom trick.
Okay, lay it on me.
So a helium atom has two electrons that interact not just with the nucleus, but, with each other. The internal repulsion makes the math incredibly complex, so complex, in fact, that you cannot write a perfectly exact wave equation for it.
So nature basically refuses to hand over the clean analytic solution.
Exactly. So physicists use the expectation value sandwich to cheat the system. Since they don't know the true state, they literally guess.
Wait, they just guess the math.
Yep. They construct a mathematically plausible wave function that looks like it should describe the electrons, and they sandwich the Hamiltonian operator between this guessed state to calculate the average energy.
But how do they know if the guess is any good?
Because it's only a guess, the fundamental laws of quantum mechanics guarantee that the calculated energy will be higher than the true lowest possible energy of the actual ground state.
Oh, so it operates like a calibration loop.
Yeah.
You take your estimated state, you tweak a spatial parameter or adjust the spread of the probability,
Right.
and you run the sandwich calculation again. And if the new average energy output is lower than the previous one, you know your modified guess is closer to physical reality.
You just iterate, continually tweaking the mathematical shape of the guess to drive the energy lower and lower until you hit floor. Precisely. They approximate the true ground state of helium to an... Yeah, it's where we finally map the abstract probability of our quantum state onto the physical dimensions of space.
So imagine mapping out the probability of finding a localized particle, say an electron, trapped inside an atom on a standard graph. The horizontal axis represents physical space, and the line on the graph forms a curve, peaking like a hill.
Right, a standard bell curve shape, for instance.
That curve represents the probability density. The higher the peak, the more likely you are to find the electron at that specific location in space.
And if we want to use an operator to find the average position of this electron, the operation in this coordinate representation is straightforward. Finding the average position is mathematically identical to finding the center of gravity of the area under that probability curve.
Oh, okay.
The operator for position, the mathematical action you apply to the wave function, is simply multiplying the wave function by the coordinate x.
So position is just direct multiplication. It's easy. But momentum, that's a totally different story. If I'm reasoning through this, momentum in quantum mechanics is fundamentally tied to the wavelength of the particle's probability amplitude.
Yes.
So to find momentum, you have to extract the spatial frequency of that wave. So you can't just multiply it by a static number. The operator for momentum has to analyze how the wave changes across space.
That is exactly the distinction. The momentum operator is not a simple multiplication, it is an algebraic differential operator. Specifically, to extract the momentum, the operation you must perform is taking the spatial derivative of the wave function.
You measure the rate of change.
Exactly, the slope of the probability wave across the coordinate x.
In doing so involves multiplying that derivative by Planck's constant divided by I.
Huh.
But, setting the specific constants aside, the core realization is that momentum is a derivative across space.
And that single realization that position is a multiplication, but momentum is a spatial derivative, that is the catalyst for the most profound anomaly in all of quantum mechanics.
Because things get incredibly strange when we stop looking at a single dimension and start mixing position and momentum together in three-dimensional space.
They really do.
To see how this breaks classical logic, we need to look at angular momentum. Imagine a particle spinning or orbiting, moving through an x and y coordinate system. To figure out the operator for angular momentum, you have to analyze how the state changes when you rotate the coordinate system itself by a tiny infinitesimal angle around the z-axis. Let's call that tiny twist epsilon.
Right, epsilon. When you apply that infinitesimal rotation, the coordinates mapping the particle shift. A point that was originally located at purely x and y moves to a new position.
Just geometrically shifting over.
Exactly. The new x-coordinate becomes the old x minus a tiny fraction of y, and the new y-coordinate becomes the old y plus a tiny fraction of x.
Okay, I can picture that.
This geometric reality, the visual shifting of points during a rotation, strictly dictates the mathematical operator for angular momentum. It forces the operator to be a specific combination of position and momentum. X times the momentum of y minus y times the momentum of x.
Which maps perfectly onto the classical physics formula for angular momentum. The classical structure is preserved, but here's where it gets really interesting. In the classical world, the order of multiplication is entirely irrelevant.
Completely irrelevant.
5 times 4 is 20, 4 times 5 is 20. If you multiply a particle's position x by its momentum, or multiply its momentum by x, the result is identical. If you subtract one from the other, they cancel out perfectly to 0.
But in the quantum realm, we just established that momentum isn't a static number. Momentum is an instruction to take a spatial derivative.
Right.
And when you mix derivatives with multiplication, the order absolutely dictates the outcome. Taking a derivative of a wave and then multiplying that result by x is fundamentally a different operation than multiplying the wave by x first, and then taking the derivative of that combined product.
Right, because if you multiply by x first, the derivative then has to act on both x and the wave function simultaneously using the product rule from calculus. The outcomes diverge.
They absolutely diverge.
So when you take the quantum operator for position, multiply it by the quantum operator for momentum, and then subtract the reverse order momentum times position, they do not cancel out. You do not get 0.
You are left with a tiny mathematical remainder. Negative Planck's constant divided by I. That remainder is known as the commutation rule.
Wow.
And what's fascinating here is, if that tiny remainder didn't exist, if Planck's constant were exactly 0, then the order of operations wouldn't matter. The classical and quantum results would be completely identical.
We just wouldn't have quantum mechanics at all.
There would be no quantum mechanics. There would be no wave interference, no uncertainty principle, no quantum tunneling. Every piece of quantum weirdness that defies human intuition stems from this one unavoidable mathematical truth: that operator x times operator p is not equal to p times x.
See, but I have to push back on the physical implications of this.
Okay, go for it.
I understand the math of the product rule, sure, but we are supposed to be describing reality. A rule where the order of operations inherently changes the physical state of the universe. It sounds like a glitch in the math, not a feature of physical space. Like, does anything in the macroscopic world actually behave like that?
I know, it defies our standard intuition, but physical space absolutely has this property built into its geometry. Let me give you a physical example.
Please do.
Imagine you are holding a standard hardcover book in front of you, with the front cover facing you and the spine pointing up.
Okay, got the book.
Now, rotate it exactly 90 degrees around the horizontal x-axis, pitching it forward so the front cover faces the floor. Then, take that result and rotate it 90 degrees around the vertical y-axis. Take a mental snapshot of exactly which way the book is facing and where the spine is pointing.
Okay, holding that orientation in my mind.
Now, reset the book to the starting position and do those exact same physical operations, but reverse the order.
So y-axis first.
Right. Rotate the book 90 degrees around the vertical y-axis first. Then, take that result and rotate it 90 degrees around the horizontal x-axis. If you look at the book now, it is resting in a completely different orientation than the first attempt. The spine is pointing in a totally different direction.
Oh, wow. Yes, performing the x rotation then the y rotation creates a completely different final state than doing y then x.
Exactly. Physical space itself dictates that when dealing with rotations and specific geometric transformations, the order of operations fundamentally changes the outcome.
That's incredible.
The quantum commutation rule isn't a math error. It is a profound reflection of the geometry of our reality at the deepest level. The operators are just mathematically expressing the twist of space itself.
That completely reframes how I'm thinking about this. Okay, so we've thoroughly explored how these quantum operators govern static properties like space, angular momentum, and the commutation rules. But the universe is continuously moving.
Right, time doesn't stop.
What happens when we let the clock run? If everything at the fundamental level is governed by blurry probability amplitudes and operators that refuse to commute, does that mean the physics of our daily lives are fundamentally broken? When a baseball flies through the air, It doesn't act like a smeared-out probability wave.
No, it acts like a solid object with a defined trajectory.
Exactly.
The macroscopic world we interact with seems incredibly rigid and predictable. To understand how that predictability emerges from quantum chaos, we have to analyze how the the average of our quantum operators, evolves over time.
Okay.
And in quantum mechanics, the rate of change of any operator's average over time is driven entirely by how that operator interacts with our old friend, the Hamiltonian, the total energy operator.
So we are analyzing the commutator again. We want to see how the operator we're tracking interacts with the energy operator and whether the order of operations leaves a remainder.
Precisely. If an operator commutes perfectly with the energy of the system, meaning the order doesn't matter and the remainder is zero, then that property is conserved. It does not change over time.
But if it doesn't commute?
Then the average value will evolve. So let's run the position operator through this time evolution formula. We are asking the math. How does the average position of this blurry quantum state change as the clock ticks forward?
And what does it say?
When you compute that interaction with the Hamiltonian, the formula spits out the expectation value of momentum divided by the mass of the particle.
Wait a minute. The change in average position over time equals momentum divided by mass. But momentum divided by mass is literally the definition of velocity.
Yep.
That is straight out of a high school classical physics textbook.
It gets even more remarkable. Next, we run the momentum operator through the exact same time evolution formula. We are asking, how does the average momentum of our quantum blur change as time progresses?
Okay, and when you calculate that interaction with the energy operator,
the math yields the negative derivative of the potential energy field.
but the negative spatial derivative of potential energy, the gradient that pushes an object down a hill, that is the exact classical definition of force.
Exactly.
The change in momentum over time equals force.
Yeah.
That is literally force equals mass times acceleration. Newton's second law.
This raises an important question. How is it that the macro world is so predictable? And the answer is staring right at us from these formulas. We just derived the core pillars of classical physics, Newton's laws of motion, strictly using the time evolution of abstract quantum operators.
So what does this all mean? It means Newton's laws aren't describing the absolute deterministic reality of individual particles.
Not at all.
Newton's laws are just describing the macroscopic averages of the underlying quantum chaos. The laws don't capture the uncertain, non-commuting internal details of the atoms, but when you zoom out and average out all those probabilities using these operators, the statistical result perfectly mimics a solid baseball flying in a predictable arc.
The rock-solid classical world is simply the expectation value of the quantum world. And proving that mathematical link actually resolved one of the most intense historical dramas in modern physics.
Oh, back in 1926, right? The physics community was divided by a massive rivalry.
Right. Werner Heisenberg on one side, Erwin Schrödinger on the other.
Heisenberg was trying to decode quantum mechanics, and he realized early on this foundational rule that position times momentum does not equal momentum times position.
Exactly. And to handle this, he built an entirely new theory of quantum mechanics using matrix algebra, because matrices are mathematical grids where the order of multiplication inherently changes the result.
So his theory was abstract, focused on discrete numbers and sudden quantum jumps between energy levels.
And completely independently at almost the exact same time, Schrödinger approached the problem from the perspective of continuous waves. He invents the wave equation, focusing on probability amplitudes flowing smoothly through the coordinate space.
And to the scientific community, they looked like two utterly incompatible theories. Heisenberg's matrices and Schrödinger's differential waves use entirely different mathematical languages and seem to describe entirely different versions of the universe.
But once the dust settled, Schrödinger dug deep into the underlying math of both systems and published a proof showing that they were, in fact, completely identical.
They were the same.
Heisenberg's abstract matrix algebra of non-commuting operators and Schrödinger's spatial differential wave equations were the exact same mathematical truths, just wearing entirely different clothes. Whether you analyze the universe using abstract operator logic or physical coordinate waves, it leads to the exact same physical reality.
A reality where the fundamental nature of existence is intrinsically blurry and uncertain, but where the mathematical averages smooth out to give us the stable, predictable world we experience.
It really is beautiful.
Which brings us perfectly to the end of our journey today. We have mapped out how translating ordinary algebra into the language of operators allows physicists to navigate a chaotic quantum landscape. We've seen how tracking the expectation values of these non-commuting states allows us to predict the average behavior of matter.
And miraculously, we saw how those exact averages scale up to seamlessly become the rock-solid rules of classical physics. It is a stunning framework that bridges the gap between the microscopic realm of probabilities and the macroscopic realm of certainty.
But it does leave me with one final, slightly unnerving thought, and I want you to sit with this. If classical physics, the solid, predictable rules of motion and force we experience every single day, is just the macro-scale average of these underlying non-commuting quantum operators, are we essentially just living in the statistical blur of a fundamentally uncertain universe? The next time you catch a baseball or lean against a solid wall, ask yourself, are you interacting with a physical object, or are you just intercepting an expectation value?
That is a brilliant lens through which to view reality.
Thank you so much for joining us on this deep dive. It is a genuine pleasure to explore these complex layers with someone who truly loves digging into the why behind the what. Keep questioning the structure of the world around you, and we will catch you on the next one.
So, imagine for a second that you're just looking down at your hand.
Okay.
And, you're holding this small, silver-colored block of metal. Just a totally normal piece of metal.
Right, which we usually think of as this chaotic, microscopic city.
Exactly. Trillions of individual atoms, billions of electrons just bouncing around in an absolute frenzy. Completely invisible to the naked eye.
Just a mess of particles doing their own thing.
Yeah, but what if I told you that under the right conditions, you aren't actually holding a collection of individual particles at all?
Wait, really?
Yeah. What if that entire block of metal is actually just one single giant quantum wave?
I mean, that completely shatters our intuition about how the universe works, doesn't it?
It totally does.
Because, we're so used to the macroscopic rules of reality. Like, if you throw a baseball, it follows a clean, predictable arc.
Right, it makes sense.
Yeah, and the weird, murky rules of quantum mechanics where particles act like these fuzzy probability clouds, those are supposed to stay safely locked away in the microscopic realm.
But they don't always stay there. And welcome to today's deep dive. We are so thrilled you've joined us because our mission today is to figure out exactly how those bizarre microscopic rules can actually leak into our everyday human-sized world.
It's a fascinating topic.
It really is. We're looking at a stack of sources centered around this legendary seminar given by the physicist Richard Feynman. Specifically, we're unpacking Chapter 21 from Volume 3 of the Feynman Lectures on Physics.
A classic.
Truly. And we're going to explore this phenomenon where you can literally hold a piece of quantum mechanics right in the palm of your hand.
Oh, normally, quantum mechanics is totally invisible to us. It deals with single particles just doing their own independent, chaotic things.
Right, you can't just look and see the wave function of a single electron.
No, exactly. But the Feynman seminar details this magnificent exception to that rule, which is superconductivity.
Ah, right, superconductivity.
We're looking at what happens when the underlying quantum character of a material suddenly amplifies itself to a massive macroscopic scale.
Okay, let's unpack this a bit, because to understand how a quantum effect gets big, we first have to figure out how electrons stop acting like chaotic individuals.
Right.
Because, as far as I understand basic physics, electrons absolutely hate each other. They have the same negative charge, so they naturally repel.
They do. In the language of quantum mechanics, electrons are what we call fermions.
Fermions.
Yeah, and the defining rule of fermions is that you cannot put more than one of them into the exact same quantum state. They demand their own space.
Like they refuse to share.
Exactly. So in a normal piece of copper wire sitting in your wall right now, those electrons are violently bouncing off each other and crashing into the atomic lattice of the metal.
I picture them like a bunch of solitary bumper cars.
That's a great way to think of it.
You've got all these individual drivers wildly steering around, inevitably slamming into each other and into the walls. And all those collisions generate friction.
Yes, and in electrical terms, that friction is resistance.
Right. That's why your laptop gets hot when you leave it plugged in. You lose all that energy as heat.
But Feynman describes this profound, almost magical change that happens when you take certain metals and lower their temperature down close to absolute zero.
So, super, super cold.
Incredibly cold.
Yeah.
That intense freezing calms the thermal vibration of the metal's atomic lattice, and something entirely counterintuitive happens.
What happens?
Electron speeds through this chilled, positively charged lattice, and as it passes, Its negative charge pulls the positive atom slightly inward.
Wait, it pulls the atoms?
Yeah, it creates this tiny concentrated dent of positive charge in its wake.
Oh, wow. So the first electron actually alters the road it's driving on.
Exactly. And because that tiny dent is positively charged, a second electron flying nearby actually gets sucked into that wake.
No way.
Yeah, the two electrons, which would normally repel each other, are suddenly bound together by this ripple in the metal structure. They form what physicists call a Cooper pair.
Okay, let me see if I have this right. The bumper cars essentially vanish because the moment they pair up, they don't act like fermions anymore.
Precisely.
The sources say they act as bosons, and bosons follow a completely different set of rules, right?
A profoundly different set of rules. Unlike fermions, bosons actually prefer to occupy the exact same quantum state.
They want to share.
Right. And because the temperature is so incredibly low, they all want to drop into the absolute lowest possible energy state available.
So if the fermion electrons are solitary, chaotic bumper cars, the boson-Cooper pairs are like a synchronized marching band.
Yes.
Every single member wants to step with the exact same foot at the exact same time in the exact same uniform.
What's fascinating here is the math behind that synchronization. It's staggering. Millions upon millions of these pairs all lock together.
Just millions of them.
And because they are in the identical state, they stop having individual mathematical identities. They literally merge into a single macroscopic wave function.
So it stops being a microscopic probability cloud.
Exactly. The abstract equation fundamentally changes its physical meaning. Usually, a wave function just calculates the probability of finding a single particle in a specific place.
Right, like a guess of where it might be.
But when billions of electron pairs occupy the exact same state, that mathematical wave becomes a physical reality. It literally maps out the measurable electric charge density and the fluid flow of electrons.
Think about what that means for you listening right now.
Yeah.
We are taking something purely mathematical, an equation that usually only applies to the invisible world of single atoms, and we're scaling it up so massively that you could physically measure its flow.
It's incredible.
Which brings us to the bizarre consequences of having this synchronized marching band in the real world. Because once all these electrons are locked into this single giant wave, they don't behave like normal electricity anymore.
Not at all. The first glaring consequence is absolute zero electrical resistance. Right. Since millions of pairs are locked into the same wave, you can't just knock one pair out of the flow anymore. You'd have to disrupt the entire macroscopic wave all at once.
Which would take a massive amount of energy, I'm assuming.
Exactly. So a current, once started in a superconductor, will theoretically keep flowing forever without losing a single drop of energy.
But reading through the sources, the magnetic interactions are where my brain really started to bend.
Oh, the Meissner effect.
Yeah, the Meissner effect. If you take a chunk of metal, freeze it until it becomes a superconductor, and then bring a magnet near it, the metal violently pushes the magnetic field out. It just expels it entirely from its interior.
It literally turns itself into a perfect magnetic mirror.
A mirror. That's so wild.
It achieves this by spontaneously generating a current on its surface that perfectly cancels out the external magnetic field. And this surface current is incredibly shallow.
How shallow are we talking?
Well, Feynman notes that for a metal like lead, this canceling current lives in a layer thousands of times thinner than a single sheet of paper. It's just this microscopic skin of moving charge.
Okay, hold on. I'm stuck on something here. I really need to challenge this. Because earlier in the source material, Feynman explicitly points out that a quantum wave function doesn't instantly change its phase when a magnetic field is turned on.
Right, it takes time.
Right. So if the wave function hasn't changed yet, how do the electrons know they're supposed to start moving to create that canceling current? Like, what pushes them before the signal even reaches them?
That is a brilliant observation, and it forces us to unpack how quantum mechanics actually treats momentum.
Okay.
In classical physics, momentum is simple. It's mass times velocity. The text calls this MV momentum. It's just physical speed.
Like a car driving down the highway.
Exactly. But in the quantum world, there is a deeper, more fundamental momentum called P momentum.
Let me guess. P momentum is tied to the wave itself.
Yes. P momentum is the dynamical rhythm, the actual phase of the quantum wave function.
Okay, so you have the physical speed and the wave's rhythm.
Right. Now, when you suddenly subject that metal to a magnetic flux, you induce a massive instantaneous electric field. And that electric field acts like a physical shove against the electrons.
So it pushes them.
It immediately alters their physical speed, their MB momentum.
But you just said the waves phase, the p momentum doesn't change right away.
Exactly, and that is the paradox. The physical speed changes, but the quantum rhythm wants to remain untouched.
So how does that work?
The only way the universe balances that contradiction is through something called the vector potential.
Okay, vector potential. The sources bring this up a lot. It's the invisible mathematical field that sits underneath the magnetic field, right?
Think of it as the invisible scaffolding that actually generates the magnetic field. The sudden introduction of this vector potential physically interacts with the electron.
It bridges the gap.
Yes, mathematically and physically. The field itself acts as the enforcer, shifting the electron's physical velocity just enough to ensure the quantum wave phase remains perfectly intact.
Oh, wow.
The electrons don't need to know anything. The geometry of the universe forces their physical speed to change just to protect the wave.
It's like the universe's accounting system instantly balancing the books. And that perfectly shallow surface current is just the physical receipt.
That's a beautiful way to put it.
It is mind-blowing. So we know a solid block of this stuff pushes magnetic fields out. But what if we change the shape? Like, what if this superconductor isn't a solid block?
Like a ring.
Yeah, imagine we drill a hole right down the middle, turning it into a ring.
This is where macroscopic quantum mechanics displays its ultimate elegance. If you cool a superconducting ring while it's sitting inside a magnetic field, the solid part of the ring expels the field, just as before.
Right, the mirror effect.
But some of those magnetic lines of force have nowhere to go, so they get trapped, passing right through the empty hole in the center.
And when you pull the external magnet away, that trapped field just stays behind.
Yes.
It's like a permanent ghost of the magnetic field, locked in place by a supercurrent swirling endlessly around the ring.
Yeah.
But the total amount of that trapped magnetic field, the flux, it can't just be any random amount, can it?
It absolutely cannot. And the reason why brings us back to our marching band.
The bosons.
Right. Those swirling electrons are all sharing one single macroscopic wave function. And a wave has a phase peaks and troughs like ripples on a pond.
Sure.
If you mathematically trace that wave function all the way around the physical ring, when you return to your starting point, the phase must perfectly match up with itself.
Because it's a physical ring.
Yeah.
The wave has to smoothly loop.
Exactly.
It can't have like a jagged, disjointed break where it meets itself.
It has to perfectly overlap. Because of that strict geometric requirement, the trapped magnetic flux inside the hole must be quantized.
Quantized, meaning in chunks.
Right. It can only exist in discrete, specific amounts. Picture perfectly spaced steps on a ladder. You can have 0 trapped flux, or 1 fundamental unit, or 2 units.
But you can never have like 1.5 units.
Never! It's physically impossible because a fractional unit would cause the wave to crash into itself and break.
But here's where it gets really interesting, right? Because the sources describe this unbelievable experiment to actually prove this.
The Dever and Fairbank experiment?
Yes, because predicting it mathematically is one thing, but physically proving a quantum phase loop, that's insane. It was done by Dever and Fairbank at Stanford.
Yes, in 1961.
They wanted to measure these literal quantum steps, but they couldn't just use a normal chunk of metal. They took a tiny copper wire, a wire just a fraction of the thickness of a human hair.
The engineering precision required to pull this off back then is still staggering to think about.
It really is. They electroplated that microscopic wire with a ridiculously thin layer of tin, which becomes a superconductor at incredibly low temperatures.
Right.
So they cool it down. They trap the magnetic field inside this tiny tin pipe, and then they have to measure the trapped magnetic moment. Do you know how they did it? They physically jiggled the wire up and down inside a pair of coils. Feynman actually compares it to a sewing machine needle, moving 100 times a second.
Jiggling a frozen wire to induce a tiny voltage just to catch a glimpse of a macroscopic quantum wave.
Measuring the physical footprints of invisible math. But when Dever and Fairbank finally looked at the data, there was a massive twist.
Oh, the Fritz London prediction.
Yeah. Before this experiment, a famous physicist named Fritz London had done the math to predict exactly how big that fundamental step on the ladder should be.
Right.
But the Stanford team measured a unit that was exactly half of what London predicted. Not close. Exactly half. Did London just, mess up the equation?
If we connect this to the bigger picture, he didn't mess up the math, he just didn't have the whole story yet.
What was he missing?
Fritz London made his prediction years before anyone understood the mechanism of superconductivity. He assumed that the electrical current was being carried by single electrons.
The bumper cars.
Right. But by 1961, the Bardeen-Cooper-Schrieffer theory had been published. We finally understood how lattice vibrations created those positive dents, leading to Cooper pairs.
So the current wasn't being carried by single electrons anymore.
No, it was being carried by paired bosons.
And so the electrical charge carrying the wave isn't one unit, it's two.
Exactly. The charge variable sits in the denominator of the equation for the flux quantum. So when you replace the charge of one electron with the charge of two,
The total fundamental unit of trapped magnetic flux is sliced exactly in half.
yes. When that data came off the Stanford instruments, it was a total revelation. It proved, on a macroscopic, measurable scale, that electrons were literally pairing up to create the current.
You jiggle a tiny wire like a sewing machine, and you prove beyond a shadow of a doubt that invisible electron pairs are sharing a single wave function. I mean, the sheer ingenuity of it.
It's beautiful science.
Okay, so we've seen what happens when the wave function loops around a physical hole. Let's push it even further. What happens if we build a wall?
A wall.
Yeah, what if you take two superconductors and place a microscopic layer of insulating material, an absolute roadblock right between them?
Ah, you're describing a Josephson junction, named after the physicist Brian Josephson.
Oh.
In a normal electrical circuit, an insulator acts as a brick wall. The electricity stops dead. But remember, we aren't dealing with normal electricity here.
We're dealing with the massive wave.
Exactly, a massive quantum wave function. And quantum waves have a habit of ignoring brick walls through a process called tunneling.
Tunneling just sounds like sci-fi to me.
Yep.
How does a wave just bypass a physical insulator?
Well, when a quantum wave hits a barrier, it doesn't just instantly drop to zero. Instead, the amplitude of the wave decays exponentially inside the barrier.
So it fades out.
It fades out. But if the insulating wall is incredibly thin, just a few atoms wide, the wave doesn't have enough space to completely fade away. A faint whisper of the wave survives and emerges on the other side, allowing the wave functions of the two separate superconductors to suddenly link up. The wave bleeds right through the gap.
And the rules for how this bleeding works are incredibly weird. The sources point out that if you apply absolutely zero voltage across this insulated gap, like no electrical pressure pushing the electrons at all, a steady current just flows right through the wall anyway.
It flows because the massive wave functions on either side naturally want to equalize their phases. They literally reach across the gap to balance each other out.
But if you DO apply a constant flat DC voltage to the junction, meaning you actively push the electrons, you don't get a steady forward current.
No, you don't.
Instead, you get rapid microscopic oscillations back and forth, which average out to zero net forward current. You apply pressure, and the forward momentum essentially flatlines into an oscillation.
It completely reverses our understanding of how circuits should work. And physicists realized they could use these weird rules to test the deepest aspects of reality through quantum interference.
This is where we get the split river analogy, right?
Yes.
Imagine a river of superconducting current. It flows along and then hits an island, splitting into two separate paths, upper path and a lower path.
Okay.
On each of those paths, you place a Josephson junction. Then, past the island, the two paths recombine back into one river. So what does this all mean for us?
Well, this raises an important question about what is physically real. I consider this the ultimate experiment outlined in these sources.
Okay, lay it on me.
Remember the vector potential, the mathematical scaffolding we discussed earlier.
Yeah, the invisible field that acted as the enforcer during the Meissner effect.
Yes. For decades, physicists debated whether the vector potential was a literal physical field existing in the real world, or if it was just a convenient mathematical trick to make the equations work.
Is math on a chalkboard.
Exactly. To finally settle the debate, researchers used that exact split river circuit you just described. But right in the middle, in the empty space between the upper and lower paths, they placed a tiny solenoid.
Which is like a microscopic coil of wire that generates a magnetic field.
Right. But here is the critical detail. The magnetic field generated by that coil is entirely locked inside the coil.
So it never physically touches the superconducting wires.
Never. The actual magnetic force is completely quarantined.
So if only the physical magnetic field was real, the superconducting circuit shouldn't react at all. It shouldn't even know the coil is there.
Precisely. But the vector potential, the invisible scaffolding that creates the magnet isn't locked inside. It bleeds out.
It spreads through space.
Yes, and it actually touches the upper and lower superconducting wires.
And because it touches the wires, it physically alters the rhythm of the quantum wave function traveling along those two paths.
Which means when those two separate paths finally recombine past the island, their rhythms are slightly out of sync. They interfere with each other.
Okay.
Sometimes the peaks line up and they add together, and sometimes a peak meets a trough and they cancel out.
So what did they see when they ran the experiment?
When researchers hooked up their instruments to the circuit, they saw the total electrical current oscillating wildly. And those oscillations perfectly track the changes in the magnetic flux trapped inside that tiny quarantined coil.
Even though the magnetic field never touched the circuit, the interference proved it.
Unequivocally. It proved that the invisible vector potential is a literal physical entity vibrating in the space around us, capable of reaching out and altering the phase of a quantum wave.
It's like feeling a breeze from a fan that is hermetically sealed inside a glass box. It shouldn't be possible, yet the math demanded it, and the physical reality proved it.
It's amazing.
But on a practical level, this isn't just about winning philosophical physics debates. The sources highlight that this exact split-river setup allows humanity to build the most hypersensitive magnetometers ever conceived.
We call them SQUIDs, superconducting quantum interference devices.
Squids. I love that.
Because the quantum interference at those junctions is so delicately balanced, you can use them to detect magnetic field changes that are staggeringly small.
How small?
We are talking about detecting the faint magnetic field generated by a single human brain from across a room.
That is absurd.
A level of sensitivity almost beyond human comprehension, all driven by macroscopic quantum interference.
Which really brings into focus the sheer scale of the journey we've taken today. I mean, we started with the murky, abstract math of chaotic, solitary electrons, bumper cars causing heat and friction.
Right.
And we saw how, through the freezing manipulation of atomic structures, they sync up into a marching band, becoming a single macroscopic quantum wave you can literally hold in your hand.
A wave that violently expels magnetic fields to act as a perfect mirror.
A wave that physically traps quantized, perfectly stepped ghosts of magnetic fields inside tiny rings.
And a wave that can whisper through solid brick walls to prove the existence of invisible fields.
Eventually giving us the ability to read the magnetic whispers of the human mind. We are literally hijacking nature at its most delicate, fundamental level and pulling it up into our world.
It really is the ultimate triumph of taking the bizarre rules of quantum probability and forcing them to operate on a classical human scale.
But, there's one final thought. I want to leave you with something to ponder as you look around your everyday life. The sources make one thing abundantly clear. This extreme quantum synchronization is incredibly fragile.
Extremely.
The magic relies entirely on absolutely freezing temperatures. The moment you introduce even a tiny bit of thermal heat, the vibration smashes those delicate Cooper pairs apart.
The marching band breaks rank.
Exactly. The wave collapses, and everything reverts back into the resistant normal reality of solitary bumper cars. Thermal agitation destroys the wave.
It is the great barrier keeping the quantum world confined to cryogenic laboratories.
But what if it wasn't? Scientists today are relentlessly hunting for the holy grail of physics. Room temperature superconductivity. Imagine for a second that we crack that code.
That changes everything.
The obvious benefit is power grids with zero energy loss, which would revolutionize the planet. But think bigger. If we didn't need liquid nitrogen to keep the wave alive, we would literally be weaving macroscopic quantum wave functions into the warm, everyday fabric of our homes, our cell phones, our cities.
The bizarre rules of quantum mechanics wouldn't be something we just study in extreme isolation. They would be the very infrastructure we walk on.
If quantum weirdness no longer required a deep freeze to survive, how would a world built out of macroscopic quantum circuits change your daily reality?
It forces you to look at every piece of metal around you just a little bit differently.
It really does. Thanks for taking this deep dive with us today. Keep questioning the visible world around you, because the invisible one is always waiting to leak through.